Sepertinya sama, tata belas mata yang masih yang lama. Seketika kembali ku jatuh cinta siapa dia sampai air mata sia-sia dari begitu banyak manusia melihat lagi-lagi dia yang baik. Tapi ku terjaga rindukan dirinya sih saat kecewa. Lupa bahwa lupakannya tak mudah tapi yang ku tak bisa berpindah sama tatapan hati masih yang lama. Ajak bicara seketika kembali ku jatuh cinta dia sudah air mata sia-sia hanya di hatiku ini terbaik tetap selalu ada singgasana tempat untuknya sepertinya sama matanya masih yang kau ajak bicara seketika kembali ku jatuh cinta tinggal cinta sakit air mata. Oh dia, wajib juga tentu. Sampai saat ini tak terfikir olehku. Aku pernah beri rasa pada orang seperti seandainya sejak awal tak ku yakinkan diriku. Tutur kata yang sempurna tak sebaik yang kukira. Andai ku tahu semua akan sia-sia, takkan ku terima cinta sesama. Bagaimana denganku terlanjur mencintaimu yang datang beri harapan lalu pergi dan menghilang. Tak terfikirkan olehmu, hatiku hancur karena tanpa sedikit alasan, pergi tanpa berpamitan. Takkan ku terima cinta sesaatku telah sejak awal tak ku yakinkan diriku. Tutur kata yang sempurna, rasa baik yang ku kira. Andai ku tahu semua akan sia-sia, takkan ku terima cinta sesaatmu. Aku lanjut mencintaimu yang tak pernah tak dipikirkan olehmu, tapi ku lanjut dalammu tanpa sedikit alasan, pergi tanpa berpamitan. Takkan ku terima cinta sesaatmu, tidak aku bertemu dengan cinta sendiri. Aku tunjukkan caramu seolah cintaiku. Lanjut mencintaimu, menanti kedatanganmu mengisi sepiku. Lama terasa waktu bergulir karena dirimu tak bersamaku. Oh Tuhan, bawa dia kembali bersamaku, di sini menjagaku selalu. Dengarlah doaku yang tak pernah meminta bahwa dia kembali bersamanya sesaat. Masih terasa hembus nafasmu saat hubungan melipur laraku. Terasa semakin dalam rasa rinduku pada dirimu. Oh Tuhan, bawa dia kembali bersama, di sini menjagaku selalu. Jangan doaku yang tak pernah meminta bahwa dia kembali bersamanya sesaat. Oh Tuhan, tolonglah bawa dia kembali bersama di sini menjawab semua doaku yang tak Kita adalah dua insan penuh cinta. Di awal tercipta kisah kita, manis tuturmu buatku terpana. Bagiku kau sempurna. Memang benar semua kata mereka. Dariku takkan cinta. Hanya sekali kau hianati. Sudah cukup bertahan hati. Mati-mati aku membelamu di depan mereka. Walau sakit tetap ku percaya kau beda dari lainnya. Bisa-bisaku dibohongi, sayang ini tetap sama. Tuhan ini cinta atau bodoh. Habis pikir dengan sifatmu itu, berulang ku maafkan, berulang lagi satu-satunya sakit tenang. Sayangku belamu di depan mereka. Membelamu di depan mereka. Sakit tetap ku percaya kau beda dari lainnya. Semua dibohongi, sayang ini sama. Tuhan ini cinta atau bodoh. Kau beda dari lainnya. katamu. Melihatmu bahagia, satu hal yang terindah, anugerah cinta yang pernah ku punya. Kau buatku percaya ketulusan cinta, seakan kisah sempurna kan tiba. Masih jelas teringat pelukanmu yang hangat, seakan semua tak mungkin menghilang. Kini hanya kenangan yang telah kau tinggalkan, tak tersisa lagi waktu bersama. Mengapa masih ada bisa rasa di dada, di saat kau pergi begitu saja. Mampukah ku bertahan tanpa hadirmu sayang? Tuhan, sampaikan rindu untuknya. Masih jelas teringat pelukanmu yang hangat, seakan semua tak mungkin menghilang. Ini hanya kenangan yang kau tinggalkan, tak tersisa lagi waktu bersama. Mengapa masih ada bisa rasa di dada, di saat kau pergi begitu saja. Mampukah tanpa hadirmu sayang? Tuhan, sampaikan rinduku untuknya. Semua cinta yang kau beri, kau katakan sampai kemarin. Sampaikan rinduku untukmu. Indah semua cerita yang telah terlewati dalam satu cinta, Kita yang pernah bermimpi jalani semua hanya ada kita. Namun ternyata pada akhirnya tak mungkin bisa ku paksa. Restunya tak berpihak pada kita. Mungkinkah aku meminta bisa kita selamanya tak terlintas dalam benakku bila hariku tanpamu. Cara telah ku coba pertahankan cinta kita, selalu ku titipkan dalam doaku, tapi ku tak mampu melawan restu. Ternyata pada akhirnya tak mungkin bisa ku paksa. Rasanya tak berpihak pada kita. Mungkinkah bisa kita selamanya terlintas awas namun bila hari bersamamu segala cara kamu coba bertahankan cinta kita selalu berikan aku tapi ku tak mampu melawan aku tersiksa melihat semuanya berubah. Tak mau tahu bagaimana hati ini tanpa cintamu. Oh, di mana aku bisa tahu dirimu yang dulu cinta dan anggap aku ada. Jika kau minta aku menjadi yang dari seluruh memori hidupmu, aku lakukan semua walau tak mungkin sanggup bohongi hatiku.
que hacemos contemplación. Que va todo el mundo. That's gotta be that we want to, but I pay a piano when I could. You used to go to the family, no, with that he had it all with the chino, it's you. Yeah, so she could now with that. And of the guy, she got it.
Cek.
Kaki, 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 hidung, hidung, hijau, kaki, bisa, kaki, mudah,
trên đường hàng Sampun Power supply, multimeter, and oscilloscope are used for the standard electrical test. In a typical industry in the lab, we need multiple of these devices, but the problem is they have excessive power, limited output, expensive, bulky, cumbersome, and inconvenient. And the solution is XDAC, a sophisticated source measurement unit for low power applications from simple electronic circuits to complex photonic integrated circuits. We also offer a variety of channel options ranging from 8 to 40, 80, and 120. We are also beginning to develop our product into a chip scale version with a wide range of imaginable applications. Start from sensing and instrumentation, telecommunications, machine learning, and quantum computing. If you're interested, we also provide a live demo unit and a GUI simulator to give you a better understanding of our product. You can find more information on our website. We are waiting for you. Together, we are unlocking the power of light.
At FLIR, we asked a simple question. Why choose between what you see and what you don't? For years, we've relied on visible light to define structure. But structure alone doesn't tell the full story. Infrared reveals transformation, heat radiating from machinery, stress forming in materials, energy shifting before failure occurs. But these two perspectives have always been separate until now. Introducing imaging system to capture high-speed visible light and the revealing power of infrared together in perfect sync. Every pixel aligned in time and space, every moment captured with absolute precision. Now, researchers and engineers can see structure and transformation at the same time, in real time, without the need to piece together separate data sets. FLIR Mix doesn't just show you the moment, it shows you what makes the moment happen. With up to 1,000 frames per second, every reaction, every shift in temperature, every hidden change is revealed, giving you the power to analyze change as it unfolds. No more wasted hours aligning data streams. No more uncertainty. Just faster, more accurate insights, so you can focus on results. FLIR Research Studio, visible and infrared processed and analyzed in one system, eliminating complexity and delivering seamless integration. One synchronized dataset for scientists, engineers, and researchers across material science, electronics testing, renewable energy, and high-speed dynamics. Patterns once missed, now visible. Failures before they happen, now preventable. The future of imaging, now here. For researchers, for engineers, for visionaries. Because when two worlds come
Together, we are unlocking the power of light. These devices. But the problem is they have excessive power, limited output, expensive, bulky, cumbersome, and inconvenient. And the solution is XDAC, a sophisticated source measurement unit for low power applications from simple electronic circuits to complex photonic integrated circuit. We also offer a variety of channel options ranging from 8 to 40, 80, and 120. We are also beginning to develop our product into a chip scale version with a wide range of imaginable applications. Start from sensing and instrumentation, telecommunications, machine learning, and quantum computing. If you're interested, we also provide a live demo unit and a GUI simulator to give you a better understanding of our product. You can find more information on our website. We are waiting for you. Together, we are unlocking the power of light.
If you're designing photonic systems, ANSYS Lumerical lights the way. From virtual reality to display technology, from auto sensors to smartphone cameras, from laser design to quantum computing, from 5G to data centers, is a world leader in photonic simulation. We've been helping engineers meet product development deadlines for nearly 20 years, collaborating with leading third-party tool providers to create new workflows, building better photonic systems on time, on spec, and with higher performance. Referenced in over 15,000 scientific papers and patents, Lumerical has been run in close to 30 million simulations by roughly 50,000 different users, by 90% of the leading research universities in the world, and by all 10 of the top IT index companies. If you're designing photonic systems at the component and circuit levels, ANSYS Lumerical is a complete cloud-ready simulation solution. It's easy to learn and deploy, innovating new solutions and techniques. For reliability, speed, and accuracy, there's only one true leader in light, ANSYS Lumerical.
Power supply, multimeter, and oscilloscope are used for the standard electrical test. In a typical industry in the lab, we need multiple of these devices, but the problem is they have excessive power, limited output, expensive, bulky, cumbersome, and inconvenient. And the solution is XDAC, a sophisticated source measurement unit for low power applications from simple electronic circuits to complex photonic integrated circuits. We also offer a variety of channel options ranging from 8 to 40, 80, and 120. We are also beginning to develop our product into a chip scale version with a wide range of imaginable applications. Start from sensing and instrumentation, telecommunications, machine learning, and quantum computing. If you're interested, we also provide a live demo unit and a GUI simulator to give you a better understanding of our product. You can find more information on our website. We are waiting for you. Together, we are unlocking the power of light.
Good morning to all participants and all speakers. Welcome to the third days of ISMOA, sorry. And now this is the end of our symposium day. So in the sessions, we are honored by joining of 7 speakers. Each speaker will be delivers a lecture lasting approximately 13 minutes. And I would like to inform that our ISMOA have a link tree, and you can upload your publications, vote for our favorite speakers, and download some photos of documentations from the ISMOA activities. Our link tree can you be accessed by linktree/ISMOA 2025.
Without further delay, let's start our first session with our moderator, Professor Sean Fengsen. Please welcome Professor Sean Fengsen. The stage and time is yours.
Okay, let's begin our session 5. The first speaker is Carsten Loxhall. Yes, right. From the Karlsruhe Institute of Technology, Germany. Let's welcome.
So welcome everybody also from my side to this presentations here. I'm very happy to be here. I want to thank, of course, Alex and all the other persons involved in the organization to give me the opportunity to travel here to Bali and to wonderful Indonesia and to meet so many friends and colleagues here. Yeah. The topic that I'm going to speak today here about is inverse design for nanophotonic systems and devices. And this reflects a little bit on the question of how to find a structure actually that serves a predefined optical purpose or that provides a predefined optical response. And we do this particular in the context of 3D nanoprinting, because as I will try to motivate that there's a lot of opportunities and you have a lot of degrees of freedom to really shape structures to give you a kind of desired response. So just to enter that sort of presentation here, I just would like to highlight a little bit what's the challenge of inverse design. So how does this actually work? So usually we start with a given geometry of a structure that is parameterized and characterized then by a certain number of degrees of freedom. So the way it's illustrated here is that these degrees of freedom really have a kind of interpretation in terms of geometrical parameters, but indeed this is not necessary. We will also later have examples where these sort of degrees of freedoms are parameters in some sort of latent space and they don't have a physical meaning. The only important thing is that you can translate these degrees of freedom into a given geometry that a structure is going to have. So this is like an object that you can consider further. So once you have this object, so you take basically your Maxwell solver of preference and calculate the optical response due to a given excitation. And from this electromagnetic field that you can evaluate then everywhere in space, so technically you can derive then an objective function. So that tells you how good a given structure is with respect to a kind of predefined purpose. And then the main task of any optimization algorithm is basically to take all the previous evaluations, so of the optical response of a given structure parameterized by a certain set of numbers, and try to come up with a new parameterization that serves the purpose presumably a bit better. And whenever you have done this, so you can close this sort of design cycle and repeat this sort of loop from the very first beginning. And then the hope is that by the hope is by iterating through the cycle so multiple times, so you come up at the end with a structure that has the most favorable response. So there are a few constraints that we have to keep in mind, which limit, let's say, our ability to work here. And that is, we only have like a limited amount of time available and also finite computational resources. Yeah? So, and this means that the sort of optimization algorithm needs to be as efficient as possible in order to come up with good solutions. So moreover, we want to optimize the structure actually adapted to a certain fabrication technique. Because if you go then subsequently to your experimental colleagues, and you tell them, please fabricate a structure, and they will tell you this is impossible with the technology that we have at hand, then there is not much use, because then anyhow you have to start from scratch. So you want to take basically the constraints that come from the fabrication process already into account when designing the structures. And the last thing is a bit more of a philosophical point of view. So we like to have this design independent, let's say, of human intervention. So to avoid repeating designs actually that have been known in the past already, but we really want to let the machine find the optimal design independent of us. And this sort of inverse design, so in our case, this takes place mostly in the context of 3D printing on the nanoscale, yes, or two-photon polymerization. So which is a technique maybe made prominent by Satoshi Kawata by the end of the 90s. So where in essence, so you take a strongly focused laser beam, you focus this into a liquid polymer. So a chemical reaction is going to take place, and the liquid polymer is going to solidify. And by changing then the spatial position of your focused laser beam, you can really provide three-dimensional materials here with desired geometries. And just to give you a bit of illustration of what type of dimension do we speak here. So we can speak of typical feature sizes, let's say down to 100 nanometer. But even if we just say we have a filter size of 1 micrometer, this is already quite small. Because thanks to a pretty large writing speed also and the large footprint and the large height, so we have really here volumetric materials where we can really shape materials on demand. Yeah. And even if we would speak just of a cubical volume, let's say with 1 millimeter side length and 1 micrometer feature size, you would still speak about 1 billion degrees of freedom that such structure is going to have. And then the question is, how exactly actually you are going to fill up these sort of 1 billion degrees of freedom, so these 1 billion boxes with material in order to have a kind of optical response that you would like to see. And this is what we call, let's say, digital blueprints, because we need to provide these digital blueprints to our experimental colleagues so that they can realize this and let's say, give these structures basically a shape that they want. And this is like the challenge. So you have 1 billion degrees of freedom, and then you have to find the most optimal configuration. So out of this sort of nearly infinite parameter space. And because there are then so many degrees of freedom, I would just like to stress that global optimization is not possible anymore, but the only thing that you can do is local optimization. And then basically you end up with a kind of gradient-based inverse design techniques. So where you basically illustrate here the sort of objective function in some sort of parameter space. So you can evaluate this objective function at one particular point in this parameter space. And then you evaluate the gradients of this objective function at this point in parameter space. And this in essence allows you to go actually here from one point in parameter space to a next point in parameter space. So where the objective function is going to be minimized. You can also formulate this as a maximization. I think this doesn't matter for the purpose, but you gradually basically go down in parameter space to the point that fulfills all criteria in the best possible way. And that's why the key challenge for this inverse design is to obtain these gradients. Yeah? So how the sort of objective function changes with respect to any degree of freedom that you're going to toggle in your design. And this is something basically where multiple techniques have been developed and are developed in the past. Yeah. And the choice of method basically is going to depend on a specific problem at hand. And this talk here is structured in such a way that I have 3 different techniques that I'm going to present here that we have been using for this purpose. And on the fly, I can also show you some examples of how we apply this to specific problems. So I'm going to start here with topology optimization. So which is like a well-established tool, basically, yeah, so that relies essentially on 2 full-wave simulations. Yeah. So I have a more technical slide in the following, but the idea is that you have a full-wave simulation and what is called the adjoint simulation. And out of these 2 full-wave simulations, basically, you can calculate the gradients of the objective functions with respect to all degrees of freedom. So there are a lot of filtering techniques basically established in order to handle experimental constraints. And the most urgent problems basically that we have to solve is doing a suitable parameterization for the systems that we can write in 3D with this nanoprinting technique, and also making sure that we have a structural integer object. Yeah, so because we cannot write objects that are free floating in space, so they would just fall down because of gravity. And that's why we need to ensure the sort of structural connectivity in order to provide designs that are really feasible also for realization. The next slide is a bit more technical. It's just like a one-on-one basis of topology optimization, so you get a bit of an idea of how this is formulated also on more rigorous theoretical grounds. So the starting point of all consideration is basically here Maxwell's equations. So where you know your source, so that emits some sort of radiation that is going to interact with a given object. And this object here is described by this material distribution in space. And you're going to obtain from that the electric field distribution. So now our objective function f is now a function of this electric field at any spatial position, depending on however you want this. And then this actual optimization problems basically requires you to minimize this objective function, which is a function here of this electric field, over your degrees of freedom that are given here by the sort of permittivity distribution. And this electric field that appears here is basically subject to that constraint, which in essence is a short formulation of Maxwell's equation. So this M here is the sort of Maxwell operator, this S is just our source, and then we have here our electric field. So now there's a lengthy mathematical derivation, but in a nutshell, you solve in addition also the sort of adjoint problem. And this adjoint problem is very similar like the sort of Maxwell problem here, where we have the sort of transpose Maxwell operator. And the source that you're considering here is the derivative of this objective function with respect to your solution, which is something that you know typically analytically, because you can have a kind of analytical expression, a differentiable expression of this objective function on your electric field. So you know the sort of adjoint source, as it's called, and then you solve the sort of second Maxwell problem to get the sort of adjoint field. And from this adjoint field and the original field, you can calculate the gradients of this objective function with respect to the sort of permittivity. And this is then the key to enter the sort of design loop, so the sort of iteration, so to perform the sort of local gradient descent type algorithm. Yeah. So then exactly, and then you're going to iterate, and there are a lot of filtering technique actually already existing in this method, like accommodating spatial feature sizes and these kind of things. So this can be all formulated in a differentiable way, and then you can consider this. So in the context of 3D nanoprinting, I have two examples that illustrate this a little bit, how this is used. So the first is actually a problem that we already discussed also in some of the presentations, I think yesterday, and that is like a coupling element. Yeah. So we are working on, let's say, integrated photonic circuits also, where people use this 3D nanoprinting to write what is called the sort of photonic wire bonds. And these photonic wire bonds are freeform waveguides, so that connect actually different photonic chips that are made out of different materials. And the reason for that is that you have, let's say, active sources. You do this as 3-5 semiconductors. Passive systems, you use silicon or SiO2-based materials. And instead of combining all these sort of different material platforms within one chip, it's actually technologically more feasible to have this in different chip components and then to connect these parts with these sort of freeform waveguides, which had been coined these photonic wire bonds. And then the problem is that these sort of photonic wire bonds, this is then polymeric waveguides, let's say with a diameter of 1 micrometer or 2 micrometers, something like this. And you need to couple this then to other waveguiding structures that exist in this sort of other material platform. So you can consider here like silicon integrated waveguides, but you can also consider here single mode waveguides. And then you need to design actually this coupling region between these photonic wire bonds and these other waveguiding elements such that you maximize actually transmission, so you have the least losses. And this is the design problem and a bit more of an abstract type of representation. In this particular example, I choose the coupling problem here between a single mode fiber and this photonic wire bond. So we have exactly that kind of situation, so that you have a design region here in the order of 20 micrometer that needs to be designed in order to minimize the reflection or to maximize transmission through this sort of system. In this particular case, I would like to stress that we know, of course, that there's like an analytical solution to this problem, which is like a smooth taper. But the smooth taper usually requires much larger taper lengths in order to reach a high transmission efficiency, which is undesirable because, let's say, chip estate is a kind of precious quantity, and you want to have this coupling region here as short as possible. But of course, we do not need to compromise actually the transmission efficiency of these systems. So this topology optimization basically in this particular case works like this, so that we consider here a rotational symmetric structure, and then it's the outer shape actually of this sort of photonic wire bond that is going to be our degree of freedom. And this is something that we suitably parameterize and then optimize actually in our algorithm. So the final outcome that you have from that sort of consideration is a structure that looks like this. So first of all, you see here that you reach efficiencies in the order of 92%, which would compare also to the efficiency that you get with a tapered structure that has a length of 80 micrometer. Yeah. And the funny thing is now, or this is the way how I understand here this sort of fringe type objects is that this in essence is like a Fabry-Perot, and it's like a Bragg type structure, like a Fabry-Perot type element, so that generates some sort of back reflected light also that destructively interferes actually with reflected light directly at the first facet. So you destructively interfere basically all the reflected light back into the structure thanks to the sort of complicated shape here, and that maximizes indeed then the sort of transmission into the forward direction. And these are then quite complicated shapes. You can also apply this so to other problems in this sort of general context. So this is here a coupling element into a kind of waveguide on top of a SiO2 layer. And this coupling element here should work independent of the polarization. So you would like to come both with X and Y polarization, and you will couple then light as good as possible into the corresponding mode of these waveguides here. And then you can use the sort of topology optimization in order to come up with a kind of spatial distribution of material here in three-dimensional space that serves this purpose particularly well. And then we can see here that basically 90% roughly of the power is going to be coupled at design wavelengths here of 1.55 micrometer for both X and for Y polarization. Yeah, and you can see here also like the field distribution that emerges from that. So this is like a top view, and this is like a cross section, and you can really see that the sort of structure couples the light then here into this waveguide by a suitable arrangement. So nevertheless, this structure here, as we've designed this, and this also has indicating to us that there are limitations, because the structure that we've seen on the previous slide is actually not feasible for fabrication, and because there have been free-floating objects, free-floating material distributions that fall apart basically from gravity or get just washed away. And then there's also the second problem that you also have voids in a kind of bulk material. And this is unfeasible from a practical perspective because the liquid photoresist that remains in these voids is not going to escape. And this is going to spoil the functionality. So that's why you need connectivity of the structure, but you also need connectivity of the voids in order to make sure that all liquid resist that has been unexposed can be released from the structure. And this is something that we have been taking into account also in this sort of design frameworks by performing auxiliary simulations. So that basically only serves the purpose to judge whether the structure is connected or not. Yeah. And we take this sort of output basically as an additional constraint basically as a part of our objective function. And what we technically do here is like we do additional heat simulations. Yeah. So basically we take the structure and we give it a thermal load, and then we put thermal sinks actually to the side of the structure. And then if the structure is well connected, all the thermal load is going to be dissipated. And if it's not connected, then the sort of thermal load leads to an increase in temperature locally, because it cannot release basically its temperature. And that's why, yeah, so then we can basically punish this sort of type of structure. So that's why we interpret now our material distribution as a thermal conductive medium, and we solve such a kind of heat diffusion equation and giving basically a thermal load to the entire structure. And then the sort of objective function that we finally derive is just an integration over the final distribution. And if this is like a large temperature value, then this is not connected. And if this is a low value, then this is very well connected. And this means that now our inverse design technique is a bit more complicated because we have sort of material distribution. So we evaluate here the sort of optical objective function the way we did it before. But now we also have two additional simulations. And so where we basically check of how large actually the sort of heat is that is going to be remain, or that remains in the structure. And also in the complementary structure, which is just the same type of simulation as before. It's just that we reverse basically the distribution of a heat conductivity here, so to measure how good the voids basically are connected. And the only thing that is then a bit challenging also is to balance basically the numbers from these sort of different simulations. So how can we judge actually how good a certain structure is, because these sort of objective functions here, these are just numbers and they are hard to compare. So this is like a typical problem in this multi-physics simulations. So basically here we use like a soft plus function, which basically judges whether a certain objective function is above or below a certain threshold criteria. So if it's below a certain threshold criteria, we don't care anymore about it. And if this is above a certain threshold criteria, then we care about this. And this threshold criteria basically tells us so how to normalize these different objective functions individually. And then we can combine actually the outcome of all these sort of three individual objective functions into a single one, and then we can close the sort of design cycle. Yeah. Okay, so I think the time is running up, so I have to take a bit care that I'm not losing here the orientation. So the second approach that I just want to flash here a little bit is how to use artificial neural networks for similar purposes. Yeah, so which is like a fashionable type of topic, and many people are using this also for their purposes at the moment. So in our case, we are using what they call these Fourier neural operators, yeah, so which we take then at the end as a surrogate solver for Maxwell's equations. So we are not using these sort of artificial neural networks for a specific design problem, because that doesn't make so much sense, because you have to generate a lot of data, so which you can solve the inverse problem actually anyhow. But the sort of Fourier neural operators as a surrogate solver for Maxwell's equations allow us to get a much quicker solution to Maxwell's equations. So in our case, so these are what they call like Fourier neural operators. So where the idea is that you start with a given structure, so you extrapolate this into some sort of higher dimensional space, and then you enter these sort of Fourier blocks, which in essence is a Fourier transformation and then a weighting actually of the individual Fourier harmonics. And then you have a kind of nonlinear activation function. And this is an approach to solve Maxwell's equations then in Fourier space. Yeah, and this makes sense because these Fourier neural operators lead to like wave type solutions because of that sort of spatial filtering in the Fourier space. And this is very much adjusted to the typical way, let's say, the solutions to Maxwell's equations are going to look like. So there's like a bit of an idea here, but in essence, this is like a network that established a sort of structure property relation. So it should predict here the sort of electromagnetic fields, and it does so essentially in Fourier space. So which is like a global convolution basically, or a convolution in reciprocal space at the end of the day. Okay, and then the idea is how do we train actually these neural networks? So how do we generate samples that are feasible also for 3D nanoprinting? And we need to link that also to the electromagnetic field. So we do so by starting here with some sort of random noise distribution. So we do a convolution with type of Gaussian structure, and then we do like a binarization. And it gives us usually this sort of blob type features that are typical elements that occur actually in the sort of 3D nanoprinting. So then we are going to interpret actually the sort of material distribution here as high and low index material, which just corresponds to our polymer and our air as a surrounding. We plug these structures into our Maxwell solver, and then we calculate the sort of electromagnetic fields. And this is the data sets that we are using then for training our neural network. Yeah, and we have these data sets in 2D and 3D. And in 2D, this would be like a scalar type of problem, and in 3D, this is then a full vectorial problem. And just to give you like a bit of a numbers, so we have in this training set, so in the order of 16,000 data sets for 2D and roughly 10,000 data sets for 3D. Okay, so then you train this neural network. And indeed, then this neural network can predict then the electromagnetic fields that emerge from structures that bear similarity to those that are contained also in this training data set. Yeah. So, and this is like a reference solution here with FDTD, and this is the prediction of this Fourier neural operator. And then you see that we have a very nice error here actually everywhere in space, and you can solve Maxwell's equation. So now the actual inverse design has the sort of Fourier neural operator as one component, but it also has one additional aspect. And that is the sort of variational autoencoder here, which basically had been pre-trained separately by taking basically all these geometries here as an input, projecting this into some sort of latent space where we take a vector with 2048 elements, and then predicting again this sort of structure. And the idea why we have been doing this is exactly this way, so that every component actually of our latent vector here is now representing somehow a structure that is similar to those that have been contained in the sort of data set. And this means that this actual design pipeline is just a sort of part here encapsulated in this green box. So you take basically a random distribution, a random vector in this latent space. So you translate this into a structure thanks to this sort of decoder here. You use this Fourier operator to calculate this electromagnetic field. You take your objective function based on these electromagnetic fields, and then technically use backpropagation to find the gradients of this objective function with respect to the vectors in this latent space. And then you perform this sort of inverse design thanks to this sort of pre-calculated quantities. And this works quite nice. This is particularly feasible also for the structure written here with 3D nanoprinting. So here, in this particular case, this was like a beam splitting element that should generate like 4 different foci. And here you basically see that you can design these structures in just a finite number of iterations. So this what is seen here actually in this sort of many gray lines. So these are different optimization runs where we start from different initial conditions. And here we really see also a benefit of the surrogate solver, because what we still do is always local inverse design. And this means that the final outcome so depends on the starting position in your latent space. Yeah. So, and depending on your starting position, you can come up actually here with many different designs. And now the surrogate solver really plays off because this is extremely fast. Basically, this inference is nearly instantaneous. And once trained, you can perform many different inverse designs made from or start from many different initial conditions. And then you just take your champion device in order to solve your actual problem. Yeah. So if you would have done this all actually with a local inverse design technique, this would have been much more challenging because it takes you many simulations actually to find out what is really the most suitable structure from a slightly more global perspective. And this is where this sort of technique really pays off essentially. Okay, so the last part I would like to flash here is this idea of automatic differentiation. So which I see like 1 minute, so I have to hurry up. So let's say the idea of the sort of automatic differentiation is so that you formulate your scientific software in such a way so that all elementary functions are differentiable itself, and then technically use chain rule in order to differentiate through your scientific code. And we use this actually for the inverse design, so of freeform surfaces, so that are written then also with 3D nanoprinting technology. Just to let's say to contrast this with traditional approaches to obtain these gradients. Of course, you can perform symbolic differentiation, but this is extremely tedious and complicated, memory intensive and slow, and you also cannot handle conditional logic that appears as a part of programming. You can also perform always numerical differentiation. But here it's like typical this sort of trade-off between round-off error and also truncation error. This has some sort of optimal step size for the sort of numeric differentiation where you basically toggle each degree of freedom and evaluate an objective function then on its own. And of course, this is very computationally demanding. So for n variables, you need at least n+1 simulations, which is unfeasible actually for many practical problems. And that's why the sort of automatic differentiation comes into a game, as I said. So here you basically use chain rules and analytical derivatives for each primitive in order to numerically or calculate directly, explicitly the differential expressions. So I stress this fact that this sort of techniques had been established in the context of the machine learning community. Yeah. So where JAX and PyTorch are very powerful frameworks for automatic differentiations. Because the sort of formulating everything in a differentiable way, this underpins basically also the development of these neural networks. And here we're just going to use this for ordinary physics-based simulations. So I have one example. I hope I have 1 more minute just to show it shortly. So we wanted to extend to the depths of focus in a cooperation with experimentalists in a microscope. So the idea is you have this object here and you have this image here. And usually the image deteriorates quite quickly as this object is put in different spatial positions. And this is what we wanted to extend actually, which is called like the extension of the depths of focus. And the idea is to put here an aperture into some sort of intermediate Fourier plane, which shapes the field distribution in a suitable way in order to solve this problem. So in our case, actually, we do this with a kind of phase-only surface profile, which is not very demanding in terms of dimensions. So we speak here of a height of micrometers, and this is like a radiosymmetric structure. But it serves really the purpose of extending the sort of focus spot quite tremendously, which is much larger when compared to the focus spot that the ordinary microscope is going to have. And this can be also fabricated, so quite nice. There's also an iteration basically contained in this sort of fabrication, where we cross-check what has been fabricated and what has been designed. And then we take the difference in order to adjust actually what is fabricated. And then after a few iterations, so we have a very good agreement between what is measured and what is designed. And then we can integrate actually these sort of filters into our microscope. And in this particular case, so we have been imaging here a smiling aperture mask. And you see that if without the sort of face mask, you see the sort of face mask if you displace this in the object plane only by ±1 millimeter. And with this face mask, you can extend actually, or you see this sort of object much sharper over an extended spatial domain. Yeah. Okay, I think then my time is up. Yes, so I'm sorry if I'm 1-2 minutes too long. I would just like to stress that the sort of 3D printing of this material provides many opportunities to provide structures with length scales on demand. You need this sort of inverse design technique in order to come up with suitable designs, and I have been presenting 3 of them and also a few applications. With this, I thank you very much for your attention.
Okay. Any questions or comments?
The coupling efficiency from the chip to the fiber. So the 0.9 is still high. However, sometimes I need 99%. So is there some further approach to get such a really high?
Yeah. So usually this can be direct linked to the number of degrees of freedom that you unlock. Yeah. So in this particular case, this sort of increasing this overall efficiency can easily be done just by extending the sort of spatial domain that you consider for the coupling region. So if you go instead of 20 micrometer, you go to 30 or 50 micrometer, then you can reach arbitrary large values. You're always better than the ordinary taper structure. This is important. Yeah. So, and it's really just a question of how many degrees of freedom you have been unlocking in order to take care on a certain objective function that you would like to handle.
Yeah, thank you.
Okay. Right.
Thank you, Carsten, for this very impressive talk. In the artificial neural network, you nicely explained that it depends on your starting point. But still, sometimes the solution was jumping to a better one. And actually, it was never jumping to a worse one. And so what happens there? Do you play special tricks?
It doesn't jump to a worse one because it's strictly gradient-based optimization. So you always just go into the direction of the best possible solution. So indeed, we also noticed this. So the problem is that this sort of objective function, this is not always a very smooth function in this sort of parameter space. So it can really happen that you have a large change, actually, even just there's a small change in the parameters. And that usually happens if you start to disconnect certain structures from each other. So if you are at a point where before you had like one blob of material with a certain shape, and then suddenly you come to a point where you have 2 blobs basically in close proximity, but still 2 close blobs. So then you have a sudden change actually in the performance. So this is a feature of the way the structures basically look like at this particular point.
Okay. Any other questions?
Thank you, Professor, for the interesting talk. I have maybe 2 questions. The first one is that in the topological optimization, we have like a lot of local minima. As I mentioned before, it can go to the beta minima and so on. But the first one is that how like is it sensitive to the initial value? And then the next is that do we need to like have a different set of initial value to just make sure that this is the best structure? And then the second one is that in your opinion, because like you have inverse design with a neural network, but you need to get an early data set for that one. But with topological optimization, you don't need the early data set. Like, how do you compare this to? Thank you.
Okay, so that was both very good question. So I think the no, I forgot the answer to the question. I think this is, so first of all, I think the idea is, or what the conjecture is, that in this sort of very high dimensional parameter spaces, the objective function tends to be rather convex again. So this problem with this sort of small blobs that we've seen here, actually, where we had this sort of many local minima, is that these structures are not very large. And I think in essence, these are not so many degrees of freedom because you spatially filter also, and then this is not the case. So in the sort of typical topology optimization problem, you think that you have a very smooth objective function at the end, and then of course you have many different local minima, but they are so indistinguishable in their value that at the end of the day you don't care of. I mean, you don't look for a global optima. You have a gazillions of different local minima, but the performance is all up to the third digit after the comma nearly the same, and then technically you don't care. Yeah. And the second question, this is also something really I try to stress. I find this a very important point. For a specific design problem, I would not use an inverse, an artificial neural network, because with this topology optimization, with Bayesian optimization, so there are many other inverse design techniques you can solve your specific inverse design problem with a much smaller number of function evaluations, because these neural networks, they need to generate, I mean, you need a lot of data in order to be able to train this. There's one huge benefit actually, and that is the sort of data generation that can be done in parallel. So the sort of local gradient-based inverse design, this is something that needs to be done strictly sequential, but this data generation, actually, this can be done in parallel. So if you have like a massive supercomputer actually at hand that can generate in parallel all this data, then in essence, maybe in the extreme case, you just need the time for a single evaluation in order to generate 20,000 data sets. And if you have done this, okay, this is like an extreme example, but if you have done this, then you can also train these sort of neural networks. Yeah. So so that's why in our case, we use this as a surrogate solver really, because then we can do many, many different designs actually of objects that all are feasible, let's say, in the context of the sort of 3D nanoprinting. So, and then this makes sense again to us. But if there's a single design problem, I think it's much better to use any other inverse design technique in order to solve it.
Okay. Okay, if there's no questions, so we thank the speakers again. Next speak is given by Oliver Martin, professor from Agro-Polytech Faculty, Lausanne, Swiss. Let's welcome.
Thank you very much. And thank you, Professor Alexander. Thank you to the local organizer. It's really a great pleasure to be here. Thank you for this fantastic evening yesterday. Did you enjoy the evening? It was amazing, wasn't it? So maybe to stay in the spirit of the evening, let's start by playing a little game. I asked Professor Alexander, I think this game is not very well known, but still, has somebody here played this game? Yes? So it's called Scrabble. You get little pieces like that with letters, and each letter has a certain value. And then you have a grid where you should make words one after the other and use the previous letters as well from the other words. And you try to make the most complicated word, so the largest, the longest word, and the word with the letters that have the highest number of points. Now, if you are about to play this game and you have a choice, you can either play this game with this set of letters, so the consonant, or you can play this game with only the vowels. So it means you have to make words only with the consonant or words with the vowel. And you have to choose. Which set would you choose? Who would set one? You would set one? Choose one? No? Two? This one? Yes. Okay, somebody else would choose this set, but I mean, altogether, it's going to be not very interesting because it will be very difficult to make nice words. So ideally, you would like to play with both sets together, the complete alphabet. Now, we're not going to be playing this game. We're going to be playing another game, and this game is based on Maxwell's equations. Now, Maxwell's equation also, you could choose. You could use only the electric part of Maxwell's equations. Or you could use only the magnetic part of Maxwell's equations. And I think in both cases, you would be a bit frustrated. No, you cannot do everything if you just have half of them. You want to use them both. And more precisely, you would like to use the coupling between electric and magnetic effects. The coupling between these two is called bi-anisotropy or magnetoelectric coupling. You see it here. I have some kind of an object and I illuminate with electric field. It will produce an electric response through this term. This is the susceptibility, which connects electric excitation with electric response. But with the same electric excitation, I might be able to produce a magnetic response. So from the electric field, I produce a magnetic response, and this is called the magnetoelectric coupling or the bi-anisotropy. Now, bi-anisotropy allows you to couple electric and magnetic effects, but it's very difficult to fabricate. If you want to have a system that is bi-anisotropic, you basically need to break its symmetry. For example, this is a small example from microwave. If you have a wire and I make a little loop in that wire, I come with an electric field, so I drive a current, but because this current makes a loop, I'm going to produce a magnetic response. And so I come with an electric field, I produce a magnetic response. I'm using basically this susceptibility here that couples the two. This is easy in microwave. It's more difficult in optics. If you want to do that in optics, to break the symmetry, you would have to make structures like this one, like a conus, which is difficult to do. So what you can do, you can cheat a little bit, and that's what we're going to be doing in that talk. Instead of changing the geometry, you can keep the geometry simple, like a small column, but then use different materials. And we're going to use that to produce bi-anisotropy in that system. So after this brief introduction, the main topic of the talk is nonlinear plasmonics. So this brings me actually back to the tutorial. In the tutorial, I talked about plasmonics. This is the optics of metal, not any metal. We only have a limited choice. We call them coinage metal, gold, silver, aluminum, copper, tungsten. And we want to do nonlinear physics with that, with those materials. This brings me back a long, long time ago. 20 years ago, I think this was the very first paper written on optical antenna. Now we talk about optical antenna quite a lot, but that was the work we did with Dieter Pohl and Bert Hecht. Our antenna was made with focused ion beam, just two gold nanostructures. When the incident light was parallel to the antenna, we had strong signal. When we turned the antenna, the signal would disappear. Now, if we look at this signal, it was actually a nonlinear signal. So we were using pulse laser. 20 years ago, the pulses were relatively long. We've seen quite a lot of pulsed photonics in that conference with very short pulses. Now we can do 100 femtoseconds or even shorter. These were 8 picoseconds, so relatively long, at 800 nanometers. So we would come at that frequency. And then we would observe at shorter wavelengths. So it means we would observe the signal at higher frequencies. So this is typical signature of a nonlinear effect. The first thing we would see, this very broad peak here, is luminescence of the gold. So basically you take two such photons at that frequency, you lose somewhere a little bit of energy and you produce something which is a bit shorter than twice the incident energy. And this is called luminescence. It's very broad and it's an incoherent process. The process I will be speaking about is second harmonic generation. There you take the same two photons and you produce one photon at exactly twice the frequency of the original photons. There are, of course, higher order processes like third order, where you take 3 photons and you get 3 times the frequency. So if we focus on that, and just to say a few words about nonlinear plasmonics, it's a process where I take the field at the fundamental frequency. So this is a vector. This can have different components, X, Y, or Z. In principle, I can mix all these components. I need 2 of them. And with that, I produce a photon at twice the frequency, so a polarization at 2 omega. And here again, we find this susceptibility, which is really a tensor now because it takes 2 field component to produce a new response at twice the frequency. In general, it can be any component of the field. Now for plasmonic materials, it's mainly on the surface that this occurs. So if you have a surface, the field can either be perpendicular or parallel to the surface. So you take two photons, one parallel, one perpendicular, and you produce a response which is perpendicular, for example. So this is actually the dominating component is this one. Two normal fields produce a second harmonic that's also normal. So let's just stick with this effect. And we want to do that in a meta-surface. So back to also what I mentioned, when was it? Yesterday? Yeah, it was yesterday. Yes, seems a long time ago. The evening was so nice. Yesterday, and we want to make a meta-surface. So we want to have a collection of nanostructures, which we call the meta-atom, put them on a surface, and we want to look at some nonlinear effect. So we could do something very simple, basic, but here what we would like is that our meta-surface behaves in the following way. It's a surface. I can eliminate from the bottom, and it's going to produce second harmonic in transmission. But when I eliminate from the top, I want that it doesn't produce any second harmonic in transmission. If you do second harmonic, normally you do that with a crystal. We've also seen quite a few examples here. If I had a crystal, a nonlinear crystal, it would be perfectly symmetric. I can come from the bottom, produce second harmonic. I can come from the top, produce second harmonic, and I have something very, very symmetric. So for the sake of what follows, I need to introduce a bit of vocabulary. I have my meta surface with my meta atoms. I have the normal to the meta surface. I'm going to call forward excitation when I come with my pulsed laser in the same direction as the normal to the surface. So this is forward excitation. And when I do that, I can produce, red is the fundamental frequency. I can produce light at the fundamental frequency that's transmitted, but I can also produce second harmonic at the transmitted direction. But some light can be reflected. I can have fundamental reflected, second harmonic reflected. And I will call backward excitation when I come from the top. And again, it can be transmitted or reflected at the fundamental or the second harmonic. Now, the meta atoms I'm using, they are this T-shaped structure. This is something that has been actually proposed a long time ago by Martti Korhonen. He's being in Finland, is being one of the founding father of nonlinear plasmonics. So these structures, because it's a T, it has two different lengths. And when you shine a pulse laser with the polarization along this bar, it produces second harmonic polarized along this bar here. And because you have these 2 degrees of freedom, it's not the billion degrees of freedom we had in the previous talk, but already it's complicated enough for us with just 2 degrees of freedom. We can produce second harmonic and we can tune the resonance of the structure by adjusting this length. So because the incident polarization is along this length, if I change this length, it's this axis here, I will change the response at the fundamental frequency. So if I look, for example, at the transmission, I come from the bottom, the light is transmitted. We see that for this region, around 180 nanometer, I have very little light transmitted, meaning that probably the light is absorbed in my structure. And it's the same if I come from the bottom or if I come from the top. So the structure is perfectly symmetric. Now, if I look at the second harmonic light, it's these panels here. The second harmonic is polarized in that direction. So I can adjust this length, it's going to be this axis here. And we see that for this length here, I have basically a maximum in second harmonic. So I adjust this length to have a maximum of second harmonic when I eliminate from the bottom. But what starts to be very surprising is that if I come from the top, from the other side, my structure looks all symmetric, but if I come from the other side, we see we have very different behavior for the second harmonic. So I'm interested in this asymmetry. So what I can use as a metric is the ratio of this divided by that, and this is what I get. So in that region of dimension, this is here, this dimension on this axis, that dimension, I have here a region where I have a maximum of second harmonic asymmetry between coming from one side or from the other side. So these are the dimensions we have been using for that system. And note something which is actually challenging for the fabrication. We have used a very small period, 250 nanometer. Now, the reason for that was again in the tutorial. We've seen in the tutorial that when you have periodic structures like a grating, if you have a very small period, you have no diffraction order. If you have a large period, you start to have diffraction. So that would be annoying because I would be looking at my meta surface and the light would go maybe on the side. So I would not be able to observe. But if I take a very small period, then all the light comes against me and it's easy to measure. So we fabricated that. We started on our glass substrate. We put the aluminum, a small glass spacer. Then we put the silver on top, our negative resist, and then we etch. And to obtain a symmetrical structure, we just deposit glass everywhere. So it's embedded in glass. So these are our structures. You see, they're quite nice. In the electron microscope, you can use a detector which is called backscattered electron, and it gives you the material contrast. You see here the aluminum has another color from the silver on the top. And again, you notice that the period is very small, 250 nanometer. So this technique also, if I make a parallel with the tutorial, it's the etching technique that we have used, which is more precise than the lift-off technique. And again, all the details are given in that paper. So here we are, we have fabricated that structure and we measure it. So we just have our simple laser here. We illuminate at 800 nanometer. The pulses are not very short, 120 femtosecond. And to measure from one side and the other side, we just turn the sample. That's of course the easiest than turning the laser and everything. And this is what we obtain. So if we go in the backward direction, so we illuminate from the top, we have a very little tiny second harmonic. But if we come from the bottom, the forward excitation, we have a huge signal. We have about 10 dB difference between the two, so about a factor of 100 between the two. So we were very pleased. We've seen that, and we have this strange response. When you come from one side, you have second harmonic. From the other side, you don't have a second harmonic. And well, we believe that this really behaves well. So first of all, let me try to understand how this works. That I've mentioned this bianisotropy. That's very important. So do we have bianisotropy in that system? So do we have component of the susceptibility tensor that are connecting electric and magnetic fields? So we can do that. There is a modeling approach which is called the generalized sheet transition conditions. So when you do simulation of metasurfaces, you can do a full wave analysis. So you take every small meta atom and you calculate, you discretize it, you calculate its response. And with that, you can look when you eliminate at the fundamental frequency what happens at the second harmonic. But it's quite tedious and you don't gain a lot of insights into how your system works. So what you can do, you can replace all these little nanostructures with just a homogeneous material, which is described with these susceptibilities. So this is called, it's an infinitely thin sheet of susceptibilities. So that's why it's called the generalized sheet transition conditions. And in our system, we can illuminate with electric field at the fundamental frequency, with magnetic field at the fundamental frequency, and we obtain an electric response at the fundamental frequency. So we have these different susceptibilities. Again, this one is bianisotropic because it connects magnetic and electric field. That's the fundamental frequency. But the system is a bit more complicated. The system has a nonlinear response. It means you need to know what happens at 2 omega, at twice the frequency. So again, an electric field at the second harmonic can produce an electric response with this susceptibility. A magnetic field at the second harmonic will produce an electric response with this bianisotropic term here that combines magnetic and electric field. This is all at 2 omega. But in that system, the magic of the system, if you want, is that you eliminate at omega and you produce second harmonic. So you also have additional terms here. This is, again, the nonlinear terms we've seen previously. For example, two electric fields at the fundamental frequency produce a response at 2 omega with this tensor. It's a higher rank tensor now that combines electric field to produce an electric response. But also here we can combine magnetic field to produce an electric response. And finally, we have a mixed term which combines electric and magnetic field at the fundamental to produce an electric response at 2 omega. So all this is a bit intricate, but what I just want to show you is with this technique, you can calculate these tensors, and this is what you obtain. So if we just focus on the linear response, we see that the term that takes a magnetic field at omega to produce a response, linear response at omega, this bi-anisotropic term is actually not negligible. It has some value. And at the second harmonic, it's this panel here, we see that these terms are actually very dominating at the green and the red term. And these are terms that always combine electric and magnetic field to produce this very strong response. So it's a bit technical, but basically what I'm saying is in those metasurfaces, we have to mix the electric and the magnetic field to obtain the response at 2 omega. Now, if we look at this system, illuminate from the bottom, get a nonlinear response in that direction. Illuminate from the top, don't get any nonlinear response. It's very tempting to say, well, this behaves like a diode. Right? You know the diode in electrical engineering, the current can flow in that direction and it cannot flow in the other direction. And a diode is, of course, a very important component for optical signal processing. I mean, a transistor, if you want, is built from a diode. But what's more interesting is that a diode is called a non-reciprocal component. And it's very tempting to think that we have invented what we would call the nonlinear diode, so a nonlinear, non-reciprocal optical element, because if I come from one side or from the other side, I have a different behavior. And you could be very tempted to say, okay, I'm going to go and publish that in Science because non-reciprocity is amazing. And if you buy me a beer this evening, I can show you a few papers that have been published in very good journals that claim non-reciprocity. But unfortunately, all these papers are wrong. So what's happening? Reciprocity, non-reciprocity is a complicated phenomenon, which is often mistreated. If you want to learn more about it, there is this very good paper from Christophe Callot. We also wrote in the context of metasurface that paper with Karim Achouri. If you look at a system that evolves as a function of time, so you start at the time equal to 0 and you let the system evolve until it reaches a certain time t. What you can do is you go back, so you take the symmetric from this instant in time, you go to the negative minus t. And then you let your system continue to evolve. If your system is reciprocal, what's going to happen is that it will evolve and it will come back to the state it had at the origin. If your system is non-reciprocal, then it's going to evolve but go to another state at the origin. So, and of course, there are many more complications which are very well described in this paper. A simple criterion about reciprocity or non-reciprocity, if we go back to electrical engineering, you know, in electrical engineering, you do scattering matrices, you do two-port system. So what we have is a two-port system. We have the metasurface. One port is we come from the bottom and we shine light, and some of the light is transmitted. So this is this term in the scattering matrix from port 1 to port 2, and some of the light is reflected. So we go from port 1 and we come back to port 1, it's this term. And we have the same here from the second port with these two. Reciprocity actually requires us that the scattering matrix is symmetric. So it requires that these two terms are the same, but there is absolutely no constraint on the reflection. It's just about the transmission. So we can do the measurement in the linear regime. If I take, we are around 800 nanometer, that was our excitation wavelengths. If I look, the signal is very faint. This is why we have a bit of hiccups, a bit of noise. But if I look at the light transmitted in the forward direction or in the backward direction, they are perfectly superimposed. So we perfectly fulfill reciprocity in the linear regime for that system. I'm doing nonlinear optics. It's a bit more complicated. So if we look for a criterion for a reciprocal nonlinear system, we can look at it as a 4-port system. We have the linear response coming from one side or from the other, and we have the nonlinear response, again, coming from one side and the other. And so our scattering matrix would be much more complicated. It would have blocks that contain what happens at the fundamental frequency. It would have blocks that contain what happens at the second harmonic, 2 omega. It would have the second harmonic generation, which is basically going from omega to 2 omega, again, from both sides. And it would have something we've seen a bit yesterday when we were speaking about quantum system, which is frequency down conversion. We come from 2 omega, and we have a response at omega. So we would have a very complicated scattering matrix, and we would have to check all these components in that matrix to see whether it's symmetric. What we've done so far is just to show that these two guys are not symmetric. So basically, we have an asymmetric nonlinear process. If I come from this side, if I come from this side, the nonlinear generation, the second harmonic, is different. So this brings me to my conclusion. We have used this nice, simple design, very simple design of T structure, where we can tune the response at the fundamental frequency by changing this dimension, and the response at the second harmonic by changing that dimension. Fabrication with plasmonic metal using dry etching, so we can have very nice structures. Measurement, we notice indeed a very important difference whether I come from one side or from the other. But be careful, this is not non-reciprocal. We just have some asymmetric time reversal behavior. So this big buzzword like reciprocity and so on and so forth, one has to use them, I think, very, very carefully. And sometimes this is mistaken with non-reciprocity. That was mostly the project of Sergei Borovic's. We've worked a lot with Karim Ashuri, who's an assistant professor in EPFL, the rest of the team, and website if you're interested in publication. And of course, I will upload my slide on the conference website. Thank you very much.
Okay, any questions? Okay.
Thanks, Olivier, for this nice talk. Just one question. When you have been retrieving these polarizabilities, it didn't look like you have a resonance in the fundamental one. And then from the second harmonic, the polarizability was not retrieved. So the chi at 2 omega. So is there a resonance in this chi at 2 omega? And was this on purpose that this is not, at least in the fundamental wavelengths, not resonant?
So this is the fundamental wavelengths. This is at omega, and we see that this susceptibility is not insignificant, but you're right, it's not resonant here. That's just the way the structure works, basically. We have previously worked on what we call double resonant antenna. So they have a design with split. They are a bit more complicated and more annoying for that type of project. They're quite large, so we could not pack them very closely together. On the other hand, you also spotted very well that here we have a resonance for these terms at the second harmonic. But you're right, here we don't have one. It's just because of this design. And we want to have them very close together so we cannot have big structures. Yeah, good point.
Okay, any other questions?
Okay, thank you for your wonderful presentation. We often to use some specific compounds like silicon nitride or lithium niobate for photonic circuit because of those compounds have nonlinear response. is using the meta surfaces potential to substitute those compounds for the integrated circuit?
Well, unfortunately not. So we have some nonlinear response. I've shown you that we had a big peak, but it remains extremely weak. So it's a very, very weak signal. So I think these good nonlinear crystals are much, much better. The main difference, and actually I can go just at the end. Oops. Sorry. The main difference, what you mentioned in crystals, oh, is it coming back? So in a crystal, what you need is to do phase matching. It means that you need to have the fundamental, the pump, go together with the second harmonic for quite a while, and you have to use the crystal properties for that. What's and this is very efficient, you can have a huge nonlinear signal. Here in a surface, like on this metal, it all occurs just at the surface, so there is no need for the phase matching condition. But the price to pay is that this is probably about 2 to 3 orders of magnitude smaller than what you can do with a crystal. So it's very weak. It's fun, it's interesting, but it's not very useful. You're right.
Okay, thank you very much.
Okay.
Olivier, thank you very much for your talk. I'm still kind of processing the last comment you made about non-reciprocity and asymmetry. And please correct me if I'm wrong. In nonlinear systems, where whenever you have bistability, you may have symmetry breaking in the way that you jump to a different solution going forward or backward. Is that the kind of thing that is happening here as well?
Yes, so what we have is really a time reversal asymmetry, but it's not sufficient to say that we have non-reciprocity. So it's a condition that is necessary, but it's not sufficient. This is why this field is very, very subtle. I mean, you can say reciprocity is just simple. Reciprocity is I can see your eyes, you can see mine. But actually, it's a bit more complicated than that.
Well, exactly. So if you look at your zero, you have in fact green solution and you have red solution,
Yes.
which means that the system is bistable. It has different solutions possible, right? And you may be able to jump one way or the other depending on the direction. Not
No,
quite.
I think this is against, well, this is of course something you do in nonlinear optics with this type of effects, exactly. You will jump from one to the other. But here it's really, we are not at time zero and jumping. We have come from this time and we're evolving to 2 different solutions.
Right.
So it's different, but there is a nice parallel to draw, that's true, yeah.
Thank you.
I'm not a theorist, so that's why my question is quite naive. So you explained that the non-reciprocal behavior using a susceptibility matrix, right? And as far as I understand that this matrix is explaining the macroscopic effect. Yes, so those matrix element you can calculate from the microscopic parameters easily.
Yes, so we basically, in this generalized sheet transition approach, this we can calculate, for example, with the technique that Carsten has shown, that were the backbone of his optimization. But if you calculate the field here, and here, you can then replace all these structures with homogeneous material, which has these properties. So you have to do, you see these matrices, they always connect electric and magnetic field. So what you have to do typically is a calculation where you come with electric field like that. You see what is transmitted with the same polarization, and you see what's transmitted in the other polarization, and you look at what is transmitted for the magnetic field and so on and so forth. And you can build a system of equations from the field you have calculated here, which is going to enable you to compute this tensor component for these materials. Karim Ashouri and Christophe Callot, they wrote a very nice book about that. So if you're interested, look for him, or I can send you the reference, where they really explain this type of technique. So indeed, you get from this discrete description a continuum description, which indeed links microscopic and macroscopic. Yeah.
Even for a second harmonics generation.
It's just other tensors. So here you have more components. This is a 3x3 matrix, and here it's a 3x3x3 matrix. So it has more components to retrieve. Yeah.
Thank you.
Okay, so let's thank the speaker again. Okay. The third speaker is called Professor Karo Tamada from Kyushu University, Japan. So let's welcome.
Okay, thank you for the kind introductions, and I'm very happy to be here. I don't know how many times I'm here in ISMOA. At the very first time, I joined the second or third meeting from Singapore and US, and I changed the place to work every 3 years. So that each time after that, AIST, and then Tokyo Tech, and then Tohoku University. And then recently, I'm staying in Kyushu, so that I come to the ISMOA from Kyushu University a couple of times. During that, Alex was also young as me, but now he become very great president of the Optical Society Indonesia, and congratulations. And my student also come to be staff member of ITV, and always I'm very happy to be here to see my old friends. Okay, so today, so I need to find out which topics I have to talk, because I'm here every 2 years. So I brought up the perovskite main story today. But before going, I want to introduce a bit about Kyushu University, because the new students are here. I'm from Kyushu area, is the south end of small island in Japan. And then our universities is here is Bari, so that relatively close. That Kyushu University has a very huge campus. This is the largest campus in Japanese university. And also this is a Faculty of Science, very new campus. And this is a concert hall we have, and huge capacity, 3,000, and the largest hall in Japanese university. And then this is also the huge library. We have a top 3 in the Japanese university. So that if you're interested to come to Kyushu, welcome. And to say, very beginning, at the first time I come here, I have been working in the self-assembled monolayer molecules and the optical response to the azure benzenes. It looks very beautiful. This is sometimes in vacuum and also in solutions. They have a beautiful alignment of nanoscale, and they changed alignment by some kind of, for example, light irradiations. But the problem of the self-assembled monolayer, because of this is molecules, the optical response is relatively small, so that I decided to switch to the nano crystal after that. But I want to say one thing. I will talk today about perovskite nanocrystals. And the perovskite is very popular nowadays for the solar cells. But now many of people start working with the self-assembled monolayer organic molecules again, because their perovskite is unstable. They need a top sealing, a bottom sealing, and also defect kind of management is needed, so that they start to the organic perovskite, but now the hybrid system of organic, so that they're even using the organic dyes, they are stable enough and now come to the product. Okay, so today this is the main topics, and before that, I am to show the what kind of nano material, nanocrystals we are self-assembling. As one of that is the core-shell type of, and also perovskite of the quantum dot, and also metal nanoparticles, sometimes bioimaging applications. And so this come to the like lab cells. So that I introduced some of the topics before, but not much about this. And so that partly I will explain this subject today. And I want to show the self-assembling process. Actually, this is very easy. So look at that. And firstly, we need to synthesize very beautiful nano-sized particle and capped with the hydrophobic molecules, and then disperse the solution colored red. But after drying up, they are spontaneously self-assembled and forming this kind of monolayers on the water surfaces. And the surface, like a centimeter or millimeter or meter type of surface, are filled by the monolayer. This can be stamping to the substrate on the solid substrate and can be used. And then this is just explanations. And firstly, nanoparticles are dispersed by the repulsion, by solvations in organic solvent. And after drying, firstly, they have a very weak interaction of van der Waals interaction, and they come to each other very close, like a nano space. And then the organic molecules, the ligand molecules start to be interacting by hydrophobic forces and interdigited. And this come to be solid-like, very stable films. And then the plasmon, localized surface plasmons, maybe I don't need to explain, but when we irradiate light and the nanoparticles, we can confine the light near the particle, depends on the size and the kind and the nanoparticles. And then when we make the self-assembled monolayers of nanoparticles, we can confine lots of light at the nano interfaces, and also we can make this nano gap, so that the enhancement factor of the optical energy come to be much more, 10 times more. This surface can be used for various applications. So that just want to explain a little bit for how the characteristics of this two different. And the case of two-particle nanogap is well known, but we try to be aligned infinite number of particles, and then actually the interacting distance between the particle is elongated. And then if a little bit of a defect or these things are happening, but for that cases, they don't care, and they can excite very stable field. And then we try to obtain by the FDG simulation what is the magic number. And one direction of 30 particle, if it does exist, then this can be the light treated, this is large enough. So that this is just, these are, as you all know, so if we think of the light waves, and then like a half wavelength, half size of waves are about a couple of 100 nanometers, so that the particle domain size is larger than that, then this domain can be treated infinite of sizes and light propagating nicely. So that, and then if the particle, metal, kind of a metal and the size of a particle, and then shape, and the number of domains and gap distance all fixed the same, then we can excite a very sharp plasma absorption band on the 2D surfaces. And then 2 years ago, I introduced for the one example of the bioimaging application using this nanoparticle sheet. So that if we just deposit the nanoparticle sheet on the glass substrate, we can confine the light a couple 10 nanometer regions so that even the fluorescence anywhere, like a leveling of cells and proteins, we can excite only the nano-interfacial fluorescence. So that nano-interfacial imaging come to be possible. Just a very simple manner. And for these cases, we try to label of the cells, live cells, and the anchoring position of this here. Then this protein is labeled. And then here is an image. And the small protein clusters are moving around, and you can see. So that this is very, we can reach to the, even the spatial resolution for the optical microscope like a limit. Of course, we cannot beat the diffraction limit, but the thickness is very thin, very high contrast. And then and also I forget to tell, but the plasma effect is once directly contacting, then quenching, and have a maximum emissions and a little bit distant and disappears. So that disappearing appear and disappear phenomena actually is saying the vertical position of the bright spot proteins are changing by time. So, but today's topics is something different. And one of the topics is for plasmonics of the new findings, but starting from our history. So that this is the data of very much before, about more than 10 years ago. What we accidentally found is try to deposit silver nanoparticle on top of the gold thin film. Then depends on the layer number, we can see this kind of orange or pinkish color change. So that time when I think I talked in this meeting, also by that time we don't know what's going on. But this is a spectrum. And when we deposit on the glass surface, it's just yellow color come to be deeper, that's it. But when we deposit on the mirror, it depends on the layer number, but actually the peak, original peak disappeared and split. And then we can, depends on the layer number, we can see the peak position change and also the intensity change. But actually, of course, the energy is kept so that they are spreading for the high energy, low energy, but phenomenologically, we can see the color change. So that we still don't know exactly what's going on, but some explanation we try to do is the particle has a lot of high dipole, and then the interface and the interacting with mirror so that they can produce a quadrupole, and the quadrupole dipole coupling is needed to get this kind of Fabry splitting type of behavior, that probably spontaneously this kind of situation are going on, as the professor explained. For this is in general, we need this kind of asymmetric features needed for the top-down technologies. But our cases, we don't. The particle is symmetry. Only asymmetry does exist at the interface, but still the huge splitting of peak we could find. And then actually we could reproduce this phenomena. And as mentioned, the previous professor a little bit, but our particle is 5 or 10 nanometer, so that for the for light, this can to be treated as a homogeneous medium, so that the N and K changing depends on the nanogap structures and so on. But we can do simulations treated as an effective continuous homogeneous medium, and then we could reproduce this kind of splitting phenomena. And then this can be used by many of the device applications, for example, multi-color change or biosensing or so on, and also the some chemical reactions on the surfaces also. And then this research followed by this kind of a similar phenomena, but much more simple, of the nanoparticle top of the metal, like a nano cavity with nano cavities. So that if we make this kind of structure, we could get the similar type of peak splitting by the interaction of the localized plasma on the top and the bottom of metals and something like that way. And then this research has been done quite well for many laboratories. But what we found is because we are the self-assembling persons, so that we can control the single particles or nano-gapped structures, and then how it affects to the, depends on the gap distance, they interact different manner to the bottom metal. If a particle is isolated, so dipole excited are coupled with mirror like this way. But if the particle distance come to be close to each other, the situation come to be close to MIM structure, metal thin film, insulated thin films. And by having a nano gap, it's kind of a high K we have, but somehow depends on the gap distance. We could see the variety of phenomena of the by the nano balanced structures. And then this is one of the example of our former staff member, now professor in the Osaka Public University. He tried to make the, he's not chemist, so that he tried to do the deposition of the thin film and heat treatment and try to make the nano structures on top of the metal insulated surfaces. And then because of this is island structure, depends on the gap distance, they change the different peak separations and the colors, something like that way. And then the gap distance is far separated, and then when the spacer, this spacer insulator thickness come to be increased, and they have bubble shift. And this is a new data now preparing the papers. But what we try to do is try to make the, this is an oxide nanoparticle, and try to deposit layer by layer, and we can control the thickness of nanoscale like that way, and then deposit the metal on top. Then this particle is kept by organic molecule, and they're a little bit weak for heat, so that without heating, they are spontaneously making this kind of structures of a bit random, but with a nanogap. So that we can easily to make the nanogap insulator metal kind of structures by this procedure. For that cases, because as I explained, they have a nanogap structure and the spacers and control the thickness by layer number and interacting with the bottom metal, we can see this kind of huge spectrum change was quite easily. And just to prove the influence of a nanogap structure, we try to be heat this surface, and then this come to be rounded and more distant. Then before they have a huge shift depends on the layer spacer numbers, but after heating, this come to be more like more spacers, so that they don't shift so much. So that I explained before, this kind of depends on the gap distance and the top particles and interacting with bottom metals, and we can see we can control the light confinement condition like this way. Now I want to switch to the quantum dot, and then quantum dot also we can make make self-assembly structure relatively easily, so that this is emitting material, so that way to use are different, but process is kind of similar. And firstly, I want to explain this is a quasar type of quantum dot, very stable, a bit toxic, but this is synthesized in the bottom-up technology, and then they kept by the organic molecule, so that they can spread at the air-water interface in the same way. Then we can make the emitting film monolayer like this way, and this film can be deposited on the substrate as well. And then, of course, we can control the layer numbers and on the glass and also on the mirror. And then what's going on is phenomenologically very similar, but on the glass, just increasing the layer number and the emission intensity increase. But the case of gold substrate, they have a maximum peak intensity, emission intensity, about 7 layers, and then decrease again. And the summarized data is here. And on the glass, it's regular emissions, but on the mirror, fluorescence is enhanced, and the maximum emission at the 7 layers, for example, about 50 nanometers thick. And we continue deposition, and nothing happened on the glass, but on the mirrors, and the second peak appears. So that this is a typical cases light trapping of peripheral type of phenomena we could get. And by the simulation, we could reproduce these structures. And actually, this quantum dot layer have a very high refractive index. We consider that, and the air and glass or gold. And then we put the light source inside, and we see how the light is confined or released, depends on the layer numbers. And then this is simulation data, so that this is experimental data, so that we could reproduce the phenomenon very nicely. And then just two conformations. If changing the refractive index, of course, the layer numbers needed to the maximum emission intensity changing. So that this is a very basic optics and like standards. But people needed to know when we make the devices like displays or people are working with that, so that this is one of the data important. And then how as the enhancement factors we can analyze. And then the mirror effect is only 2 times, but the test of the enhancement coming from the plasmons and also we cannot distinguish, but the plasmon and also light confinement. So the additional 4 times of enhancement come to be by these structures, so that we can have the more enhanced emissions by use of a backside mirror. And the good thing is, in usual we use metals in anyway, like aluminum to make the display for because of electrode. So that is people are naturally using, but not much aware of that. Okay, so the last talk is the perovskite. This is my previous student. He succeeded to synthesize a variety of perovskite pure crystals. It's not mixed ions. This is pure materials, no mixing ions, but changing the particle size by changing the preparation synthesis temperature. So that we started with the mostly stable high temperature and on purpose go to the lower. In usual, the particle come to be very unstable or say low, difficult to isolate. But what he found is after synthesis, he frozen this organic dispersion solutions and the frozen condition doing ultracentrifuge. Then even the few nanometer average is like 5 to 10, or smaller one is like 3 nanoparticle can be isolated, purified. So that now we come to the bunch of different particles and different colors, and so that if you are interested in like a wavelengths matching for some ideas of the pattern structures or whatever, and we can provide these different emitting materials. And if you want to learn how to synthesize, you can come to my lab. And the problem is perovskite nanocrystal. They are very weak for the water and oxygens. So that what we cannot use the monolayer formation at the air-water interface. So that we use the spin coating. But even for spin coating, we can make very beautiful monolayers actually, and we can deposit layer by layer. This is the image. The point is, like Uran did before in my lab, we purify many times, 3-4 times, and we need to remove all extra organic molecules to produce the very rich self-assembly. And if we do that, we can make the perfect monolayer on the substrate, and after that, perfectly dried. This is the point. Then even the keep using good solvent, first layer is not dissolving. We can make the second layer, third layer, just repeating this process. And we could get the maximum enhancement in a similar manner to the previous quantum dot cases. And then the next challenge is we try to be transfer the film for the patterning. That is this kind of surface chemistry we need to do. This is first spin coated layer, transfer for the PDMS stamp, and another substrate. So that cases interaction affinity with substrate need to be more and more by layer. So that we need to start relatively weak interacting substrate. So that these other particles kept by the hydrocarbon, so that they have a very strong affinity with hydrocarbon surfaces. But we started from the fluorinated surfaces, but the fully fluorinated surface is like a Teflon and non-wettable, so that we cannot make the monolayer. So that we introduce only a little bit of fluorinated one and making the mixed film. And this, we use the knowledge about self-acid monolayers. And the longer molecule tend to be adsorbed faster. So that to make the mixed film, we need to like 80% of short molecule and only 10-20% of longer molecules, and we could make the mixed film. And then like this way, we control the work of adhesions. I mean, this means is contact angle, wettability, and we succeeded. They transfer the film step by step like this way. And many people, other laboratory, is keep using polymer layer, PMMA, 5. Okay, PMMA. This is very easy process. And if we use very thin PMMA, it doesn't matter so much, but we need more voltage to work for the like applying the electric field and emitting. But many people doesn't matter and they're using this process. But the problem is we try to make the very small pattern because the polymer is continuous, so that a lot of defect when the peeling or patterning. But we set back to basic without PMMA, just clean the nanocrystals, and then we can get to the very nice pattern surfaces like this way. And this is just last topics I want to show. But our associate professor Dan, he's also working with self-assembly, but this is a living cell. Living cells and layer by layer and the DNA functionalized and then decide to the positions, and we induce the fusion of the cells. So that, like we can make the pattern of living cell. This is living. So that this come to be biomimetic organ tissue type of researches. So that even the material is metal or semiconductor, oxide, and the living cells, basically idea is the same. So we can, by controlling of the interacting forces, we can do this like this way. And this is our lab member. I just want to say I'm the editor of this applied nanomaterials, so that they say nano, but if the size is less than 500, then this can be treated nano. And even the flat surfaces, thickness is less than 500 nanometer, this can be treated as nano. But the point is, the system need to have a nano-related interesting phenomena. then this is accepted as our journal. Please try to submit to the our journals. And this is very last slide. Next year, we will have an Asian Nano meeting in Fukuoka, so that say I said nano is less than 500 nanometer. So that if you are interested in, please come to this meeting. And we are planning to do the banquet in the aquarium, so we can have a dinner in front of a fish tank. It should be very fun. And then welcome. Thank you very much for your attention.
Okay. Any questions? Okay.
Okay, thank you very much for the very interesting talks. So there are two questions. The first, could you explain again the mechanism of the nanocavity effects on the LSPR? And the second one, recently I'm trying to use and to modify the surface using the graphene or reduced graphene oxide to the gold thin film and study of the LSPR. It has just started, so maybe do you have any idea or advice if we use the graphene oxide or reduced graphene or graphene? Because as you know, graphene is very exact material in terms of crystal and also the loss of surface. Thank you.
Okay. So from the last questions, recently many people working with the graphene oxide together with particle mixing, especially for device applications. And the graphene is used as like a light absorber and then changing the absorbed light wavelengths. And yeah, this is a kind of promising. You can find so many papers in our journals, and it's very popular subject. And your question is for the which
Nanocavity effect on the LSPR. I think you showed that in
the very
Yeah,
first.
yes.
Huh?
Yeah,
This one?
Yes,
This
yes,
one?
yes.
Okay. So that this depends on the structure of the, this case is a cubic. Then when light irradiate, then they can have a electromagnetic field at this edge part of the case of cube. Then this field is interact with the mirror underneath and then enhanced. And then this depends on the spaces, and they have this kind of Rabi splitting type of phenomena. So that it's very much depends on the round particle has only interacting over the bottom part because the edge is needed to have a very strong local field. So that then interacting with mirror and with mirror effect. So that is, yeah, here is the simple explanation. But this plus minus dipole, it depends on the structure of the metals. But anyway, they can find some partner in the mirror and interacting and then splitting kind of phenomenon.
Okay, so maybe there is something like a critical size of the cavity.
Yeah, it's so that it's it need to be so strong so that they have a kind of shapes to have a strong dipoles, and also the thickness is if too far, no interaction, so that they need some kind of nano gap structures.
Okay. Okay, maybe the last questions. So, here.
Thank you for your interesting talk. So I have two questions. The first one is that when you are using the Langmuir plugin, so you put the particle is already dispersed in organic solvent, and then you put it on top of water, right? Can we do it the invert one? So we have, let's say, a water dispersed particle, and then we put it on some organic solvent. And if so, like how do we control the evaporation, and then what kind of choice of solvent that we can use? And then the second one is that because recently there are some progress in water dispersed perovskite quantum dots. So can we do this Langmuir plugin process with perovskite quantum dots? Thank you.
Okay, the first question is, it's not water system, but what we have tried is using the mixed solvent system and dispersed. And then actually solvent mixing ratio is different in bulk solution and top surfaces. And then also there's a conversion, convection flow, so that they bring the particle on the top and then self-assembly. We wrote a paper in a nanoscale. Maybe you can use that idea. And then second question is, yeah, if you can make like a shielding, nice shielding, then you can use the air-water interface. But that case is you need some hydrophobic functions, so to flow, so that you can play with not too much of hydrophobic, then they form the 3D aggregate, so that to see the balanced between the hydrophobic, hydrophilic, then you can make the monorails. Yeah.
Okay. Okay. If there's no questions, we thank the speakers again. Okay. Thank you.
Thank you to all three speakers and our moderator for the insightful session. At the time, I kindly invite Professor Karsten Roxko, Professor Oliver, and Professor Koru Tamade to the stage, and also our moderator, Professor Sam Vincent, to hand over our souvenir. Once again, thank you to all three speakers and our moderator. Before we begin our next session, we will take a short 30 minutes coffee break. And we will second session at 10:30.
And also, I would like to remind us once again, our coffee breaks has been moved, please. So it's located in front of this room. So if you want to get some coffee, can please join us in the front. Thank you.
Power supply, multimeter, and oscilloscope are used for the standard electrical test. In a typical industry in the lab, we need multiple of these devices, but the problem is they have excessive power, limited output, expensive, bulky, cumbersome, and inconvenient. And the solution is XStack, a sophisticated source measurement unit for low power applications, from simple electronic circuits to complex photonic integrated circuits. We also offer a variety of channel options, ranging from 8 to 40, 80, and 120. We are also beginning to develop our product into a chip scale version with a wide range of imaginable applications. Start from sensing and instrumentation, telecommunications, machine learning, and quantum computing. If you're interested, we also provide a live demo unit and a GUI simulator to give you a better understanding of our product. You can find more information on our website. We are waiting for you. Together, we are unlocking the power of light.
At FLIR, we asked a simple question: why choose between what you see and what you don't? For years, we've relied on visible light to define structure. But structure alone doesn't tell the full story. Infrared reveals transformation, heat radiating from machinery, stress forming in materials, energy shifting before failure occurs. But these two perspectives have always been separate until now. Introducing FLIR Mix, the first imaging system to capture high-speed visible light and the revealing power of infrared together in perfect sync. Every pixel aligned in time and space, every moment captured with absolute precision. Now, researchers and engineers can see structure and transformation at the same time in real time without the need to piece together separate data sets. FLIR Mix doesn't just show you the moment, it shows you what makes the moment happen. With up to 1,000 frames per second, every reaction, every shift in temperature, every hidden change is revealed, giving you the power to analyze change as it unfolds. No more wasted hours aligning data streams. No more uncertainty. Just faster, more accurate insights, so you can focus on results. With FLIR Research Studio, visible and infrared data are captured, processed, and analyzed in one system, eliminating complexity and delivering seamless integration. One workflow, one synchronized data set for scientists, engineers, and researchers across material science, electronics testing, renewable energy, and high-speed dynamics. Patterns once missed, now visible. Failures before they happen, now preventable. The future of imaging, now here. For researchers, for engineers, for visionaries. Because when two worlds come together, you don't just see more, you see everything. FLIR Mix. See more, no more.
If you're designing photonic systems, ANSYS Lumerical lights the way. From virtual reality to display technology, from auto sensors to smartphone cameras, from laser design to quantum computing, from 5G to data centers, ANSYS Lumerical is a world leader in photonic simulation. We've been helping engineers meet product development deadlines for nearly 20 years, collaborating with leading third-party tool providers to create new workflows, building better photonic systems on time, on spec, and with higher performance. Referenced in over 15,000 scientific papers and patents, Lumerical has been run in close to 30 million simulations by roughly 50,000 different users, by 90% of the leading research universities in the world, and by all 10 of the top IT index companies. If you're designing photonic systems at the component and circuit levels, ANSYS Lumerical is a complete cloud-ready simulation solution. It's easy to learn and deploy, constantly innovating new solutions and techniques. For reliability, speed, and accuracy, there's only one true leader in light, ANSYS Lumerical.
Power supply, multimeter, and oscilloscope are used for the standard electrical test. In a typical industry in the lab, we need multiple of these devices, but the problem is they have excessive power, limited output, expensive, bulky, cumbersome, and inconvenient. And the solution is XStack, a sophisticated source measurement unit for low-power applications from simple electronic circuits to complex photonic integrated circuits. We also offer a variety of channel options, ranging from 8 to 40, 80, and 120. We are also beginning to develop our product into a chip-scale version with a wide range of imaginable applications. Start from sensing and instrumentation telecommunications, machine learning, and quantum computing. If you're interested, we also provide a live demo unit and a GUI simulator to give you a better understanding of our product. You can find more information on our website. We are waiting for you. Together, we are unlocking the power of light.
If you're designing photonic systems, ANSYS Lumerical lights the way. From virtual reality to display technology, from auto sensors to smartphone cameras, from laser design to quantum computing, from 5G to data centers, ANSYS Lumerical is a world leader in photonic simulation. Party tool providers to create new workflows, building better photonic systems on time, on spec, and with higher performance. Referenced in over 15,000 scientific papers and patents, Lumerical has been run in close to 30 million simulations by roughly 50,000 different users, by 90% of the leading research universities in the world, and by all 10 of the top IT index companies. If you are designing photonic systems at the component and circuit levels, ANSYS Lumerical is a complete cloud-ready simulation solution. It's easy to learn and deploy, constantly innovating new solutions and techniques. For reliability, speed, and accuracy, there's only one true leader in light, ANSYS Lumerical.
Power supply, multimeter, and oscilloscope are used for the standard electrical test. In a typical industry in the lab, we need multiple of these devices, but the problem XDAC, a sophisticated source measurement unit for low power applications from simple electronic circuits to complex photonic integrated circuits. We also offer a variety of channel options ranging from 8 to 40, 80, and 120. We are also beginning to develop our product into a chip-scale version with a wide range of imaginable applications, starting from sensing and instrumentation, telecommunications, machine learning, and quantum computing. If you're interested, we also provide a live demo unit and a GUI simulator to give you a better understanding of our product. You can find more information on our website. We are waiting for you. Together, we are unlocking the power of light.
If you're designing photonic systems, ANSYS Lumerical lights the way. From virtual reality to display technology, from auto sensors to smartphone cameras, from laser design to quantum computing, from 5G to data centers, ANSYS Lumerical is a world leader in photonic simulation. We've been helping engineers meet product development deadlines for nearly 20 years, collaborating with leading third-party tool providers to create new workflows, building better photonic systems on time. 1,000 scientific papers and patents, Lumerical has been run in close to 30 million simulations by roughly 50,000 different users, by 90% of the leading research universities in the world, and by all 10 of the top IT index companies. If you're designing photonic systems at the component and circuit levels, ANSYS Lumerical is a complete cloud-ready simulation solution. It's easy to learn and deploy, constantly innovating new solutions and techniques. For reliability, speed, and accuracy, there's only one true leader in light, ANSYS Lumerical.
Power supply, multimeter, and oscilloscope are used for the standard electrical test. In a typical industry in the lab, we need multiple of these devices, but the problem is they have excessive power, limited output, expensive, bulky, cumbersome, and inconvenient. And the solution is XDAC, a sophisticated source measurement unit for low power applications from simple electronic circuits to complex photonic integrated circuits. We also offer a variety of channel options ranging from 8 to 40, 80, and 120. We are also beginning to develop our product into a chip-scale version with a wide range of imaginable applications. Start from sensing and instrumentation, telecommunications, machine learning, and quantum computing. If you're interested, we also provide a live demo unit and a GUI simulator to give you a better understanding of our product. You can find more information on our website. We are waiting for you. Together, we are unlocking the power of light.
If you're designing photonic systems, ANSYS Lumerical lights the way. From virtual reality to display technology, from auto sensors to smartphone cameras, from laser design to quantum computing, from 5G to data centers. ANSYS Lumerical is a world leader in photonic simulation. We've been helping engineers meet product development deadlines for nearly 20 years, collaborating with leading third-party tool providers to create new workflows, building better photonic systems on time, on spec, and with higher performance. Referenced in over 15,000 scientific papers and patents, Lumerical has been run in close to 30 million simulations by roughly 50,000 different users, by 90% of the leading research universities in the world, and by all 10 of the top IT index companies. If you're designing photonic systems at the component and circuit levels, ANSYS Lumerical is a complete cloud-ready simulation solution. It's easy to learn and deploy, constantly innovating new solutions and techniques. For reliability, speed, and accuracy, there's only one true leader in light, ANSYS Lumerical.
Power supply, multimeter, and oscilloscope are used for the standard electrical test. In a typical industry in the lab, we need multiple of these devices, but the problem is they have excessive power, limited output, expensive, bulky, cumbersome, and inconvenient. And the solution is XStack, a sophisticated source measurement unit for low power applications from simple electronic circuits to complex photonic integrated circuits. We also offer a variety of channel options ranging from 8 to 40, 80, and 120. We are also beginning to develop our product into a chip scale version with a wide range of imaginable applications. Start from sensing and instrumentation, telecommunications, machine learning, quantum computing. If you're interested, we also provide a live demo unit and a GUI simulator to give you a better understanding of our product. You can find more information on our website. We are waiting for you. Together, we are unlocking the power of light.
I'm Dr. Yvette Matley, and I'm thrilled to be here today to tell you about the next generation of our NIR spectrometer, the NearQuest Plus. The NearQuest Plus is available in configurations covering the complete NIR wavelength range from 900 to 2500 nanometers, and it's customizable to fit your specific application needs. We have put our 30 plus years of experience to squeeze every ounce of performance out of the components that we're using in the NearQuest Plus. So it won't look any different to you than your standard NearQuest, but the performance of the NearQuest Plus will look much different. I'm very excited to report that we are seeing a 2.5 times increase in the sensitivity into the bench. For those of you who have ever worked in the NIR region, you know that we're always starved for light. And the best way to get the most accurate measurements is to get more light into the system. And that is precisely what the NearQuest Plus will do for you. To accomplish this, we're using various indium gallium arsenide or InGaAs detectors, a thermoelectrically cooled detector that will let you cool the detector down 40 degrees Celsius below ambient temperature. This keeps the noise very low, which also improves on your ability to detect low signal levels. Ocean Insight was the first to develop a modular spectrometer approach. And in the case of the NearQuest Plus, we've kept that going with different levels of throughput based on the slit that we use, with different responsivities based on the gratings, and can actually find its way out of the lab to make measurements, or can be taken and set up very easily where the measurements need to occur. And as a whole, this enables our customers, our partners, to do so much more than they could ever do with these benchtop integrated type of systems. A very important part of the whole picture involving the NearQuest Plus is having the tools that you need to use the data that you're acquiring from that spectrometer. OceanView will enable you to use the NearQuest Plus in absorbance, transmission, or reflectance mode, in addition to providing a full range of features, including strip charting, customization of your data processing, and many other features. we want to quantify and we want to be able to determine sugar for fruit sorting, for example. Ocean has a companion to the NearQuest Plus, called Ocean Intelligence, which is really going to allow you to take that spectral data to the next level. The NearQuest Plus is ready for shipping today, with custom configurations also available to match your specific application needs. That's it. That's the NearQuest Plus.
If you're designing photonic systems, ANSYS Lumerical lights the way. From virtual reality to display technology, from auto sensors to smartphone cameras, from laser design to quantum computing, from 5G to data centers, ANSYS Lumerical is a world leader in photonic simulation. We've been helping engineers meet product development deadlines for nearly 20 years, collaborating with leading third-party tool providers to create new workflows, building better photonic systems on time, on spec, and with higher performance. Referenced in over 15,000 scientific papers and patents, Lumerical has been run in close to 30 million simulations by roughly 50,000 different users, by 90% of the leading research universities in the world, and by all 10 of the top IT index companies. If you're designing photonic systems at the component and circuit levels, ANSYS Lumerical is a complete cloud-ready simulation solution. It's easy to learn and deploy, constantly innovating new solutions and techniques. For reliability, speed, and accuracy, there's only one true leader in light, ANSYS Lumerical.
Power supply, multimeter, and oscilloscope are used for the standard electrical test. In a typical industry in the lab, we need multiple of these devices, but the problem is they have excessive power, limited output, expensive, bulky, cumbersome, and inconvenient. And the solution is XDAC, a sophisticated source measurement unit for low-power applications from simple electronic circuits to complex photonic integrated circuits. We also offer a variety of channel options, ranging from 8 to 40, 80, and 120. We are also beginning to develop our product into a chip-scale version with a wide range of imaginable applications. Start from sensing and instrumentation, telecommunications, machine learning, and quantum computing. If you're interested, we also provide a live demo unit and a GUI simulator to give you a better understanding of our product. You can find more information on our website. We are waiting for you. Together, we are unlocking the power of light.
Welcome back, everyone. Welcome to our second sessions for today's agenda. For second sessions, I would like to invite our moderator, Professor Min Kyoseo. He will be our moderator for these sessions. For Professor Ken.
Yeah, thank you for coming to this session. I would like to introduce the first speaker, Professor Takashi Kuroda from the National Institute for Material Science, NIMS, Japan. And the title of his talk is the development of the photonic crystal-based quantum cascade laser. Yeah, please.
Thank you very much for kind introduction, and also thank you very much, Professor Iskander and other coordinators for this meeting. So I'm quite happy to come back to Indonesia once again. This is second time, and also very beautiful places, and also please thank you for providing me such a great experience. So yes, so today I talk about yes, our recent work on the development of photonic crystal-based yes, lasers, surface emitting lasers. And this is the collaboration, results of collaborations with my supervisors, and I am one of the colleagues of Kazuaki Sakoda-san. He might be that more common persons in this community. So unfortunately, he cannot come here. So that's why that I'd like to explain that our research. So yes, before going to the main topic that please give me a few tens of seconds for about my brief introduction to our team in NIMS. I'm sorry, I am not familiar with this Nobel type laser pointer. So yes, we are currently focuses on two directions. One is that photonic crystal, a photonic crystal based photonic or metamaterial applications to novel optical devices. This is today's topic and led by Kazuaki Sakoda. And I mainly work on the quantum dots devices for the application of quantum light sources. And yes, so here that I briefly talk about the research. So we have a very original technique to fabricate semiconductor quantum dots, and yes, named by droplet epitaxy. So this is in fact the very first demonstration of the self-assembled growth of the semiconductor 3-5 quantum dots. So here, so in this, one of the advantage of this techniques that we can prepare the quantum dots independent of the choice of straight orientations. So here that we use the cubic crystals with a zinc blende type structures. So in general, that in standard growth approach using standard growth approach, normally that they use the growth substrates of 001 surface at this plane. So that here that we can use that 111 directions. So 111 directions are very symmetric surface. So the atoms are arranged in the forming a threefold triangle geometry. So that's why that we can produce that such a triangle shaped quantum dots. So it means that there's no optical anisotropy in any places. So then the polarization is absolutely symmetric. So that's why that this function is used to produce entangled photon pairs quite efficiently. So that's why yes, I'm working on this mainly working this field, and this is yes. So but today that I'm talking about another content. So here we are trying to bridge the two technologies or in the state-of-the-art technologies. One is the photonic crystals and also the quantum cascade lasers. So we create the vertical emitting near mid-infrared lasers using with the help of photonic crystals. So quantum cascade laser, in short, the QCL. So QCL is a semiconductor lasers, of course, but it uses the subband transitions formed in quantum wells. So this is the electronic structures, electronic levels confined in quantum wells. Now that this is the quantum wells, and this is the ground state and the first excited states. So we are going to use the transition between these two states formed in quantum wells. So then the so the higher confinement gives rise to that increase of the transition energy. So that's why that it's quite easy, capable of tuning wavelengths in a wide range, and essentially that yes, very unique light source emitting in the mid-infrared regions. We are now interested in this range. This is important for detecting several chemical species. Yes, so there are several targets for the mid-IR QCL, so like the gas sensing and so on, and diagonal, yes, and yes, many applications that yes. So the difference, okay, so the surface emitting photonic crystal lasers, yes, Susumu Noda in Kyoto has made plenty of that achievement, but not on the QCL at the moment, because there are several yes, difficulties. One is that yes, so now that the QCL, the transition dipole moment is polarized normal to the quantum wave layers. So that's why that the projection of the dipole moment is perpendicular to the layer. So that's why that yes, we cannot use a standard pixel design to get particle emissions. So, and also that the oscillator strength or transition strength is much smaller than the standard semiconductor lasers. Yes, so that's why that we need huge numbers of quantum wells, huge numbers of quantum wells in the growth. So actually that we fabricate those complicated quantum well structures in total more than several micrometers. So yes, we are using molecular beam epitaxy. So it takes a very long time to produce one chip. So it takes a few days, I heard, for producing one chip. So the fabricating that the high quality wafer is also a quite challenging issue. So surface emitting lasers that the length of output window. So that's why that now the beam divergence is quite small. So we can achieve that very sharp collimated, well collimated beam. So then it can the beam is going yes yes we can get such a good beam quality. So then those characteristics are useful for such kind of remote monitoring. So we can irradiate the laser beam from far from the target, then shine the IR beam, then we measure the scattering signals from this one, then we can check quantify yes, the density of chemical gases, toxic gases from here. So for this one, we need good collimated beam. So that's why we need surface emitting lasers. So here is the example of our two-dimensional photonic crystal resonators. We use our photonic crystal resonators to get particle emission signals. So yes, so here we put that on the wafers. We fabricate small circular pillars with in this case square array pillars, and yes, with this size, and you can see so the and where quantum wells is made of indium gallium arsenide. Then on the top that we also put indium gallium arsenide layers, and that make microfabrication that using EV lithography and dry etching. So this is a cross section that you can see that such kind of small structures. So in order to achieve the particle emissions, we need to design the photonic crystals. So this is the in plane band or photonic dispersions of our devices for the square lattice square lattice photonic crystals. So in order to get a strong gain, that the first that we have to use the mode which has a zero group velocity. So it means that this so now that the electromagnetic waves are formed in the form is in a standing wave. So that's why that so that they can get a very high gain, and also that those zero group velocity points are at the gamma point of that of this diagram. Gamma point is at the zero momentum stage. So that's why that the emissions occurs at exactly perpendicular to the surface because of the conservation of the momentum conservation rules. So that's why that we here that we are going to look at we are going to interested in this formals. Yes, and then we have to we have to design that those those modes are so now this is the gain regions of our devices. Then that we So in fact that our QCL that the device by device this gain positions is changes. So that's why that the first that after making the growth that we measure that the gain spectra in gain spectra, and then that we start to design and set that the parameters, and then that we can make that fabricate the final devices and check the performance. This is our cycle. But we what we should do is that we need to characterize everything in the mid-infrared vision. So it's not quite easy. That some useful way to characterize the mid-IR photonic crystal dispersion curves. So that's why that the oops. So in the mid-infrared region, that normally that we use FTIR. So FTIR and FTIR, but the FTIR it's quite useful, but in fact that in standard FTIR they use a very focused. It uses a very focused beam, so that's why that we cannot resolve the angle dependence. So we need to obtain the angle resolved data. So that's why that here we constructed special apparatus to observe reflection spectra of the device with very high angle dispersions that is compatible with standard FTIR machine. Yes, and then at the here this is the first example of the dispersion to observe the dispersion curves at near mid-IR region. So this is a case for that photonic Dirac cones. Yes, photonic Dirac cones are formed in standard silicon on insulator waveguides. So you can see that at some conditions that you can see that this is the reflection spectra for different incident angles from 0 degrees to 3 degrees. So the spectra is systematically changes. So then you see that at 0 angle, at 0 degrees, normal incidence 2 modes are degenerated. So that's what this means, that it is evidence of the formation of the Dirac cones at the gamma point through the accidental degeneracy. This is a standard case, so 2 modes are split at the gamma point. So after that, yes, this is the case of our QCL devices. Now the spectra is not so beautiful compared to SOI case, but anyway, by looking at the peak positions, that we can map the dispersion in plane dispersion curves and identify that the modes which we are going to use the vertical emissions. So for the design that yes, we used finite element method. So the different points for yes, the difference between the standard photon crystal vertical emission lasers is that the first yes, here we need to look at the TM polarized light. So that in standard laser structures that they are going to use, they are going to look at the TE mode. Yes. So and also at yes, another point is that yes, in the mid-infrared regions, there are yes, the device contains a really high density of conduction electrons. This is a purely n-doped semiconductors. So that's why those free carriers also absorbs the IR light strongly. So that's why we surely take into account that the imaginary part of the refractive index of these materials, of the host materials. So then yes, we can also that we need to characterize the extraction efficiency given by this value. So yes, and also that the Q factor we can get the Q factors by looking at by solving the eigen equations of the mode, and then we can get the imaginary complex energies, complex eigen energies. So then from this one we can get the Q factors or the lifetime of the mode. So anyway, the key parameters is extraction efficiency and also Q factors. So then yes, this is it was okay. We are going to change that. We are going to show you that the result of different designs. These are very initial designs. So here we use the circular pillars, the simple circular pillars that are arranged in a square lattice. Yes, and second generation devices that we use such kind of pentagonal pillars. Yes, so then yes, this is the design, and also that this is the actual the pictures of those designs of our actual devices. So you can see that the formation of pentagonal pillars in this case. So okay, so yes, we use finite element calculations using a COMSOL, commercial software, and yes, this is when we used when you used circular pillars. So that in that case that it now that it is arranged in, it has a perfect C4V symmetry. So that's why the modes are characterized by this symmetry notations like A2. So A2 is in fact monopole mode and quadrupole and dipole mode. And dipole mode has a very strongly coupled to the free space. So, but however, in that case, because of the strong coupling to the free wave, so Q factor is slightly much lower. So that's why we cannot use those two modes. So we need to use these two modes. So this is the actual Q factors for each mode. So among them this B2 mode shows that the high Q factors. Okay, this Q factor is limited by the imaginary part of the refractive index. So that's why it is not so large. But anyway, yeah, to compare to yes, standard calculations. So anyway, we can expect this mode will go to emit. Yes. However, yes, you see that this is quadrupole mode, so it's quite difficult to emit the light in normal directions because of the symmetry. Yes, high symmetry. So that's why that the emissions must appear slightly oblique emissions. Yes, this is our predictions. And in fact, that this is the far field pattern of the first device made of the circular symmetries. You can see that such kind of donut shape far fields patterns. So it means that exactly at the exactly normal emissions is prohibited, but these slightly oblique emissions only appears. Yes, yes, this is absolutely single mode emissions for this mode, but because of the yes, because of the finite device process, there is an uncertainty of momentum. So that's why that we can see that such kind of yes, donut shape. Yes, so signature okay. So the signature is also known as the formation of band states in continuum in is here. So okay, the problem. Okay, this is the performance of the devices. So this is the first device performance. So here we can see that the emission spectra, our single mode emission spectra at this our almost target wavelength regions 4.3 micrometers or something like that. And this is the intensity power output as a function of the input current. This green line, green marks. So then there is a threshold. Then it starts to emit. Yes. So now yes, this is the first demonstration of the mid-IR particle emissions. So we're quite happy around 4 years or yes. So but unfortunately yes, the output power is quite small, so around 10, 12 milliwatt or something like that, because of the yes, lower power. It must be due to the formation of the symmetry protected bound states in continuums. Yes, so because of the presence of the perfect symmetry, so it's quite difficult to see that difficult to get the strong output. Yes, so that's why that we are going to slightly yes break the symmetry. So then now that we use the pentagonal pillar shape like this one. So pentagonal shape. So why we choose this pentagonal shape is that we can essentially optimize the coupling extraction efficiency or extraction efficiency by changing several small numbers of parameters like that. Here that we are going to change that these are circular positions C1 and C2 values. And then we calculate the extraction efficiencies with changing those values. And then yes, we can get some optimized pentagonal shape to get the highest intensity. So actually this is yes, the optimized shape of our pentagons. So then this is the calculation results that for the first generation yes devices that yes this is a relatively high Q factors we can achieve, but the extraction efficiency is quite yes not so large, yes, this value, because of the presence of symmetry. So weakly broken symmetry case, pentagonal pillars. So in that case, so now that we can get relatively yes finite extraction efficiency. Okay, there are four modes. Four modes are close to the gamma point, and then yes finite values, and also yes similar Q factor values. So then we hope that we can get high output. So this is the performance comparison between the two devices. So the first device is circular pillars, perfect symmetry. Okay, the intensity curve is like this one. Its output is limited to around 10 milliwatt. So the second device is that it's this one, this black, this black lines. So now that it is 5 times higher, because and also that the far field patterns, it shows a sharp single peak because the symmetry is broken. So then we can get the higher output powers. Yes. So still that there is a symmetry is not still that there is partially symmetric. So that's why that we need to break the symmetry more. So our idea is quite simple, that we are going to change the square lattice photonic crystals to rectangular lattice photonic crystals. So now that okay, so now that the symmetry is much more broken. So that's why that we can get a higher intensity, and also that for optimization that it's quite easy, because that in the square lattice case that there are 4 modes are closely at the gamma point. So these 4 modes, we are going to look at the 4 modes as a function of the several parameters. But here this degeneracy is lifted to the 2 modes. はい、ありがとうございます。So then the optimization is quite easy. So then okay, so okay, here is that the characterization technique. So here we are looking at the photocurrent data, photocurrent signals with using a tunable lasers with changing the angles, because of the QCL also works as a detectors. So then we are going to the photocurrent as a function of the wavelengths with excitation laser for the y-axis angles and x-axis. So now that you can see that the absolutely different emission properties, showing that the evidence of the formation that these unique band structures. Okay, I'm going to skip this one. So now that this is the final slide. So this, okay, now that the first device and second device is 5 times higher. Now the final device, rectangular lattice device, is much larger. So this one is positive. This one, and also that we achieved now, yes, peak output power is higher than the 1 watt. So then yes, this is the current status of our mid-IR QCL lasers. But still, compared to the standard QCL, the value is quite not so large. But anyway, yes, we are going to improve this one more. Okay, here is the acknowledgement. So this is a collaboration with NIMS and also Toshiba and yes, Tokai University, and yes, Toshiba makes a very excellent good wafers for this one. And yes, that's all. Okay, thank you very much for your attention.
Yeah, thank you very much. So it's time for the questions or comments from the audience. Yes, please.
Thank you very much for the interesting talks, Professor. So my first question will be because previously you showed that there is some Dirac point at gamma, right? So I want to know, have you ever tried to do lasing with this point? Because like previously you already said that for the A and B modes, it's a symmetry protected PIC, so it will not lace at gamma point, it's off angle. So what is your comment about that? And then for the second one is that you use this pentagon pillars rather than the symmetrical circular pillar. So did you use that to break the symmetry of a finite Q factor of the BIC mode, or is there any other reason to do that? Thank you.
About the first question, okay, so we want to we want initially that we want to use this Dirac bonds dispersion Dirac bond modes for that erasing more that in fact that several researchers have already tried to demonstrate this one. But unfortunately that at the moment that yes, this is only for the story for the SOI devices. So at the moment that we cannot successfully make the erasing at this Dirac modes. The problem is that we need a more fabrication precision to make that Dirac modes. And the second question is that okay, so for the pentagonal mirrors, we use the pentagons that essentially that the Q factors are limited by not the design. Q factors are not determined by the design, but determined by the imaginary part of refractive index loss. So that's why the Q factors are almost the same. Yes, but then using the pentagons, we can get a larger extraction efficiency. Yes, this is the same for the pentagonal case and also the rectangular this case. Yes.
So this Q factor is measured for the normal incident, or so the Q factor is measured for the normal incident lasing, not for the off angle one.
Right, exactly.
So the PIC mode is already a quasi PIC at the gamma point.
Yeah, yes.
Okay, thank you.
Any other questions? Let me ask you a quick question. So you are still using the TM polarization in the level of the quantum L, and then what is the final polarization state of the second device using the pentagonal pillars?
Physical reason?
I mean the final polarization state in the plot field.
Final polarization state. Okay. I have not yet measured the final polarization state in the in asymmetric devices, but I believe that this must be some linearly polarized state, because to assume that this is elongated.
It would be some subtend direction, right?
Yes.
Any further questions from the audience? If not, then let's thank speaker again.
Thank you very much.
So now let's move to the second invite talk, which will be given by Professor Irina Kabakova from the University Technology Sydney, Australia. And the title of her invited speech is the Brilliant Microscopy for Label-Free Micromechanical Imaging of Biological Materials.
Okay, I think everything is working now. I'm sorry for this delay, and I want to start by saying this is my first time in ISMO, and I would really like to thank the organizing committee, and in particular Professor Alexander, for inviting me here and giving this really lovely opportunity to visit you all and to present my research and also meet the community. Really valuable experience for me, and I hope this is not the last one. And we are going to change gears quite a bit, I'm afraid. So from lasers to biophotonics and bioimaging. So I will be talking about brilliant microscopy for micromechanical imaging of biomaterial cells and tissues. I'm Marina. I'm professor at UTS in Sydney, Australia, where I run my group. And before we proceed, I would like to acknowledge the funding that supports our research, and this is Australian Research Council funding and the 2 Centres of Excellence, COMS and Cubic. So this is my lovely group. In Australia, we mostly have nice weather and we love spending time outdoors and barbecuing. So this is one of our recent catch-ups and a barbecue in the park. And a lot of data which I will be showing you is actually not me taking this data in the lab, but my team members, my wonderful postdocs and students who are all here. So before we start, I would like to ask you, have you heard of mechanobiology? Have you heard such term? And if you heard, please raise your hand up. Yes, we have a few hands, but not too many. And that's excellent, because this is what I'm going to talk about. So mechanobiology is very exciting field in modern biology, and it's very recent, to be honest. So about 20 years ago, people realized that there is a strong connection between cellular function and the health of cells and cell mechanical properties and the environment, mechanical properties of the environment of cells. And here you have a very good example where mechanics plays a very important role. So if you have stem cells which are not differentiated, they're sort of neutral if you think of it, and you place them on different substrates, stiff and soft, those cells will behave very differently, and they will start dividing and changing, and they will produce cells of completely different qualities, and they can form different organs. So they can differentiate into muscle cells or fat cells or skin cells and things like that, depending on cues they sense of the mechanical environment outside. Isn't it fascinating? When I learned it, I thought it's really amazing that we can do things like that. But there is also very strong connection between pathology, so disease, and mechanical properties. And I give you one example. So cancer, very bad disease. You know that cancer cells, they divide very fast. But you may not know that cancer cells need to change their mechanical properties to get from the site of primary tumor to the bloodstream, and then from the bloodstream to form secondary tumor, right? So this is a process metastasis. And to do so, the cells need to change themselves to become really squishable, to go through small places and openings to get to the bloodstream. So it's actually fascinating what happens on mechanical level in tissues and cells. And this is why we need all sorts of measurements, characterization techniques to measure mechanics on a cellular level. And this is very non-trivial task, because cells are small, so they can range from 5 micron to 100 micron or so, depending on the type. And how do we measure mechanics of a single cell? So we need subcellular resolution, we need sort of submicron resolution to resolve features. And ideally, we want to do things non-destructively. So we don't want to ruin these cells. So for example, we have the gold standard of mechanical characterization and cell and tissue is indentation, where we have a little needle on a cantilever, and we pretty much just going across this cell and we're poking this cell with this needle. So first, we are only measuring on surface, right? We are not measuring inside the material. And second, well, you may throw the cell afterwards, after you poked it 100 times. It's not going to be any good, right? So there is optical tweezers where we put little beads. They're usually dielectric particles, a few micron in size, and we can do wonderful things with it. We can attach it to a cell, or even better, we can attach those little beads to, let's say, a DNA molecule, and then with the beams of light, focus beams of light, we start to manipulate those beads, and we can either kind of squish the cell and see how elastic or non-elastic it is, or we can stretch DNA molecules. This is wonderful, very powerful. It's not easy, and we somehow need to deliver those beads. So this is what brings me to brilliant microscopy, and this is our specialty in Sydney in my lab, where we can only use one focus beam of light. We don't need to poke anything, to squeeze anything, and we can shine light inside the cell, and we can learn about mechanical properties in the focal volume. All right, so in my lab, what we do, we specialize on many different things, and our primary technology is brilliant imaging, and we apply to many different problems, from engineering novel biomaterials, and I will show you example of it, to mapping cells and tissues. Here, where the three-dimensional benefit of brilliant microscopy comes through, we are not measuring on surface, we can measure in volumes just by scanning the beam of light. So what you see here is we have 2D cell mapping, or we can measure organoids like that, and we can map mechanical properties across tissues which are quite big, so a few hundred micrometers in size. Of course, the technique is quite generic. We don't have to apply it to biomedical, to biological matter. We can also look at solid state and learn of dynamical processes like phase transitions. So this is phase transitions in perovskite crystals. And I'm really passionate about integration of this technology so that we can apply it in situ and in vivo in endoscopic arrangement. So we can look at things inside the body. We don't have to take biopsy. Okay, so in the talk, I'm going to very briefly introduce the technique and physical parameters and limitations. I'm going to show you two examples, one in application to cancer research and second to biomedical engineering of new materials for cardiac research. And I'm also going to show you some first attempts in integration and creating brilliant endoscopes. All right, let's go. So the physics of brilliant light scattering is very old. It's more than 100 years old. However, it's only started to be applied to biological tissues and in biological sort of context. We focus it inside the material of interest, and where we have the focal point in that beam, so that could be very small voxel, so it could be very small volume of, let's say, micron cubed. This light interacts efficiently with the matter. And in this matter, we have tiny pressure waves. So those pressure waves are originating from thermodynamic fluctuations of pressure and density, and they travel with the speed of sound. So this happens that our light is coupling with the gigahertz pressure waves and gets a little frequency shift. And you can think of it as a Doppler shift. So if we have a moving density wave, light reflects from it, but because the wave is moving, it's traveling with the speed of sound, we have a little Doppler shift and we obtain frequency shift, right? So this frequency shift, we call it brilliant frequency shift, and it's a direct function of a few things. It's refractive index of material, but there is this V, which is the sound velocity, right? And sound velocity is a function of elasticity and density. So it's a ratio of longitudinal storage modulus and density. So if we know that density doesn't change significantly, and we have some idea of refractive index, Then by measuring frequency shift, we can directly determine the longitudinal modulus, or we can keep it as a frequency shift as a marker, as a contrast mechanism. Of course, this is interaction of light and sound. And because sound does not propagate forever and doesn't exist, you know, a very long time, those sound little waves, they die out. The width of our peaks is inversely proportional to the lifetime of phonons. And that's very useful information for us because it let us know how lossy is the material. And loss in those squishy biological systems usually is linked to viscosity. So in one go, we can learn about elasticity and viscosity of our tissues. Well, it's a bit hand-wavy idea, and we can discuss the details later on. So we are quite new community, but we have international society. So if you're interested, you can find us online. And we also have a conference like this one every year, and it's called Brilliant Conference. And this year it's happening in Berlin, in Germany. And the organizer is Professor Jochen Guck from Max Planck there. And we also just published the first paper that gives you standards, how to measure, how to report the data, how to analyze the data and things like that. So have a look if you're interested. So a few words on the spatial resolution. So we use beam of light. We can focus it to diffraction limit. So you might think that we are diffraction limited. So we can go to, let's say, a few 100 nanometer resolution in this technique. And well, unfortunately, it's not quite right because our interaction are not only light interaction, it's interaction between light and sound waves. And we are taking measurement over extended period of time, let's say certain milliseconds or seconds, and the phonons are moving. So it is actually the acoustic mean free path, so how far the phonons go. That's what limits our resolution. And in those biological squishy materials, the phonons don't move very fast, they decay very fast. So it's on an order of 1 micron. It's actually pretty good still, because there are not so many mechanical techniques for characterization which have this resolution. So we are quite happy with 1 micron. So it's a bit worse than the diffraction limit of light if we are measuring with visible laser. But, you know, it's not such a bad reduction. And there are more aspects to it, depending on the structure of the material. So if you have periodicity, if you have boundaries, that definitely going to affect things. And if you're interested, have a look at the review. There is in-depth discussion about the resolution limits there. So now instrumentation. I have to give you a warning that there are many ways of doing brilliant microscopy, and I don't have time today to discuss all of it. But I'm going to talk about the 2 approaches that we use in the lab in Sydney. Importantly, I want to really sort of make you aware that doing this measurements is quite tricky. And the reason for it is the scattering efficiency, brilliant light scattering, is quite low. So if you have 1 billion photons, then maybe 1 will interact with the pressure wave. So the efficiency is very low. It's similar to Raman scattering. Secondly, the frequencies that we need to detect, the frequency shifts, are in gigahertz range, which means that a normal diffraction grating or a prism is not going to work, right? It doesn't have enough resolution. So these are all the challenges, and we need to somehow overcome it. So basically, we have 2 ways of doing spontaneous brilliant scattering measurements, and one is to use a scanning tandem Fabry-Perot systems, which is pretty much coupled Fabry-Perot interferometers or etalogs, and they're synchronized and aligned perfectly. And in these systems, the light beam goes 6 times across these 2 etalons, and that gives us very, very good frequency selectivity, and that works very well. So the downside of the system is that you know, you have to put everything on vibration isolation stage. You have to use piezo to change distance between the mirrors. So it's not that good, I would say. But it sort of works, but the speed is limited to about 1 second per spectrum. And the second version is non-moving etalon. It's also a Fabry-Perot with coatings, and it's called Viper. And that actually was invented in Japan in late 1990s for telecommunications, and then applied for telecommunications. But now it reached to all sorts of fields, from atomic clocks to spectroscopy and microscopy. All right, so in Sydney, we have both microscopy systems. The first one is based on TFP, so this is tandem Fabry-Perot system. Wonderful system, very high spectral resolution, reconfigurable. You can measure many materials, change the free spectral range, etc., etc. The downside is acquisition time. So if you have big bulky sample and you want to do 3D scanning of that, well, good luck to you, because it's going to take about 10 hours. So the second system is something new that we developed, and it has Olympus inverted fluorescent microscope, and it coupled to yet another laser which drives these Brillouin scattering interaction, and it has its own VPA, so the virtual imaged phase array spectrometer, operates at the same frequency of laser, 660 nanometers. This is for a reason, because we want to go away from the blue and green. Blue and green are absorbent tissues, and we don't want to damage our cells and tissues. So 660 is within the transparency region, and nothing is, or almost nothing is absorbed there. So this system is a little bit faster. So we're already able to measure spectrum in about 20 to 50 milliseconds. So if we need to measure, let's say, 2D cell map, then it's about maybe a few seconds or a minute or two. So it's not too bad. So you can do imaging with the system. All right, so this is just an example for you how the diffraction patterns look like on VPA spectrometer. And what you see here that confirms my previous statement, you see very bright peaks. Unfortunately, these are not Brillouin peaks. These are Rayleigh peaks. So this is all the stray light and elastically scattered Rayleigh light. It's way more efficient and strong. And then what we need to find, those little tiny peaks here, which are peaks of interest. So these are Brillouin peaks, and we need to find them, isolate them, feed them, okay? So now what we can do with it. And I'll show you two applications, and we'll start with first talking a little bit about cancer. I have a long-term collaboration with Gowan Institute in Sydney, and this is an institute of medical research specializing in cancer research. And my team works with Thomas's labs there, Thomas Cox, professor at Gowan, and Thomas has specific interest in pancreatic and breast cancer. So in this work, we looked at triple-negative breast cancer, and we had tissues from mice and from people. And initially, what we were after is to compare how cancer cells and tissues are different in their mechanical properties. And what you can see here is that tumor cells are stiffer compared to healthy ones. But second point of interest was to look at how heterogeneous cancer tissues are. And if you look at, this is your histology staining. So this is just mouse tissue, right, in collagen. And you can see that, yes, there is some structure, but it's not really visible in a sense. You cannot define the regions, what is stiff, what is soft. If you look at the Brillouin map, then you see hotspots. So the color here is coded as a Brillouin frequency shift value, absolute value. And red color corresponds to stiff locations, and blue color soft, low frequency shift. And you can see that there is quite a lot of heterogeneity across. If we overlay Then in the middle of that tissue, somehow it was softer, at the periphery it was stiffer. So this is an interesting point. If you do chemotherapy for this cancer, the cells that are sitting in stiff parts have completely different metabolic processing. So they consume nutrition differently to the cells which are sitting in the soft one. So they will respond to the treatment in a very different way. And in fact, this is one of the reasons why triple negative breast cancer is so notorious and so hard to treat, and it doesn't respond to chemotherapy at all. So that was very interesting finding and confirmed some of our biological hypotheses. So now we go to cardiac tissue repair, and this is my colleague Carmina Gentili, who is in the School of Biomedical Engineering at UTS. And he is very passionate in designing those little mini hearts. And I have a little video for you. So if can we play the video, please? How do we do it? So I have, okay. So if you look very, very carefully, what? Okay, no? It was working, yes. So the thing is, yeah. No, it should fine. Yeah. So let's look again at the beginning. Do you see it's moving? Yes, like the amplitude is very small. So Carmine makes these mini hearts out of hydrogel and all sorts of cells. And they have cardiac cells and epithelial cells to create vasculature. So they are functional, the same as our hearts. Our hearts, they push the blood. So they have mechanical function, right? So they contract. And those mini hearts also contract, although the contractile potential, I would say, is a bit low and the frequency is not quite there. So the idea for these mini hearts is they're transplanted to, well, at the moment, animals, so the experiments are that have heart failure. So with heart failure, what you have, cells die, and the tissue becomes fibrotic, it becomes too stiff, it's no longer contracts. So they are injecting those mini hearts into a failed tissue in the hope that the cells will incorporate into these dead regions essentially and regenerate those regions. And the mechanical functions of this heart, as well as their sort of biological and chemical potential, is very important. So the problem is that when we started working on those on this project, these hydrogels, they deteriorate very, very fast. So in 2 days, those hearts, they disintegrate, they fall apart. So we thought what we can do about it. And we decided to incorporate proteins from silk, and you can see there's silk fibroin here, into the model. So silk fibroin is a protein extracted from silk fibers. It's completely biodegradable, and it's also a natural material, so it doesn't create immune reaction from the body against this material. So it's a very good idea to incorporate it, and the material has very good mechanical properties, and it kind of stiffens the network and changes the porosity and many other factors. And we wanted to know at micro scale what happens to the material, and if we can tune mechanical properties of the material by changing concentration of the silk. So this was the work done by our student Laura Vittori, and we've shown that with a small concentration of silk, indeed, we can increase stiffness. And those hearts, thank you very much, and those hearts, they were actually changing the frequency of their contractile activity, and stiffer these hearts were contracting with a high frequency, which is to be expected because you're changing spring constant essentially. All right, I need to hurry up a little bit, and the last couple of minutes I'll spend on talking about the endoscopy and the work towards endoscopy. And that's in collaboration, this work is done in collaboration with Stuttgart University. I visited Stuttgart just the week before I came here to Bali, and we had a very nice project where this gentleman, Joshua Trapp, who is a PhD student in Stuttgart, visited us a couple of months ago and did these experiments. All right, so the major challenge of achieving fiber-Brilliant scattering or fiber-Brilliant imaging is the fact that the fiber itself sketches light. So if you do experiments and replace one-to-one all the bulk components to fiber components, then you quickly notice that you're not measuring the target media. What you're measuring is on the same frequency, and it's pretty much the frequency of brilliant scattering in fiber itself. So there are a number of ideas how we can separate the incoming and outgoing or scattered light in those fiber systems. And one of these ideas is by using two fibers. So one for delivery of light, and second one is for collection of the scattered light. In that case, the signals don't mix and you are measuring directly the scattered light. Of course, you need to be very careful because the scattering volume is small and scattering efficiency is very small too, but that's possible. And we done it by just putting two fibers and a green lens together. It kind of worked, but the efficiency was very poor. And the reason for it, this is centrally symmetrical system, of course, and you have two fibers which are like 2-point sources. So if you model it, then there is no overlap. You focus light in one spot, but you're not collecting light, scattered light from that spot. Okay? So the efficiency of back collection is less than 1%. So it's a bit pointless. And yes, it worked in water and it worked in ethanol, but it would never work in tissue because tissue is notorious. It's multiple scattering and you have to have very, very efficient optical systems for that. So to overcome these disadvantages, we've done a range of experiments. And the first idea was sort of very trivial. What if we replace normal fiber by a hollow core fiber, where there is no material in the core, so there is hence no brilliant scattering in the core, and we don't have to filter anything. And that worked, and that was published in 2020. We used this fiber where it was the cylinders that created a band gap, and that was the guidance principle for the fiber. But I want to spend a minute or two discussing this setup, which is what Stuttgart people helped us with. And these are free-form lenses which are 3D printed at the tip of the fiber. And it works in that way. So you have a first fiber that guides light in, and then you have this surface, which is focusing light into the point in tissue, let's say, and the scattered light is collected by a second surface and coupled into the second single mode fiber. All right. Very quickly, this is how the device was packaged. There is a little lens here. You hardly can see it. We compared it to no lens device. And of course, lens device was performing much better. The focal spot size was about 10 micron in lateral and 43 micron in axial. So not really tiny, but nonetheless, for tissue imaging, that's reasonable. And this is how the result look like. So we tried to characterize our probe using this target with features down to 10 micron or so, and we were able to measure really well all the features down to 10 micron. We did also mapping of UTS logger, which worked very well. We were able to resolve spectra of different polymers using this probe. And you can see there is no background whatsoever. So we're really able to separate incoming and backgoing light. And we put this probe to a test using biological materials. So these are protein droplets in liquid solution. So unfortunately, the droplets were fairly small, so they were about 10 micron. So we just barely see them, but it's very, very blurry images. And we need to either improve the resolution of our probe, spatial resolution, or we need to find a different biological material to test this probe. What I wanted to mention is, so it brings me back a little bit to the talk that Carson given this morning. So this is a direct design. So this is sort of intuitive, right? We have two lenses that are focusing in the point. I wonder what indirect design can do, right? Because they may look nothing like these lenses, but they can perform much better. So that would be an interesting question to ask. Well, with this, I would like to summarize. I've shown you several examples and also some integration work going towards endoscopy. And I want to use the last minute to invite you to our Australian conference called WOMBAT. And that's conference on brilliant scattering and optomechanics. If you have interest in those subjects, submission is still open and it will be in Sydney in early February. Please come and visit us. And thank you very much. And I acknowledge all the members of my team and the funding bodies again. Thank you.
Yeah, thank you very much. So it's time for the question or comment from the audience. Let me ask you some couple of questions. The first one is that you showed us the examples of their cancer, their tumor cells. So what kind of other some possible biomaterials can be effectively examined by your brilliant scattering, the endoscope?
Well, I think the world is your oyster. You can measure pretty much whatever you want to, as long as the material does not absorb very much at the wavelengths of the driving laser. Of course, the depth of imaging is similar to other optical techniques. We have depths of imaging of 100 or few hundred micrometers, depending on how scattery is the material. So more opaque things have lower density, depths of imaging. Yeah. But you can look at hydrogels, you can look at tissues, there are studies, there's actually a few groups in Japan who are interested in the application of this technique to bone. So there are lots of interesting questions related to osteoporosis and diseases like that in bone material. So you can still do it, yeah.
Yes, thanks for. I just I was not fully. I'm not deep in the sort of experimental aspect, so that's why this might be a stupid question. But if I understood, this is like all confocal type of imaging type of techniques. Yeah. So is there a way to parallelize actually this image acquisition? Because I had the impression that this is something that takes a lot of time, and maybe one can take inspiration of techniques from OCT also, where at least line scans might be possible. Is this like a development?
Absolutely. That's a very good question. I didn't include it in my slides, but there is a lot of activity going around the world to parallelize. So the line scanning already exists. You can do brilliant FTR measurements as well, and that can give you wide field imaging. It comes with certain penalties. So I guess if you're prepared for the penalties, confocal gives you the best resolution and the best spectral resolution as well, because you don't have any crosstalk or anything like that. But for some applications, those penalties are totally acceptable and you can speed things up significantly.
More questions? Yeah, please.
Okay, thank you. Can you explain a little bit about the consensus statement on the brilliant scattering mechanism? So what kind of consensus was this? Is this the setup or is toward to standardization?
So the paper I mentioned, the consensus statement. So consensus statement is pretty much a paper released by the Brilliant Society that summarizes all the technical requirements to do the measurement with reporting standards. So the field is quite evolved these days. There are a number of ways how you can do the measurement using different apparatus, but there are, I guess, to date, because everyone was evolving slightly differently and reporting slightly differently, it's very hard to compare those experiments. So the consensus statement puts the minimum requirements, how to report the measurements and how to analyze the data so that we can start comparing it across the labs and across the techniques. Yeah.
Some further questions? Yes, please.
Thank you for nice talk. And it seems like you do imaging on the floating cells or tissues, but not adhered cells. Is it correct?
I'm sorry, not which cells?
The cells is immobilized, it attached to the surfaces.
There is no reason to not look at them. In fact, they're usually on substrate. So cells do not survive very well when they are floating in liquid. They need to attach because they need to migrate. So there is no reason why you can't do it.
Okay, because of you, if you want to go to the higher resolutions or try to increase the contrast, maybe using some surfaces.
Yes. So in fact, majority of the samples are either monolayer of cells, they are on hydrogel substrate. So they're sitting on the substrate, they can move around. Yeah, so that works. There is no limitation to that. And the spheroids which are shown, they are embedded in hydrogel. So they're still getting all the nutrition and they use hydrogel as a mimic of the surrounding tissue so that they get the support. But it's a nice question, thank you.
Yeah, we have to next talk. So let's thank speaker again. So let me introduce the last invited speaker in this session. They are Professor Rahmat Hidayat. They are from the Institute of Technology of Bandung, Indonesia. And the title of his talk is Highlight the perovskite nanocrystals for solar cells and their crucial effects of their surface defects and states.
Okay, firstly, I would like to say thank you to organizing committee, particularly Dr. Alex Iskandar, who give the opportunity for me to stand here to give a presentation about our research. And usually, I always be there, become a member of organizing committee. Okay, thank you very much. And okay, this time I would like to talk about the halide perovskite nanocrystal semiconductors with application for solar cell. And the focus, my talk is about the crucial effects of surface defects and states. And this is the outline of my presentations. And I would like to give an introduction about the halide perovskites and crystal structures and how to prepare the samples. Actually, this is a very general knowledge, but I noticed that the perovskite is not so popular in photonics researchers. Not really, maybe you already know, but not very popular in photonic researchers. So from yesterday till today, maybe the first time I heard about perovskite in the presentation by Professor Iriana. This is the first time I heard this perovskite words in this symposium. And the second part about the crystal defects and defect states. And the last part is how to identify and to understand the effect of surface defect states on the perovskite solar cell characteristics and performance. Okay, maybe you already know that now we have a third generation of, there are 3 generations of solar cells. And the last new emerging solar cell is based on perovskite solar cell, perovskite materials. So what is a perovskite materials? So this is actually not the really new materials, because we have already know many types of perovskite materials. And maybe for optical and photonic researchers may be already familiar with the oxide inorganic perovskite, where we have oxide as the element, the constituting element of this perovskite crystal. But now, maybe in the last 1 decade, we have halide perovskite, and we have iodide or halide element in this crystal structure. So yeah, okay. And but there is a big difference in oxide perovskite. Mostly, they have non-semiconducting or non-semiconductor. But halide perovskite, we have semiconductor properties. And okay, this is the crystal structure of perovskite, and we can draw the crystal structure like this or also like this one. And the general structure formula is AMX3 or sometimes ABX3, where A is the monocation from alkali metals, and B is a bications here, mostly is tin and lead. But very recently, many researchers trying to use germanium. And X here, monoanion halides here. And the most popular is iodide, and next is bromide. And this is the structure ABX. Instead of alkali metals, here, we can also use organic cation as the A component. Okay, there are many applications of halide perovskite. In the beginning, of course, the aim of the application of halide perovskite is for solar cells. But after a few years, then the application expand for photodetectors. And this is interesting. It's not only for UV visible light, but many perovskite materials can be used for detect X-rays light. And other application, actually this is opposite of this application. That is for light emitting diodes or laser. And this is interesting. In the same materials, we have we can apply for photon to electricity conversion, but for other application, we use for electricity to photon conversion. And very recently, maybe in the last 5 years, Okay, in the last 5 years, there are many reports reporting about the nonlinear optical properties of these perovskite materials. The origin is from the symmetry breaking from centrosymmetric to non-centrosymmetrics in these materials for particular types. And in this case, we have we can apply for photon-to-photon conversion. So this is a very interesting materials, many potential application with interesting physical properties. And now, but the problem is for example, for solar cell application, we must make a very thin layer. And the most simple method is using wet chemical process. And this is a simple illustration of the process. We just do spin coating and dropping by anti-solvent, and then we can get a thin film. But the films contain polycrystals of nanocrystals. It forms grains with the size maybe 100 nanometers. So many researchers trying to improve the method, the preparation methods, and for example, like this, various type of layer preparation methods. The aim is to extend the grain size. By increasing the grain size, then we can reduce the interface grain area. So it may help to improve the properties. And this is the basic solar cell structure. If you want to make a solar cell using this material, the preparation is very simple. We just put the perovskite layer in between electron transport and hole transport layer. And we can get, this is a scale laboratory devices. And okay, so what is the basic principle of solar cell? When a light or photon absorbed by perovskite, and then electron will be excited to conduction band, and the electron will be transferred to electron transport layer and going to oxide electrode here, metal electrode here. And the hole also moves to opposite electrodes, and the voltage will be governed in between in these two electrodes. So the basic phenomenon is photovoltaic. And in general, we can still consider the basic concept of silicon semiconductors to understand the process happen in this solar cell. But if we look at in detail, the process really different. There are some big difference between silicon and these perovskite materials. The first is silicon built by covalent bonding, but in halide perovskite is built by ionic bonding. And there is no concept of intrinsic types, and also, but in halide perovskite, usually they have direct semiconductors properties, but the diffusion lines are quite different. In silicon can reach up to 100 microns, but in halide perovskite only a few hundreds meter up to a few micrometer. And in the beginning, there are many studies about the electronic structure, and it is the work by Philip and co-workers in maybe about 10 years ago. They saw that the electronic electronic structure consisted of valence band and conduction band. And we did also the same work for MIPBI3, and we also confirm that there are a valence band and conduction band, but the valence band is contributed from iodide, and conduction band contributed from lead, yeah, PB. And this combination PB and I is very important because they form the octahedron structure here. Octahedron structure here. So that's why in recent times, the absorption of light will be interpreted by the formation of exciton by the involving this octahedron structure. Okay, but unfortunately, this material, because this is ionized crystal, so there are many possibilities, the formation of the defect inside or particularly on the surface. And some calculation works reported the formation of gates energy defect level in the valence band, on the conduction band, and also in the band gap, depend on the type of defects. And then what it is, this will influence the process of electron and hole extraction in the solar cell. And particularly, if the non-radiative recombination because of these defects large, then it increase the sun resistor in the equivalent circuit. And okay, but how we can identify and understanding the effect of these surface defects? And of course, there are many characterization methods, but we are focused on the use of impedance spectroscopy, particularly intensity modulated photovoltaic spectroscopy. So we give a perturbation in modulated signals, not from external power supply, but from light. So we can get impedance from these measurements. The other technique using transient photovoltaics or transient photocurrent. We shine the solar cell by a pulse laser in nanoseconds, and we record the decay of the voltage or current. And of course, in this presentation, I only show the transient photovoltaics, and the measurement is in open circuit conditions. So the decay will correspond to the accumulation of electron or hole at the electrodes and the relaxation to the valence band. Okay, so first there are three cases, and the first case is to see how the morphology effects affects the performance. These are different structure of perovskite solar cell. This is compact hetero layers, and this mesoscopic structure, different type. But the brown is the perovskite crystals. So there are two the VI characteristic almost the same, but this is better compared this one, the CLA, and the decay looks like exponential. So this tells that accumulated. So we focus on the TiO2 or the transport layer parts. So after electron excitation from valence band to conduction band, electrons moves to TiO2 here. This is electrons transport layer. But because the measurement under open circuit, there are no current flowing out from the cell. So the electron accumulated here. So it behaves like a capacitor. But there are relaxation pathway here, directly from conduction band to valence band or via surface states. And then this process behaves like a resistor, sun resistor here. But in this case, we have a simple exponential decay. We can see both in these cells. But if, okay, now we look at in detail in the short time region. This is in logarithmic scale. And we can see this is the process in the microseconds. We have a very different feature of decay characteristics. And the cell A rise slowly here, but the cell B rise quickly. This mesoscopic structure rise very quickly. There are two different characteristics. And we are trying to understand about this difference. So we consider the electron photogeneration and transport from perovskite to TiO2 to titanium oxide layer. And this is a general equations. But in this case, in TiO2 layer, there is no photogeneration. Photogeneration occurs only in the perovskite layer. So we can simplify this equation maybe like this, but we consider that the population of the electron at this TiO2 layer composed by or consisting of two parts. The first is determined by the relaxation process, TiO2 at TiO2, as I shown before, and the other part is represent the supply, the supply of electron from perovskite to TiO2 layer. So there are two factors, transport and recombination. So we try to do a convolution of, this is a simple convolution calculation, and we get the potential change response like this. So this is the simulation. We can see if the recombination factor affected the decay in the long time region domain, but the transport determine the rise part of the decay. Yeah. So the rise part is originated from electrons or determined by the electron transport across trapping sites. There are many trapping sites at the interface of grain. So this will delay because maybe the electron undergoes trapping and detrapping in the trapping site. And another case, we usually prepare several samples in one batch. And this is an example. We have we prepare several samples and measure the characteristic, and we see different characteristic. This is the good cell here. I'm sorry. This is the good cell. It is moderate, and this poor characteristic sample or cells. What is the reason? The difference in this variation of characteristics? Because if we characterize, for example, the optical properties, this is all samples shows the same absorption, shows the same absorption spectra with almost same absorbance. So they have almost the same thickness, same optical absorption coefficients. And if we also check the crystal structure, yeah, all sample shows the same XRD pattern. Yeah, all shows the same XRD pattern. No difference in the bulk characteristic of the fabricated perovskite nanocrystal layers. So, but why the solar cell characteristic difference? So this may be important questions. So we are trying to elucidate this difference by doing some measurements, but the main part is using transient photovoltaic measurements. And we can see here for the good sample, this has more close to exponential decay characteristic. But here, the moderate and pure sample, if we try to fit with a function, we get that this decay matches with the stretch exponential function. So what is the stretch exponential function? This is the pure exponential function. But for stretch exponential function, we have a beta parameter here. So, okay, we are trying to fit and get some parameters. Beta is, oh, sorry, I forget to write here. Beta is almost a half. Beta is almost a half. And then tau, the parameter tau here is very small in microseconds. And then the second part, tau in milliseconds. So this means there are very, very fast relaxation process here. So we interpret that this related with the transport, multiple trapping process in the surface before the electron goes through the TiO2 layer. So we get clear understanding here how the surface states affects the transient photovoltaic decay characteristics. And the last part maybe about the passivation. The passivation, so to improve or to neutralize these defect states, there are many reports about the passivation treatment, but there are no so much studies how this passivation treatment can affect the charge transport and charge extraction in solar cell. So there is a bigger question here, how the passivation molecules or passivation treatment can affect the charge carrier electron or hole transport and extraction. So this is a simple treatment. We add trifluoroacetic acid, organofluorine molecules to antisolvent during the preparations. So this can remove some weakly bound anion or cation, or so we hope it can compensate this some vacant defects. And this is without passivation molecules. The solar cell quickly degraded only in 4 days. Yeah, this is the first day measurements, and this is in the measurement in the 4th day. So the characteristics quite quickly degraded. But if we add passivation molecule up to 5%, there is no so much degradation. And we also see some big difference in GV characteristics, and maybe we can see clear, more simple here. When we add passivation molecules, we can see the variations. The variations become much smaller, particularly this at 5% of organic passivation molecules. And efficiency also much, the variation much smaller. So this means improve reproducibility and stability of the device. But what happened here, maybe I skip here. This is the IMVS results. I just want to show that for the best sample, we get ideal semicircle here. But the other, we have a suppressed semicircle. So what happened here? We again look at the characteristic by doing TPV measurements, but now we apply DC light bias. We add light DC source here, shine the cells together with nanosecond laser here. So this means that we measure, we can by adjusting the LED intensity, we change the condition of the cell from at various level of operating level. Of course, this is a sample of the raw data. This is when there is no DC light bias. The same decay like I presented before. And with this DC light bias, the response, of course, becomes smaller. Yeah, becomes smaller because there is a change in the operating voltage of the solar cell. And this is the result. And we can see the variation of decay characteristic depend on the light, the LED intensity. And this is in the logarithmic scale. We can see here, there is a big difference of decay characteristic. This is without passivation molecule, this with passivation molecules. But there is a big question here. There is a delay, rise, decay here. So, okay. Because the time is over now, I just want to emphasize that the rise decay here related with the downward band bending due to surface defect states. So this result from our works, and this is our summary, that simple and facile perovskite layer preparation is very interesting and with many application, but there is some disadvantage. We have to carefully do the preparation to reduce the surface defect states in these materials. Maybe, yeah, okay. Thank you very much.
Very much. So it's time for the questions and comments from the audience. Yes, please.
Yes, thanks for this very nice talk. Just one question. So you have been discussing also this impact of this morphology, yeah? And like on slide 22 or so, 23. So the question is, how did you came to these morphologies? So this is like just cartoonistic images, or you was using like fate field modeling?
The morphology characterized by electron microscopy, spectroscopy. So we can, I don't show here, but in our paper we show the image of detail of the difference in image morphology.
Other questions? Yes, please.
Okay, thank you. So last week I joined the symposium for the perovskite solar cells and heard the latest trend from the Miyasaka and Hayase, and then people stopped using titanium oxide. This is using because it's not necessary. They found this is historically used for the dye sensitized solar cells, but actually this they found out is not needed. It's rather band structure is come to be rather worse, so that instead, as you mentioned the very last, some layer, monolayer, very thin layer, organic layer is used for the to control the band bending structures, but very simple and only perovskite and nothing else type of structures are. You can try once, but they said the titanium oxide is not much.
Okay, yeah, there's
latest data.
There's some trends recently to
It's very recent.
because there are some report that without one of transport layer it can also produce good performance. Okay, yeah, thank you very much for the information.
Any further questions? Okay, if not, then let's thank the speaker again, and also thank all the other speakers in this session.
Okay, thank you for all of three presenters and our moderator. Now I would like to request again to all the three presenter, Professor Alex. Sorry, I would like to request to all the three presenter, Professor Takashi Kuroda, Professor Inana Kabakova, and Professor Hamati Daya to come forward to retrieve the souvenir, and also our moderator, Professor Min Kyoseo, to hand the souvenir. Now let's continue to the group photos to all moderators and presenter. Thank you once again to all three presenters and our moderator. Please give a round of applause. Okay, now before we move to our lunch sections, I would like to invite our sponsor for the ISMOA event. I would like to invite Niche Lab to present short presentations about their company. For Niche Labs, time is yours.
Okay, good afternoon once again. My name is Anggi. I'm the CEO of Nix Labs. So I'll keep this brief and to the point. So in recent years, integrated photonics has advanced in incredible path, and from cutting edge research into industrial applications. At Nix Lab, we are proud to play a part in this progress by delivering control and driver systems that help turn photonic concepts into working systems. So now I would like to share some real-world use cases by our customers that highlight how our product and how our technology impact their applications in experiments. Okay. So we begin with a breakthrough from IST and the University of Tokyo, where researchers developed an integrated photonic accelerator of deep learning workloads. So what's impressive here is their use of optical matrix multiplication to reduce energy consumption in inference tasks, a critical factor for scalable AI infrastructure. Our Expo system here were used to drive and control the photonic components with high speed, high resolution analog voltages. And this allowed precise tuning of the optical pathways, enabling real-time configurability of the system. The result is the scalable photonic chip that significantly improves power efficiency of deep learning inference, this is the key milestone in AI industry. Next, we head to space, or rather the tools that help us study it. These collaborations between NASA Jet Propulsion Laboratory, Caltech, and also Observatory in France presents a highly stable photonic spectrograph optimized for detecting exoplanets via radial velocity measurement. The precision required in the setup is immense. Nanometer level optical path stability. And our Expo system provided stable, low noise bias control to the integrated photonic circuits, ensuring minimal drift and also repeatable performance over long durations. This project showcases how photonics, backed by precision of our technology, can advance the search of life beyond the Earth. So beyond academic research, our technology is also enabling innovation in industry, especially in the field of photonic wafer testing. Semiconductor foundries are beginning to integrate photonic chip testing right at their wafer level, and Nix Lab plays critical role in this process. So in here, our system is embedded into custom probe cards used to electrically interface with photonic chips while they are still on the wafer. And this allows engineers to perform high throughput testing, tuning, and validation of thousands of photonics components before they are diced and packaged. So the compact form factor, programmability, and high channel count of our solutions make it ideal for modern wafer probers handling the integrated photonics. And we are proud to support semiconductor manufacturing in accelerating this procedure. Okay, so back to academic. Between some of the Hong Kong University and also Tianjin University focuses on improving data center communication. This paper introduces a novel architecture for high capacity fiber optic transceivers using integrated photonics. Their system pushes the limits throughput while reducing complexity and also footprint. And NixLab XDEC here played a key role in the dynamic configurations of photonic modulators and filters, enabling real-time tuning and calibrations. So this is essential for optimizing signal integrity across the channel. So next, this work is from IIT Madras, focuses on photonic radio frequency filters, a key technology for the next generations of wireless communications, and including 5G and beyond. So the team implemented a tunable RF filter using integrated photonics, dynamic spectrum access. And here our XDEC system was used to bias the phase shifters and to enable elements with high precision. This enable agile filtering and on-the-fly reconfigurations. This is crucial for real-time adaptive radio frequency front ends in dense wireless environments. So in this innovative study, researchers from Beijing University proposed a photonic arithmetic processor, a step toward all optical computing. The system uses a programmable mesh of interferometers to perform fundamental operations like addition and multiplication using light rather than electrons. And our XDEC here provided the fine-grained voltage control needed to dynamically configure the informatic paths, enabling functional reprogramming of the processor during operations. These works represent a significant move towards scalable, high-speed, low-energy photonic computing systems with broad implications for data-intensive workloads and AI. And lastly, this research from TU Eindhoven focuses on integrated photonics for LiDAR systems, a critical component in autonomous vehicle. So the team developed a photonic beam steering solution with high speed, low power, and compact footprint, improving the resolution scalability of LiDAR units. And NixLab XDEC here played a vital role in controlling the phase shifters and tuning elements, ensuring precise beam positioning and repeatable scanning performance. So with compact and tunable photonic solution like this, the path toward affordable and high performance LiDAR become, more achievable. Okay, so this is our company. So we are headquartered in United States. Okay, so before we are in Australia before, but now we have already moved our headquarters to Palo Alto and also Rochester, and we also have manufacturing facility in Indonesia, in Bandung, Indonesia, and Okay, so across these groundbreaking researchers, a clear theme emerges, which is photonics system has expanded into a new domain. And then in all this effort, reliable high solutions and programmable systems is essential. And this is where Next Lab comes in. And then we are really happy if all of you would like to have a collaborate with us. Thank you.
Thank you once again from Niche Labs. Now we will continue to our lunch sections. Our lunch sections will be with the durations for like 40 minutes. So we will be gonna back at 1:30. So please for all the participants here can do their lunch, and then don't forget to come at 1:30 and don't be late because we will continue with our new session. Thank you. And also, I would like to inform once again for the participants that want to join the excursion tomorrow, please be sign the papers in front. And because we want the list who want to join the excursions tomorrow. Thank you.
Power supply, multimeter, and oscilloscope are used for the standard electrical test. In a typical industry in the lab, we need multiple of these devices, but the problem is they have excessive power, limited output, expensive, bulky, cumbersome, and inconvenient. And the solution is XDAC, a sophisticated source measurement unit for low power applications from simple electronic circuits to complex photonic integrated circuits. We also offer a variety of channel options ranging from 8 to 40, 80, and 120. We are also beginning to develop our product into a chip scale version with a wide range of imaginable applications. Start from sensing and instrumentation, telecommunications, machine learning, and quantum computing. If you're interested, we also provide a live demo unit and a GUI simulator to give you a better understanding of our product. You can find more information on our website. We are waiting for you. Together, we are unlocking the power of light.
At FLIR, we asked a simple question. Why choose between what you see and what you don't? For years, we've relied on visible light to define structure. But structure alone doesn't tell the full story. Infrared reveals transformation, heat radiating from machinery, stress forming in materials, energy shifting. Two perspectives have always been separate until now. Introducing FLIR Mix, the first imaging system to capture high-speed visible light and the revealing power of infrared together in perfect sync. Every pixel aligned in time and space, every moment captured with absolute precision. Now, researchers and engineers can see structure and transformation at the same time, in real time, without the need to piece together separate data sets. FLIR Mix doesn't just show you the moment, it shows you what makes the moment happen. With up to 1 second, every reaction in temperature, every hidden change giving you the power to analyze change as it unfolds. No more wasted hours aligning data streams. No more uncertainty, just faster, more accurate insights, so you can focus on results. With FLIR Research Studio, visible and infrared data are captured, processed, and analyzed in one system. Plus integration, one workflow, one synchronized data set for scientists, engineers, and researchers across material science, electronics testing, renewable energy, and high-speed dynamics. Patterns once missed, now visible. Failures before they happen, now preventable. The future of imaging, now here. For researchers, for engineers, for visionaries. Because when two worlds come together, you don't just see more, you see everything. FLIR Mix, or no more.
If you're designing photonic systems, ANSYS Lumerical lights the way. From virtual reality to display technology, from auto sensors to smartphone cameras, from laser design to quantum computing, from 5G to data centers, ANSYS Lumerical is a world leader in photonic simulation. Product development deadlines for nearly 20 years, collaborating with leading third-party tool providers to create new workflows, building better photonic systems on time, on spec, and with higher performance. Referenced in over 15,000 scientific papers and patents, Lumerical has been run in close to 30 million simulations by roughly 50,000 different users, by 90% of the leading companies in the world, and by all IT index companies. If you're designing photonic systems at the component and circuit levels, ANSYS Lumerical is a complete cloud-ready simulation solution. It's easy to learn and deploy, constantly innovating new solutions and techniques. For reliability and accuracy, there's only one true leader in light, ANSYS Numerical.
Are used for the standard electrical test. In a typical industry in the lab, we need multiple of these devices, but the problem is they have excessive power, limited output, expensive, bulky, cumbersome, and inconvenient. And the solution is XDAC, a sophisticated source measurement unit for low power applications from simple electronic circuits to complex photonic integrated circuits. We also offer a variety of channel options ranging from 8 to 40, 80, and 120. We are also beginning to develop our product into a chip scale version with a wide range of imaginable applications. Start from sensing and instrumentation, telecommunications, machine learning, and quantum computing. If you're interested, we also provide a live demo unit and a GUI simulator to give you a better understanding of our product. You can find more information on our website. We are waiting for you. Together, we are unlocking the power of light.
If you're designing photonic systems, ANSYS Numerical lights the way. From virtual reality to display technology, from auto sensors to smartphone cameras, from laser design to quantum 5G centers, ANSYS Numerical is a world leader in photonic simulation.
Good afternoon, welcome back, everyone. Let us now begin our third session. For the session, I would like to invite Professor Alexander Iskander, who will serve as the moderator. Please welcome Professor Alexander Iskander. The time and stage is yours.
Thank you, everybody. Hello, Didit. Are you on?
Hello, Alex. Good afternoon.
Okay.
Can you hear me?
Yes, we can hear you. Thank you. So before we start with our Meoncha lecture, I want to say, please bear me 5 minutes to introduce the Meoncha lecture. So, the late Professor Meoncha was probably a teacher for most of us in optics community. He's not only our teacher, he was also our mentor, our friend, and he was also, next please. Okay, he was also a person that we look up to. This is a photo of him when he was working in Japan, doing a short visit in 1970s, I think. And this is 2019. You can see that he's still working. This was probably, he was 86 years old. And a sad note, the right-hand photo was taken probably a week before he passed away. So for us, Prof. Chia was like our godfather of optics. And he was here to start the ISMOA meeting conferences all the way back to 2001, the first ISMOA. And he always attended ISMOA and giving support to everybody attending ISMOA, including the last ISMOA 2019. You can see he was talking to the youngest ever ISMOA participant, a high school student, giving a support, giving motivation. He was our idol. And back in 2010, some of us, Prof. Shah again initiated that some of us created our Indonesian Optical Society. So we create this Indonesian Optical Society, and ISMOA is then led by the belongs to the Indonesian Optical Society. So because Prof. Chia has worked more than 50 years in science and he gave a lot of legacy to us, we would like to commemorate his legacy by creating this Meoncha lecture. This is the third Meoncha lecture, and this 2025 Meoncha lecture will be delivered by Dr. Didit Yudhistira from IMEC, Belgium. He is a principal member of the technical staff in silicon photonics integration. Dr. Didit Yudhistira received his PhD degree from Institute of Photonic Sciences, ICFO, in Barcelona. And then he did a few postdoctoral research in France, and also he was a research fellow at RMIT, Melbourne. And then after that, did join IMEC in 2017 up until now as first as a senior product engineer, and now he is a principal member of technical. Did share his results, his latest results on nano laser. So the floor is yours.
Thank you, Alex. Thank you for introductions. I'm not sure whether my screen is already on the display over there. Oh, all right. So first of all, I'd like to thank again personally to Pak Alex and also the ISMOA committees for inviting me to the ISMOA right now to give my own lecture. Is a privilege. It's also honor for me for the opportunity. Actually, I like to join the ISMOA personally, to be there in Bali. I've been to Bali myself. It's got same on me. And actually, this is my third ISMOA. So the first one actually back in 2001, indeed, the very first ISMOA when I was still a student. But yeah, this is the third one. Time flies. It's already like 15 ISMOA. That's really indeed a legacy that actually our teacher Professor Chia, or what we call him as a Pak Chia, legacy to actually to bring optics to Indonesia community locally and also internationally to the world, at least to participate on that. So indeed, for this opportunity, I'll give a lecture about the nano-rich laser. But before I dive into the topic, maybe I can already share my screen. Do you have my screen over there?
Yes, we have.
All right.
Just need to put it slideshow.
Yeah. Then I use my pointer. So as already Alex introduced early on, that currently I'm working at IMEC in Belgium as the PMTS, principal member of technical staff, leading on the second photonic integrations. So basically, nano-rich gallium arsenide laser is one of the topics that I'm involved as a project at IMEC, because I'm also involved in a couple of projects in parallel. And now it's privilege from my side to share with you our recent results on the topic of nano-rich laser. But before we dive into the topic itself, maybe I will spend maybe like 10 or 15 minutes. Firstly, to share with you a memory of late Professor or Pak Chia from my personal experience, and also maybe I also share a bit or introduce you what IMEC is. Then I will go to the topic of nano-rich. So yeah. So whenever we talk about ISMOA, so ISMOA is International Symposium. Actually, I always think MO is my own from the Pak Chia's name. There's always an anecdote. So every time we think of ISMOA, we always think of, at least for me, first is the Department of Physics. As you can see on the left-hand side, a beautiful building of the Fisika ITB, Institute Technology of Bandung, over there, and of course the Pak Chia himself as the initiator of the ISMOA, and also I believe is also co-founder of ISMOA. So why these two always pop out on my head? because on the left-hand side, the building of Department of Physics, this is actually an image or picture of the very infamous 1201 lecture room. This is where the workshop of the first ISMOA was held, where I was a student participating to the workshop. And then, of course, Pak Chia, as already mentioned, that the initiator of ISMOA and also the co-founder. Pak Chia also a teacher. Teacher, as already Pak Alex mentioned, not only a teacher, but also a mentor, and also indeed persons who we always look up to. So I was lucky enough, actually, to be one of the Pak Chia student. I remember I was looking for the final project for my undergrad, to completion for my undergrad degree. So before actually I joined physics, I want to be a theoretical physicist at that time, before I know about the field of optics, right? So, but then I changed my mind. Then I joined Pak Chia team, and actually Pak Chia is the one who introduced me to the world of optics. At that time, it's always called it as optic or integrated optics, but now is people always call it as a photonics. And I remember when I was busy with my final project, usually, you know, in Indonesia, when you have like a big gathering, meeting your family, always your family member asking about, okay, what are you doing right now? You're already almost in your final year of your study, and what's topic that you're working on? And I said, okay, actually, I'm working on optics, right? I'm so proud saying that optics. But of course, the average my family member has no clue what optics is, right? So the kind of like feedback that I receive from them, okay, optics. So you're gonna be working at Opticsys, because I think Opticsys is one of the a brand, a store in Indonesia selling glasses. Yeah, of course, average Indonesian at that time, maybe back then, is not really familiar with the field of optics. They just only know optics like glasses and so on. But then, yeah, Pak Chia introduced me to the world of optics, integrated optics, waveguide, and so on. And there is one thing that I like to share for this particular moment, something that really shaped or always that I keep as a principle of my life. You know, as Pak Chia student, I need to take all the Pak Chia's courses, right? And not only the compulsory one, but also the couple of optional courses that Pak Chia gave. I don't remember the name of the course, but I do remember this one. I think for those who are in the field of photonics or similar to the field of photonics, you are well. You know very well about the Helmholtz equation, right? That's what I can put over there. So the Helmholtz equations is what we can see here is indeed a cornerstone in wave theory. And the Helmholtz equations solving problems like in acoustics, electromagnetisms, even fluid dynamics. So I remember in that course, Pak Chia asked students, solve these equations. I remember, okay, I was asked by Chia to come to the front, to the board, and asked me to solve this Helmholtz equation, because he knew that I already familiar with Helmholtz equation and how to solve it. But there is one thing that I forgot actually. I know I remember how to solve it, but there is one thing that's pretty important. This is something that really shaped my understanding not only of physics, but also life itself. Because if you just solve Helmholtz equations, there will be like infinite solutions to Helmholtz equations solution if you don't introduce or impose boundary conditions, right? So you can have like a infinite solution, if you don't introduce boundary condition. That's one thing that I learned from Pak Chia. Don't forget boundary conditions. So, of course, for waveguide, you have boundary condition like I learned later on there are two kind of boundary conditions like Dirichlet or Newman boundary conditions. But for this one, yeah, the boundary conditions not only helping you to solve this equation, but also for life, for career path, relationships, and also technical specs that I've been working here at IMEC. We are talking about specs, upper limit and lower limit. That's basically boundary conditions. And that's actually helps to create clarity. So I already mentioned that start with infinite possibilities, solutions always valid in unbounded space, right? But applying boundary conditions, so you define your constraints and also you define limitation, not in the negative way, right? But for the life, you always need to kind of bound it into something. Maybe your dream, you want to be someone, you want to be something. So that would be your boundary conditions that you need to apply to get very useful or meaningful what you want to be in your life. And then once infinite possibility, that will converge to the clarity with the boundary conditions. So you can see this for unbounded solution of the Helmholtz. You can have like in this illustration, you have like waves on the oceans that can be different kind of patterns, like really like chaotic and so on. Of course, it can be beautiful, but yeah, it's difficult to kind of grasp what kind of wave if you don't have like a boundary condition. Of course, in ocean, there's always boundary condition itself, which is the earth with everything in it. But I think you get what I mean. So with respect to optical waveguides, you can see here a nice illustration of the optical waveguide. Like an artist illustration doesn't look like this in real life, I can tell you. And then here, with the boundary condition, we can get the standing wave, number of modes that are guided in the waveguide. Let's say 2-dimensional waveguide, 3-dimensional waveguide, certain polarization, and so on, right? So but actually, what Pak Chia thought, at least to me, with respect to boundary conditions, that actually boundary conditions do not restrict you, but it's actually help you, guide you to focus, makes the problems solvable, and then leads us down structured path of discovery. So boundary conditions are the key to finding a relevant solution. So the keywords here is relevant. So that's something that I learned from Pak Chia that I really deeply, actually, shaping deeply to be who I am right now, because of boundary conditions, right? So then, how is it actually impacting your life and work? So for the career path, so with the boundary conditions, your dream, so you're bound by your skills, patience, and also maybe industry demands. So that can actually form a clear path what you want to be, your dream, right? For the relationship, so it's flourished through personal values, respect. I'm a student, and there's a docent or teacher or lecturer. Then you need to act as a student. You know your boundary, right? Then can also help you with the good communications, human to human interaction, and so on. And also with for my relevant work, in this case, CMOS fabrications, that actually define as always the boundary conditions. What is your feature size? What is your spec? What's this critical dimension here and so on, right? That's in order what? In order to fabricate, to produce a reliable chip production. So yeah, then of course for the navigating your career, so with the boundary conditions, here I think of boundary condition is my dream. So I can choose whatever I want to be, but I need to choose, means that I have boundary conditions. So then your career becomes clear because you set the boundary condition that guide your path. So exploring directions, your interest in educations that can show you number of options that will be available for you, You define your constraint, your skill, job market. You know what the job market is looking for. Maybe it's about AI, photonics, and so on, so on. And that can converge path, right? So decision help you find your unique career. I'm talking maybe to the younger audience in the room. That really find your body conditions, meaning find your dream. That's what the key learning, of course, among others that I learned a lot from Professor Chia or Pak Chia. So for myself, yeah, I always want to be working in R&D. That's always my dream. I joined physics, the Department of Physics. At that time, always people say, okay, you join the Department of Physics, or you want to be a lecturer. I don't say, well, of course, if I'm good enough, I can be a lecturer. But that's not my passion. It's not my dream. It's not my boundary conditions. So I look right after I got the bachelor degree, as what Pak Alex says. So I got the PhD, but then I spent quite some time in academia until I moved away from academia and joined industry. Actually, before I joined IMEC, I joined Infineon in a production fab, producing a real chip that, well, chip means real means that it's really producing chips for the customer. And then I was there for almost 1.5 or 2 years in Malaysia before I joined IMEC, what you can see over here. So that's what I hope it's not that long that I kind of like share with you my really life experience or key life lessons that I learned from Pak Chia, and I really appreciate that. I always think of Pak Chia still to be as my teacher, even though he's not among us anymore. And then yeah, one of the legacy of Pak Chia, apart from ISMOA, is his student. So I'm so proud of being one of his students. And then yeah, so then for the next section of my lecture, I'd like to introduce you a bit about IMEC. So IMEC, so what IMEC, IMEC is basically, well, not basically, it stands for Inter-University Microelectronic Centrum, or Inter-University Microelectronic Center, headquartered in Belgium, in Leuven, where I'm at. And actually, IMEC is more than just another R&D hub. So here I will share with you a short video. I hope it doesn't take long. If the video can start, yeah.
There is no sound.
Oh, there's no sound.
You have
how
to
can I
share
the
sound.
How to share the sound? Yeah.
Go
Oh yeah,
to
yeah. This one.
Okay.
Is it okay? Can you
Not
hear?
yet. No, not yet.
Oh.
There is a button, a share button, and then not only sharing video, but share sound.
Yeah, this is what I. Oh, okay, cool. Yeah.
Innovative minds.
Is it okay now?
Okay, excellent. Yep.
Yeah,
but
perfect.
sets them. Committed to pushing the chip roadmap way beyond its limits. To make chips smaller, faster, more affordable, and more sustainable. We enable breakthroughs through talent and gather the entire microchip industry in our world-class clean rooms and labs. We accelerate the transfer of technology from the research lab to the market by combining chip expertise and application knowledge with data and AI to touch every corner of society, from healthcare to energy, from automotive to connectivity, and always with the planet in mind. We're defining the future, for a better life through technology. Together.
All right, so that's a short glimpse of what IMEC is. Again, this is like a corporate video that I like to share with you, at least to introduce you. Maybe some of you do not know what IMEC and what IMEC is all about. So I hope that the short video can and at least introduce you what IMEC has been working on, and then and really what IMEC can actually have what is called as shape the future of society. So IMEC is established or founded back in 1984, so it's already almost more than 40 years. So what you can see here is already been pioneering this semiconductor roadmap, and IMEC's microchips technology, because we've been working closely with a couple of partners that really give an impact directly to the human society with the technology, like Microsoft, Intel, Apple, you name it. So smartphone in the every smartphone there are also chips that where IMEC also contributes to the development of the chip through the partner. So what makes IMEC a semiconductor lab of the world? Because it's considered like a three parts. So it's skilled people. We do have we can say a world-class infrastructure, and also the global ecosystem. So for the skilled people, actually IMEC has more than over 6,000 employees across the globe, and coming from 100 nationalities. But they, what I can share with you that among these 6,000 employees, I can tell you that only 4 of Indonesians working for IMEC. Well, IMEC maybe can grow in the future after I introduce IMEC to you, to young researcher or young students in the room. So, so with the global ecosystems, we've got over 600 partners, so working together. So system partners, suppliers, equipment suppliers. You can see on the video, there's SML, there's applied materials, KLA, and so on, and design house like a Lucida for the photonics, IDM foundries, and Fabless, and so on, right? So we really work with the partners across the globe from different kind of like sector. So so now we do have 2 clean rooms. You can see here with the 12,000 meter square clean room. So there are two clean rooms, like 2 big clean rooms. What we call as Fab 1 for 200 millimeter, and Fab 2 and 3 for 300 millimeter. And then we got over 250 tools. And then as a fab is running 24/7. So really it's always running. So there's always something that is being processed, in particular in this building. So now we also building a new fab, what we call a Fab 4. So there's another 6,000 meter square clean expansion with 2.5 billion investment. So it's currently in progress. This is another video. Maybe I will not go to that video because of the time. So we got the global collaborations with more than 2,200 universities, and then from the collaborations with universities, we defined a long-term research pipeline that will be implemented from academic insight into industrial innovation. That's how what the IMEC model really is. Really work together with university. We are not competing with university. We are also not competing with the in the industry. We're not TSMC and so on, right? But we really kind of like being a hub to kind of bring what universities kind of like achievement or bleeding edge kind of technology, do prototyping at IMEC, and then the partners will benefit from that, which is industrial partner. So yeah, semiconductors are the core of the deep tech innovation. If you remember back in the COVID time, there's a chip shortages, and then people start looking, where is my chip and so on. That actually all produced in fab, semiconductor fab, what we call it as a CMOS fab. So yeah, what IMEC offers. So first R&D collaboration, and second one innovations through the service and solution, and lastly is a venturing startup. So we also do have startups and funds. So for the R&D, with the state-of-the-art infrastructure, with the high recent like a deep with the EUV lithography that is produced by ASML, even that lithography is not yet in the market or in used by TSMC, for instance, we are the first one who has a chance opportunity to use that lithography tool. So with a large international network, deep technology knowledge, and so on, that's actually how the R&D collaborations that IMEC is going on. As already mentioned to you before, this is the bird view of the IMEC campus here in Leuven, Belgium. So this is IMEC Tower where the office people are sitting. And then you can see here, this is the 200 millimeter fab. This is the very first fab. Fab is a clean room where we fabricate the wafer. So 200 millimeter means that the size of the wafer in diameter is 200 millimeter. And then there is another one which is 300 millimeter, which is the larger wafer. And usually 300 millimeter is the one that you use to run R&D, whereas 200 millimeter is more measure, where you do kind of like low volume manufacturing kind of stuff, right? So innovations. So what is innovations? We through the what we call as IMEC link. So we provide the packaging, testing, and qualification to the partner, and we do prototyping like 50 chips, and then from this one, then the partner can be able to do like a mass production up to millions. But we don't do this. This is actually is done by partners like Samsung, TSMC, Global Foundry, and so on. So with the startup, so they cover startup. So at IMEC, IMEC also offers startup to, if you do have some ideas, then you can then pinch your ideas to get funding, internal funding. Then you can establish a new startup. So there's like an ecosystem also at IMEC to nurture startup to be produced. So here for the startup prototyping with a low volume pilot production and so on, right? So this is more or less the, once you have a startup, then you have access to the clean room, then you can do kind of like low volume pilot productions. You can start kind of like having the like a product. So yeah, this is where IMEC is. This is the Belgium, and on top of that is the Netherlands. It's not there. So this is Belgium, and this is Leuven. So over there is Brussels. If you've been to Belgium, that is not far. So it just only takes 20 minutes or so by train to get to go to Leuven from Brussels. So within Belgium, there are a couple of R&D groups. Flemish is part of Belgium, who speak Dutch. So here, there's a couple of like a Ghent University. We know that with Ghent University, the couple of universities where this IMEC also there. And then across the globe, you can see here, we do have a couple of R&D in the US, a couple of them from West to East Coast. The recent one is in Spain, Malaga, which is really nice site that's being developed. And then also a couple of sites, but it's not this only representative in Asia. That would be nice if we do have also somewhere in Indonesia, but we don't know. So here, in terms of the growth from the 1984, you can see that you can really see that there's exponential growth in revenue. So the white one actually money that the IMEC received from the local government, so Flemish government in this case. So it's not that much now because compared to the what revenue that we receive from the industry. So this is really unique kind of like R&D, right? Because all the competitors come to IMEC like TSMC, Global Foundry, Intel, Apple, and so on. They are all competitors in terms of the product, but they come to IMEC for R&D kind of collaboration. Then, yeah, so IMEC as a world-leading R&D hub. So IMEC aspire to achieve the impossible, that aiming for disruptive innovations. And IMEC maximize social impact by creating a smart, sustainable solution. What to enhance quality of life? So this is what IMEC is. So IMEC, we shape the future, something like that. So yeah, there are a couple of activities. I just simply mentioned to you a couple of them, and there is one which is related to the topic that I'm gonna start with. Sorry for the quite long introduction, perhaps. So within IMEC, so there are, I already mentioned to you, there are a couple of activities. There's a memory, CMOS, FET, transistor, RF, and so on. But I myself is part of optical I/O team. Optical I/O means the I/O means interconnect or input output, right? So in this case, we are developing optical devices, photonic devices that are relevant to the interconnect kind of applications. In this case, two kind of wavelengths, 1310, C-band and O-band, 1550, right? So these are all the state of the arts, what we call it as IMEC SIP. SIP is the second photonic platforms. There are all well established that the partner can already be able to access. So these are not kind of a new development. So this kind of always is more a bit more a mature kind of devices. You can see here there's a ring modulator over there, and there is a electro-absorption modulator, germanium silicon. There is a Mach Zehnder. There's a photodetector, and of course there's the waveguide. In this case, not only silicon waveguide or SOI, silicon on SOI, but also there's a silicon nitride waveguide with the quite reasonably good optical loss, 0.2 to 0.5 dB per centimeter. And then now we can go directly to the topic itself, and then how IMEC help to kind of like contributes to the what this issue that we are having right now. So now I'm introducing you to the AI stuff, right? I think you know about AI. I think you've been also using ChatGPT, Gemini, and so on. So you can see here from the curve, right? So the y-axis is a compute operations, and then the x-axis is the timeline. So you can see here from 50 to 2010 is almost linear in terms of the compute operations. So you will know what happens after 2010. It's the slope is kind of like jump. So it's doubling every 3 months in terms of the compute operation. So what happened actually? That's because not only because something happens with the, like for instance like a Zoom call right now, but also it's mostly it's like an AI driven kind of applications. That AI becomes a bottleneck by a data communication rather than by computer, because for the AI it uses GPU, like NVIDIA, they are the one the cornerstone for the GPU producer. They can keep on improving their GPU and also CPU from AMD or Intel. But the thing is, in terms of interconnect, so to connect from, if you're talking about the cloud computation, there's a rack to rack, right? So you're not going to be able to rely on the copper cable anymore, because of there is a gap here. You can see over there, there's a gap in terms of the bandwidth that the interconnection can offer. You'll not be able to keep up how the GPU and CPU performs. There's a huge gap over there if we still rely on the old technology based on copper, right? So at some point, there is a kind of like a trade-off, right? Here is an optical I/O power wall, and then we need to kind of like what is it, to, this is basically interconnect wall when we still use copper, so the performance is little decreasing with the distance. So with a short distance, if you are talking about connecting GPU to GPU, like in the motherboard, of course you're not going to do optical link for that. You still rely on the standard copper connection or whatever you have on motherboard, right? Because you can see a performance still high. But when you come to the distance, when you want to connect a rack, if you are familiar with the rack in the cloud compute center, there's like a bunch of racks, and each of the racks are connected usually through the optical fiber. That's where this optical interconnect plays role. So you can see here, if you're talking about the H bandwidth density times energy efficiency, and then here with the interconnect distance. So for this one, this can still be delivered by electrical kind of connection, but then when it comes to the distance more than 10 meter, then this is where the optical link is needed. So you can see here, this is the corresponding stuff, ethical things that actually in it, as already mentioned to you before, for the chip, you can still rely on the ethical interconnect, packaging and so on. But when you're talking about a cluster like a rack to rack, is where the optical interconnect is actually needed, and also for the cloud data center over there. So because you are relying on the cloud now, you rarely maybe with the photo, if you use Apple product, you have iCloud where you store all the photos. They actually all store in the cloud data center that requires then optical link, optical interconnect. So in order, because the demand on because I already mentioned to you, there's like a gap between the CPU GPU performance increase with respect to the interconnect bandwidth, and that which require optical interconnect. Now people trying to kind of improve what is already available in the market. So the one is with the pluggable. This is a pluggable transceiver optic. So this is you have the we have ASICs application specific IC. So this is your EIC, electrical integrated circuit, and you always have the optics sitting over there, right? This is like a very first. This is what maybe aware of that's already used or deployed in the data center. So it can provide like 100 up to 800 gigabits, and then we are trying. People have been trying, or in this case also, I've been trying to kind of like reducing the size. So by bringing optics closer to the EIC. So this is PIC, and of course the PIC is photon integrated circuit to EIC. So now it becomes kind of a co-package all together between EIC and PIC. But of course, there is something that is needed in order to be able to get to this point. Because before, all the transmitter, modulator, and even laser are sitting outside EIC, right? And then now we want to have everything on the same chip, what we call it as a co-package optic. So here, there's a transition over there from pluggable optics, which I already shared in the previous slide, down to the what they call it. This is from the light matter slide, Gen 5. So this is a 3D co-package optics with integrated lasers. So you can see here, these are all the components, right? So laser always somewhere outside the ASIC or EIC. They bring the optical component closer to EIC, but still laser is somewhere outside. And now when Gen 3, they already start to have like a disaggregated laser supply over there. But then if you are on the Gen 5, sorry. So that's where you really have everything all together, the laser, the PIC, the EIC all together in a single chip. That's like really holy grail to enable, to accommodate AI needs for the future, in the future. So let's have a look. What is the current status of the PIC, right? So the PIC, this is, again, I got it from the light matter, although I do have a couple of illustrations, but I think it's better to use a light matter. So this is a standard kind of like a really simplified PIC or silicon photonics. So what does the silicon photonic look like? Right, yeah, we have a photodetector to detect the light, convert the light from the information that the light brings into the electrical signal, vice versa, right? So there's a waveguide, of course, there's a link modulator to modulate, so to put the information into the light through the modulation, here through the ring modulator, and there's a splitter, and there's grating couplers, and this is one example from the our ISIP platform, like a waveguide and grating couplers. Grating couplers here is to actually, if you want to couple the light into the PIC. So there's a fiber actually over there hovering over there, that will then you'll be able to copy the light, that then the light will be kind of like do kind of interesting stuff on the PIC. So, but then here, as you can see, this based on silicon. It's not bare silicon, it's not a bulk silicon, but it's SOI, silicon on insulator. So there is a silicon where you define all the waveguides, everything else, and there is a box which is a buried oxide. So this is like 2 micron, and then you have a silicon substrate, so SOI. So it's not a bare silicon, it's SOI silicon sitting on top of insulator, supported by the silicon substrate. But all the processes, all the fabrication are actually enabled by CMOS processing. But we still don't have laser here, right? So then how can then we be able to integrate laser into the silicon photonics? So I, I put an illustration here. This is a standard helium neon laser that I used this laser when I was doing my bachelor study, working on prism coupling setup. So that's why I use this one. So you're not gonna, well, in terms of the scale, and then here, are you gonna put like this laser and directly put it onto the silicon, like so? Of course not, right? But then how then you're gonna put laser on silicon? So what is the, how you gonna actually, how you gonna be able to make a laser in the first place, right? So it's laser actually, right? So, well, silicon is good for everything, but not laser. That's always the trade-off in the world. Maybe the boundary condition that I already mentioned before. So we can see what is the really the limitation with the silicon. Why silicon is not good to produce light? That's a problem. Why? Because silicon doesn't have a direct band gap. So here I give you an illustration of the band gap, a band diagram. Here on the left-hand side is for 3,5 materials. If you know in the table, 3, group 3 and 5, like gallium and arsenic, and indium and phosphine. So it's part 3,5, gallium arsenide, indium phosphide. So for these 3,5 matter, you have a direct band gap where you really have, direct band gap means that then when the excited electrons to the conduction band, and then from the electron back to the valence band, then it will emit photon. So direct recombination. So after they combine, then it always emit photon. But for the silicon, as it doesn't have direct band gap, it needs to get through phonon. Phonon here, well, if you know what acoustic, phononic crystal and so on, but phonon is means heat. Meaning that you try to somehow be able to go to the conduction band, but in order to go back to the valence, it needs kind of like, it produces heat, but heat is killer. So we don't want heat at all in silicon photonic application. So heat is killer. You don't want to do that, right? So the silicon is not good for producing light. 3,5 is, right? So what can we do? So actually, there has already been kind of like different kind of integration approaches, how to bring 3,5 onto silicon, right? So here I mentioned 3 of them, like a 3 main approaches, incorporating 3,5 into silicon to get on-chip laser. So one is hybrid integrations, and the second was heterogeneous integration, and the last one is monolithic integrations. And gallium arsenide nano-rich laser that I'm gonna share with you soon is actually monolithic integrations, right? So basically hybrid integration is like you already have all the laser outside and you put it into the chip, right? So one of the technique here is a microtransfer printing. Now it's actually really promoted or really heavily developed by team in the University of Ghent. And the second heterogeneous integration basically is a wafer-to-wafer bonding. So you have SOI and you have 3,5 and then you bond it, right? So then you're gonna then the next step will be just patterning and so on and so on. And the last one is monolithic integration. So you want to grow, so you directly grow 3,5 epitaxial growth on silicon. And one technique that I mentioned here is called template assisted selective epitaxy, or TASE, which is actually introduced by IBM Zurich. So, but in terms of the PIC density, so you can see here in this illustration, so actually going from hybrid kind of like a temporary solution. We know that silicon can produce light. We know that 35 can produce light, and we know how to fabricate laser on 35, and we put it on the finished, almost well finished SOI silicon PIC, and then we put it right. It's like a microdistant printing. It's a hybrid integration. But heterogeneous integrations is the bonding, but the ultimate goal is actually monolithic integrations. So where we grow 35 directly on silicon, right? But the thing is, there's what is it? A challenge there. Not that easy to grow 35 crystal directly on silicon. Why? Because there's a lattice mismatch. There's another like how the world always, well, of course, kind of like really give a chance to human to find solution. So if you do directly grow 35 directly onto silicon due to the lattice mismatch, what happens? You can see here, there is defects. You can clearly see here what we call as a threading dislocation. This killer. So having this defect, even though you can produce light or laser, then your laser not gonna be survive. Maybe you can survive one day, but next day is already dead. Because that threading dislocation degrade laser output efficiency, because acting as non-radiative center, because basically it's like a scatterer. So if you have direct band gap, and then if you have a defect, then the actor will not go directly to the valence. It will go stop first at the defects, and then so it's killer basically, right? If you do directly grow 35 on silicon, then if you don't do anything else, then it will be killer. So then I'm gonna go through a bit different kind of monolithic integration approaches. So as already mentioned before, from the IBM, the second one is this is kind of recently, well, it's quite recent publication where they be able to grow 35 on SOI, but they grow it on the substrate of SOI with the groove over there. And of course, the one that we actually introducing here is nano-rich engineering, or what we call as NRE. How this actually, apart from this one, able to mitigate issue with the defects that actually comes from the lattice mismatch between 35 and silicon, right? So this all comes with the an engineering approach. So NRE is based on aspect ratio trapping of misfit defects. So on the defect, we try to trap. So then here, this is our silicon substrate, and then there's silicon dioxide over there. We are trapping all defects. We're confining them over here. This is aspect ratio trapping, meaning that the ratio between the height and the width need to be certain value, in this case 3, then to be able to confine all defects. So here, if you are looking at the cross-section view, so all the defects is confined over there, and here where all the active devices or stack really is. So then we have almost defect-free. It's not completely free, but at least in terms of density is much less, which is really useful for the laser application. And there are different techniques for epitaxial growth, and one of them is MOVPE, metal organic vapor epitaxy, and there's also MVE, but the one that we use is MOVPE. So now I'm going to the topic itself, the gallium arsenide and non-rich. This is a recent publication, a recent result that we published in a Nature paper, where we are able. Yes.
You have 5 minutes, yeah? Okay, thank you.
Oh, okay, sorry. Then here for the laser itself, we have this is already published in a Nature journal, and then maybe I can go directly how we fabricate them. So this is start with the bare silicon. Then I think I can go directly to the. It's important that I can share with you how we fabricate them. So then basically this is a couple of process steps until we grow the laser, and then we not only we grow the laser, we also put a photodiode to allow us for the inline characterization. So here, this is the view of the one wafer with bunch of lasers in it, right? And then this is the cross-section view. So here, this is the nanoreach. So we connecting the nanoreach with the tungsten plug over there, with all the quantum wells, and then all the defects over there, right? And then this is almost like a end of the fabrications of nanoreach lasers, with all the defects confined thanks to the IRT process. So how does the nanolaser perform? So here, after we fabricated the laser, take one wafer and we dice it. So we take one side as a cavity, and then we as a mirror, right? And then we use the inline photodiode, also based on nanoreach structure, and then we characterize them with the external optical fiber, which combining with spectrum analyzer. That here you can see this is the IV or LII curve. So there is like a really clear, obvious signature of the lasing. There's like a threshold current over there, and then there's a spontaneous emission, and then there's stimulated emission, right? So when you're looking at the current itself, we are moving from the very low current until the above the threshold current. Then we can really see a strong peak that indicates the presence of the laser or lasing. This is done with a 1.4 millimeter. Then we, of course, we try, well, this is a zoom in of this image. So when you increase the current because of the heat, right? And there's a redshift over there. Then once we know that the laser works, then we do the wafer scale characterization. In this case, we are using the fiber hovering on top of the laser on this cavity, and then in combination of that, we also have an inline photodiode. So here, then by doing so, we are able to characterize in wafer scale our laser with different kind of design of experiments. In this case, for the length of 2 millimeter. So we observe 113 lasers, right? And then this is the corresponding location on the wafer, right? And then, of course, then we are able to kind of like get all the laser with different length, and then how that they perform a number of lasers counts per laser length per wafer. And of course, then here, this is key results. The lasing, in this case, we still have the laser operating at a 1020. It's not yet in the C-band O band. And then there is output power can go up to 1.75 milliwatt with a swap efficiency 0.5 watt per amp. And this is single mode lasing. So for the another wafer scale characterization, where we rely on the MMF multimode fiber hovering on the chip, and then we can then be able to get the spectra, and this is the movie where the laser output on the device is currently acting or performing. So here with the side mode suppressions, 25 dB with a linear slope of 13.6 picometer per milliamp. And in terms of the reliability, so we got the CW laser. We know that it performs. We also did do like a reliability study. So when the Nature paper was published, we mentioned that our laser can withstand up to 500 hours, right? And then this is if we benchmarking with the other monolithic integration approaches. So what we can see here, in terms of defect density is much less compared to the other publications. And then for the slope efficiency is quite high. It's 0.5 watt per amp compared to the others. But of course, at the moment, the wavelength is still not at the C or O band wavelength. So what are the next steps, right? So we know that we are able to have to demonstrate the wafer scale nanoreach laser. And first thing first, that we want to tackle reliability. So for this one, there is a follow-up study in which that we are able, actually the laser that we fabricated actually able to be alive. Lifetime is up to 1,000 hours. But of course, the current requirement for the industry is actually more than 20,000 hours. So at the moment, what is the bottleneck here? The bottleneck here is because we have a contact directly. We put a contact directly into the active region over there. That actually creates the charge crowding that lead to the reliability issue with the laser. So what we do next here is actually we move away the contact. We move the contact away from the active region by introducing the fin. So by having this one, then we are able to decouple the contact and the active region so that we can then be able to reduce the impact of the electrical crowding, which can impact on the lifetime of the laser. So the early development is already done. So here, this is the current state of the new nanorich, where we can then be able to realize fin. And also we recently got a patent for this concept, which is granted a few months ago. And then after we are able to tackle the contact for the reliability of the laser, for the lifetime of the laser, the next step will be, of course, to go beyond 125, 120, go to the O-band, right? So of course, at the end of the day, we want to apply this laser onto the O-band, C-band application. And then after that, then we can be able to integrate this nanorich laser onto the PIC. So how to integrate them is one way is through the additive coupler over there, right? It's quite old publications. And there are many other things where we can be able to integrate the nanorich laser into the PIC. So finally, acknowledgement. So this is not like a one single person's kind of like project. This is consists of many people, like epitaxy group people, and of course, Silicon Photonics. So me as one of them, and also working together with the University hand by hand. So at the end, the strong collaborations help to sustain the challenges. It's very essential. So this is also part of the IMEC. And then hopefully, I'm very sorry that I did have maybe pretty long introduction before I jump into the topic itself, but I hope that with a short glimpse of what nanorich laser is can help you to understand or aware of what we've been working on, and then how we are going to go beyond what we already achieved or published in the Nature paper. Thanks, Alex. Thanks all. I'm sorry for very long
Thank you.
introductions.
Thank you,
because I
Didit.
can see the people in the room.
Thank you for a beautiful memory of the late Prof. Shah, and also for the introduction to IMEC. We have very short time, perhaps one question from Dr. Andri Mahendra.
All right.
Hello, Mas Didit. Great to
Hello.
connect again after 12 years before we
Indeed,
connect
indeed.
in Sydney, in Australia. Yeah, thank you for the great talk. I just wondering about the nano rich laser that you built up, right? Yeah, yeah. So in the future or in the current implementation, how many laser that you can actually manufacture in the fab, and then how the future expected, like participation that can handle by that chip. So basically, that's the question that I would like to know. Thank you.
Thanks, Andre. It's really good to connect you again after 12 years. Indeed, thanks for the questions. The thing is that when we are talking about the wafer fabrication, right? So we are talking about the one wafer consists of many dies, and one die consists of many devices, right? So for this demonstration, we can even have for one wafer have more than like more than 1,000 lasers per wafer. But of course, not all the laser actually will be really useful, because here we do have a different length, we have different size of the nanorich, and so on, right? That at the end, of course, we're not gonna be making laser all of them in one wafer without having any PIC component in it, right? So at the end, for the possible deployment of this laser on the PIC, we're gonna really have ways how we only grow selectively on certain area where it is relevant, then to couple this laser into the optical waveguide on PIC. So, but of course, we still need to solve the issue with the contact, with the reliability, right? Because we still want to have this laser that can go more than 20K hours, which is actually the industrial requirement. That's also then linked to the heat that you mentioned. So the heat dissipation, right? So that's why here it's really important to have really good quality of 3-5 material, so that we don't want to kind of like inject power that much for the current to be useful for the light emission. So that actually comes to the how we're going to engineer. At the moment, we already have a good quality of epi, right, in terms of the, if you're looking at this. But then how you are really going to be really improve further how the current can be injected into the active region that will then lead to the lasing itself. That's can be either come from how the quantum well that we have over there be function. At the moment is quantum well, for the future maybe quantum dots, right? And that will have reduced the heat. As I mentioned to you, the heat is, it can be a killer, but can also be, there's always be a solution to mitigate heat. But of course, the first thing first is to improve the contacting to the laser to reduce the current requirement, and then we can reduce the heat.
Thank you.
Hopefully that my answers enough for you.
Yeah, thank you.
Thank you.
No worries.
Well, we are really running late. Did it? I'm sorry we cannot
sorry.
accept more question. So let's thank
so sorry
Didit
for that.
once again for a beautiful talk. And can you zoom in to me? Didit, we prepared a special certificate for you
Ah, okay. Wow.
as
My
a
second certificate.
2025 Meoncha lecturer, and also the organizing committee are happy to give you this memorabilia from 2025
I wish
ISMOA.
I wish I were there actually, Pak Alex, to really.
Yeah.
Wow, nice. Thank you very much.
When you come
Maybe
back home for a vacation, please come.
Maybe I can ask
Yeah.
David. David is there, right?
Yeah, David is here. I'll ask if he want to take it with him. Otherwise, we wait for you here in Indonesia.
Oh,
Okay.
that's great. That's great.
Thank you once again, Didit. Let's give a
Thank you,
applause,
Alex.
big
Thank you
applause to
all.
you.
Yeah.
Before I turn my chair to the Master of Ceremony, I just want to remind everybody, the oral presenter and also poster presenter, there will be best poster and best oral. Okay, so please do your best to get this presentation. Right. Please.
Okay, thank you, Professor Alex, for being our moderator. Now, as Professor Alex said, we will move to our presentation poster. As we do before, these presentations will be divided by two. There will be room A and room B. Room A is exactly right here, and then room B is on our right. So from room A, I would like to tell the participants number from OP09 until OP13. It will be in the room A, and then in the room B will be OP14 until OP18. So for those participants with those participant numbers can be moved now. And also I would like to remind that your presentations will be lasting 15 minutes, exactly 15 minutes. And if you pass that times, our moderator will be stop your presentations. Thank you. Okay, now let us start our presentation sessions in the room A, and I would like to invite our moderator for these presentations, Professor Inea Kabakova, to become our moderator. Thank you.
Thank you very much. You saw me this morning giving presentation and I will be chairing the session. So we are running with about 42 minutes delay from the schedule and we have 5 15-minute presentation. 2 first presentations will be online and then the 3 after that will be in person. And I ask please all the speakers keep on time, 15 minutes strict. And do we have a person showing timing? Okay, yes, excellent, excellent. So yes, for especially for our speakers online, yes, we have to be 15 minutes sharp, including questions. Well, it's my great pleasure to introduce the first speaker, Mohandis Shadik from National Research and Innovations Agency in Indonesia. Without further ado, Mohandis, please proceed with your talk. Mohandis, you're still muted. We can't hear you. If you can unmute yourself. We can see your slides though. Hello.
Okay. Can you hear me?
Yes, we can hear you now, and yeah, if you now share your slides with us, and then you can start.
Is it there yet, the
Yes.
slides?
Yes, Mohan, it's all good. Please carry on.
Okay, thank you for the introduction. Good afternoon, ladies and gentlemen. It is my pleasure to present our work, facial microwave synthesis of seaweed-derived carbon dots with pH-sensitive and 2-photon fluorescence properties. I'm Mohandis Siddiq from Research Center for Photonics, National Research and Innovation Agency, or BRAIN. Okay, carbon dots are small carbon nanoparticles with some form of surface passivation. Carbon dots or CDs are currently emerging as a class of promising fluorescence probe because of their low photo-bleaching, versatile surfaces, and excellent biocompatibility and environmental friendliness. So many of the precursors of carbon dots are from natural materials. So usually they can be synthesized with a very facile method. So here, one of the example is carbon dots from seaweed with synthesis with microwave techniques. So the synthesis of carbon dots from natural materials with microwave-based methods is economical and environmentally friendly. So the produced CDs have stronger luminescence and various colors. So here we use seaweed as the precursor, and then use the microwave. We heat it with a temperature of 120 degrees Celsius here with varying time. Here the morphology of carbon dots. Here with the microwave time is 15 minutes. And the average size of the carbon dot is 3.5 nanometers. And we can see here the XPS and FTIR of the carbon dots produced. You can see here that there is a lot of functional groups on the surface of the carbon dots from the XPS and the FTIR results here. It's there is carboxyl, hydroxyl, and amino functional groups here. And we measure the UV vis here. We can see that around 230 nanometers, there is pi star transitions from the core of the carbon dots, and the around 300 nanometers, there is n pi star transitions from the surface of the carbon dots here. And you can see the photoluminescence or fluorescence of the carbon dots here. And you can see the maximum intensity of the fluorescence is when the carbon dots heated with microwave 15 minutes. So we use 15 minutes for the next measurement, for further measurements here. You can see that the maximum intensity happens at 400 nanometers, the maximum fluorescence here. And as you can see here, this is the excitation wavelength of 320 nanometers. You can see the fluorescence changes when we change the pH from 3 to 9. So this carbon dots can be used as a sensor for pH from these results. And this is when we excite the carbon dots with 800 nanometers femtosecond laser. You can see there is a fluorescence here around 500 nanometers. And you can see its scale, the fluorescence intensity scales with the square of the power. Here we can see that the two photon fluorescence excited at 800 nanometers doesn't have difference in the rest time with the normal fluorescence excited at 405 nanometers. So and you can see also there is no signal, no fluorescence signal when we excite the carbon dots with continuous wave lasers at 633 nanometers. So from this result, we can conclude that the photon fluorescence happens via a virtual intermediate stage, not a real intermediate stage. Okay, and this is our conclusions. Environmentally friendly carbon dots from seaweed has been synthesized with facial microwave assisted techniques. The produced CDs have pH sensitive and to photon fluorescence properties. The observed pH sensitivity is attributed to the reversible deprotonation of surface functional groups. Meanwhile, the observed two photon fluorescence arises primarily from two photon absorption via a virtual intermediate state facilitated by short pulse excitation. Thank you for your attention.
Thank you, Muhandis. You did very fast with so we have plenty time for questions. And I'm now looking at the audience. Do we have questions? Anyone? Maybe I'll get started with the first question. The seaweeds that you used to fabricate your carbon dots, is it specific type of seaweeds or any would do?
Oh yeah, I'm sorry. There's a specific type. It's called in Latin Capaphysus alvarezi.
Mm-hmm. Okay, and do you what is so special about this type? Why this one is necessary and not the other ones?
Well, this is abundance in Indonesia. This is
I
kind
see,
of
I see.
red algae.
Right, red algae. Okay, thank you very much. Yes, we'll try with the audience again. Any questions for Muhandis? Yeah, Alex.
Yes, thank you, Dr. Mohandes, for your presentation. You showed a graph. Can you go back to your slides of sensing using your quantum carbon dot? If I'm not mistaken, because you go too fast.
Which one?
It's coming. Your slide is coming.
Okay.
Slide number 9, probably. Yeah, for pH. This is like what is the sensitivity of this in terms of the pH? You showed the graph, but the number we just deduce it.
This is like what is colorimetric or this is just for not really sensitive, you know. It's when you what is it called? It's kind of just for like 1 pH from 3 to 4, 4 to 5, 5 to 6, something like that. So it's not for the sensitive detection of pH.
Okay, thank you.
Since we still have a few minutes, I may follow up with another question. So this is follow up from Alex's question. So it looks like you calibrating your instrument, your sensor, pH sensor, based on intensity of fluorescent signal. Is it correct?
Yes.
Okay. And is there a minimum concentration of your carbon dots that needs to maintain in solution for your sensor to work?
We only use one concentration actually.
And what is that concentration?
It's 10 milligram per.
What is it?
10 milligram.
10 milligram per milliliter.
Yes.
Okay. Well, thank you very much. Thank you very much, Dr. Mohandes. And let's thank the speaker. As we don't have any further questions, I suggest we carry on, and I now would like to introduce our next speaker, Dwi Bayuwati, from National Research and Innovations Agency in Indonesia, who will be talking about optical fiber pressure sensor.
Yes.
You're very welcome, Dwi.
Hello. Hello. Can you hear me? Hello.
Yes. Everything is working. We can see you, but we don't see your slides. So maybe you would like to share your slides.
Good afternoon. I'm sorry. Thank you, Professor Irina. I would like to present my research under title is optical fiber pressure.
We still don't see the slides. You need to share it. Yes, you need to press share button and share the slides.
I already.
We only see your camera, Dwi.
Share.
Yes, loading now.
Okay. Yes. Do you see my slide?
Yeah. Let's give it a second.
Yes.
Yes. Please proceed.
Okay. I'm sorry. This is the title of my research. This is the early stage of the research. this is my college. We are from BRIN also in Serpong. And this is the outline. What is this? And this is for introduction. We know pressure sensing and water level monitoring are essential to be used in various applications. At first, there are conventional electronic and mechanical pressure sensor, and then optical fiber sensor comes, and because of many advantages like this, immune to electromagnetic with allow remote installation, waterproof, and capable of real-time monitoring system. And this is the typical application: monitoring industrial water tank, irrigation level, root control, sea surface monitoring, and so on. Here, a transducer convert pressure variation into measurable optical signal. The principle of this sensor, optical sensor, is like this. So we have optical fiber in a band form of a loop form, and then when light, suppose LED or laser light in, and then we bend it, some light will be leaked out, and there will be bending loss, and this phenomena that we will be used for the sensor, for the pressure sensor. For the theory, here we use theoretical modeling. So based on three steps combined with guide theory, exponential attenuation model, and fluid state. Because we use column water to measure pressure by adding the water in the column. This is the first expression that we will use. This is the expression for bending loss of a stud index fiber. We will be model, but not to calculate exactly physically, only to model by semi-empirical expression. Usually people use a simple expression like this. So this is power out. This is when no pressure, and this K bending coefficient and R bending radius. This will be then according to the external that the fiber code that can be pressure, can be displacement, and so on. And this is when we have water column, and then the pressure will be expressed like this. With this equation, and we can rewrite the equation 1 into this. So we change the P into pressure. Pressure can be depend on rho, C, and H. But it is the meaning of this parameter. For this system, we use fiber optic single mode SMF 28, 10 meter, and bending radius of the sensor 4 centimeters, laser wavelength 1300 nanometers. And this is the diagram of the experiment setup. But before I will show, this is the pressure sensor. Consists of a buoy and paper sensor here with housing and then weight. So we immerse this sensor into the water pipe and fill the pipe gradually with water. And then for experiment, we will verify the performance of the sensor by measuring the output of the sensor optically and electronically. This is laser launched into the fiber after divided by fiber copper into two parts. So this is sensor signal and reference signal. And then the output read by power meter F1 and 2. This is the early stage. So we are developing a new system, developing system using detector and then data processing and using PC and processing application. This is the experimental setup, and then the experimental procedure. This already explained. We test the performance of the sensor system by measuring the optical power output and water pressure or water haze in the ring 0 until 150 using experimental setup that we see here. This already explained. This is the sensor status. So this is the first condition. When no pressure, this sensor like this. We use loop fiber. When water added and then pressure rising, the sensor will be put up and then change into ellipse and etc. into ellipse. So and the end it will be like bow tie, the form of the sensor. This is the only result that I can report now. This is the water head and optical power output and water pressure relation when we use water column with a height around 2 meters, and we can only measure until 150 centimeters. This pressure, red dot, and blue output power in microwatt. And then we will analyze the result using two kind of modeling linear and modeling exponential. But before that, I will this way, this 50, the data under 50 is irregular. Why? Because 50 is the dimension of this system fiber. So we just write down here. So when in 50 centimeter range, maybe it is stuck. The system stuck here, so the sensor will be irregular. The power of the sensor. So it's better if in the real application, we start from 50 centimeters. This just that's my thought. And this is the modeling. We make two modeling linear fit. From linear fit, next we can get the sensitivity of the sensor. From linear fit of optical power versus water pressure, we will get sensitivity to pressure minus 0.574 microwatt per millibar. And for optical power versus water head, we got linear fit with sensitivity minus 0.442 microwatt per centimeter. And then for exponential modeling, we can also model the system using exponential, but it has to be noted that this can be used only if the pressure is lower, and also for water head also lower. If the pressure is high, we have to use a complex theoretical bending loss. This in the lab is just simple set up simple component because lack of fun, so we use what we can use. This is we make our laser generator, laser driver. And for research and discussion, the system shows that water head versus water pressure shows linear relationship as expected. And for water head against power output, it's almost linear, but it shows rather curved. Now this is show the beginning of the exponential effect. Then it is the calculated sensitivities that is useful for instrument calibration or when calculating the minimum resolution. And conclusion, in principle, the sensor works properly. The power output can be modeled in linear or exponential model, but it's in a limited range. Both model can work well, but it is an empirical method and useful for calibration or sensing application in real-time system. For high accuracy theoretical modeling, we need to work harder to use a complex equation, complex principle calculation. To get a better exponential curve, we can try several further investigation like using wider range of water level or using other type of fiber optic or adding some layer in the fiber optic to get sharper bending to fiber. And for system, for advanced study of development of system and method, we can optimize the design, optimizing the design by other fiber band structure or adding data reader also and processor to be compatible with IoT system and also compatible feature for automatic calibration. And this is the work that we are working now. We would like to acknowledge the National Research and Innovation Agency Indonesia BRIN for supporting this research. Thank you very much.
Thank you very much. Thank you very much for your presentation. Now the floor is open for questions. Yes, Alex.
Thank you, Dr. Dwi. I just want to make it clear. Can we see your slide?
No, I lost.
No, your slide.
I lost.
PowerPoint. No, next one.
Yes. Can you
okay.
see?
Yes, I can see your right. Don't worry, just like this is okay. Your tube or your pipe, is it a closed pipe or an open pipe?
Open.
Because you're measuring pressure.
Oh, open.
Yeah.
But the pressure changing. Like this.
Yeah, yeah, it is open or closed? Open.
Yes.
So your buoy actually floats up when you add some more water. So the pressure that the fiber is experiencing is always the same, isn't it? Because your buoy will just flow up.
Yes, yes,
The more water you
yes,
put into your pipe,
yes. The pressure is
the
going up.
buoy and yeah. So the water pressure that experienced by the fiber
Yeah.
will be the same. Because hydrostatic pressure is pressure at the bottom compared to the surface, isn't it? But if your buoy is always flowing up, it's going up with the surface of your water, then it should not. Yeah.
We make that the buoy stable in this position by give weights a weight system here. So
But then you change the weight.
Stable. No, already steady with just adding water. When adding water, we have some mechanical mechanism here. So when water added, it's going up, that's slightly going up, like that. This open. But this make a stable sensor stable in this pipe.
Okay. Maybe we talk again later.
Yeah.
Yes, it's probably
Yeah.
a good opportunity to catch up.
Yeah, we will
this
catch up later,
topic.
Budi. Thank you.
Thank you,
Okay,
Dr.
thank you.
Dwi. And we now run out of time, unfortunately, so we cannot ask any more questions. And we need to move to our next speaker, who I believe is present here. Is it
Okay,
correct?
thank you very much.
Thank you very much.
Yes.
So our next speaker, so this is paper 11, is Muhammad Asharuddin from Institute Technology Bandung, Indonesia. And Muhammad will be talking about the influence of bromide iodide ratio on the photoluminescence characteristics of colloidal of multiple anion cesium lead halide perovskite nanocrystals. So we're looking forward to your presentation, Muhammad. Hey. Yes, it's all working. Okay, the floor is yours.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. First of all, I would like to thank you very much for Professor Udayana who has given me time to talk about my work. And today I'm going to present our work. The title is The Influence of Bromide Iodide Ratio on the Photoluminescence Characteristic of Colloidal Multiple Anion Cesium Lead Halide Perovskite Nanocrystals. Okay, in my presentation, it contains 4 sections. First is introduction, experimental, result, and discussion, and summary. Okay, we go into introduction. Okay, in recent years, the development of organic and organic semiconductor is growing rapidly, especially in the perovskite nanocrystals. The perovskite nanocrystals is a type of nanomaterial semiconductor with a chemical general chemical let me see this IBX3, where A is the organic or inorganic cation, B is a metal cation, and X is a halide anion. Among the various perovskite, all inorganic lead halide, especially cesium lead halide, has various outstanding properties, including the tunable band gap, high photoluminescence quantum yields, narrow emission bandwidth, and high colorability and covering visible light energy. So this feature making them as promising candidate for a material outlet for optoelectronic devices like solar cell, LED, photodetector, photocatalyst, and laser. So in our previous research, we try to calculate the band structure and the projected density of cell of the cesium with bromide, and we found that this materials has a direct band gap with the valence band maximum is a primarily composed of the Br for p orbitals. The conduction band minimum is mainly derived from the 6p orbitals. So its structures make them the strong optical transition and efficient photoluminescence. And experimentally, we also found that the cesium bromide has a strong and narrow emissions around 521 nanometers, and it was confirmed that its material has a high optical quality with the efficient band edge recombination. So this finding make us a basis for our works or current works. So to explain the application of our materials, so we have to tune the emission. So we have tuned the emission. So how we tune the emission of the perovskite? Generally, there are three strategies to tune the emission of the perovskite. The first is a doping element, which using several elements to replace the A side or B side of our perovskite structure. And the second is dimensionally control. Like we develop the several shape like quantum dots, nanorods, nanowires, and nanobands and nanovelots. And the last is the halide composition. But among these three strategy, the halide composition is the easier way to tuning the photoluminescence or the emission of our nanocrystal. So by mix the halide perovskite, especially for Br and iodide, we can precisely control the emission of the emission wavelength via compositional tuning, and we can control the band structure and the wavelength emission. So we can apply it with the various applications like laser and photodetectors. So this work is to study the influence of Br and iodide ratio in mixed halide perovskite nanocrystal on the optical property with respect to the nanocrystal size and electronic structure for the electronic application. Okay, for the experimental section, we use wet chemical process. In our synthesis, we use hot injection method. That we have the hot injection method where the cesium OLED has as a source of the cesium, and we injected into the PBBR2 or PBI2 hot. So the color change after the injection, it's indicating that they are rapidly grow the nanocrystal and make the formation of the perovskite. And by controlling the ratio of PBBR2 and PBI2, we can control the color of solution. After injection, we cooling them to stop the reaction, and after that we centrifugation and purify, because we know that our synthesis there are possibility unreacted product in our nanocrystal. So we purified it using hexane and centrifugation again, and after that we found like this phaser. The green is the cesium PBBR3, and the right is the cesium PBI3. Okay, for the characterization, we use the XRD and higher time to analyze the structure of our nanocrystal, and UV vis and photoluminescence spectroscopy to analyze the optical properties such as the absorbance and the photoluminescence. And we also conducted the PL decay measurement to determine the um, the long life of our excitant. So our research that the cesium lead bromide, the XRD pattern of the cesium lead our nanocrystals show that we mentioned that with the reference data from the crystallography, and we found that our nanocrystal formation is the orthorhombic cesium lead bromide, and the HLTM TM looks like the morphological and dimensional characteristics of our nanocrystals is revealed from the uniform nanocube with the monodispersed and narrow size distribution. The size, the average size around 9.45 nanometers. For the next, we compare the cesium lead bromide with the cesium lead iodide nanocrystals. There is the TEM image of the cesium PBBr3 and the cesium PBI3. Visually, we can see that there are significant difference between the nanocrystals. As the nanocrystals in this image compared to the cesium lead bromides, it appears larger. How can it be happen? It's been happen because the bromide in the cesium lead bromide has a smaller radius of ion, so it's make the cesium lead bromide has a smaller size. So to check our hypothesis, we also conducted the higher time and the difference ratio, cesium PBBr 1 ratio, 1.2 ratio, and the iodide rich. And we can see they are increasing in nanocrystal size with the more iodide content in the which is caused by the larger ionic radius of iodide. It can leading to the lattice expansion and larger nanocrystals. So to investigate the optical properties of our nanocrystal, we also measure the absorbance and the photoluminescence. We can see the band edge of our nanocrystals can be the band edge and then the photoluminescence peak as with redshift to the redshift and redshift with the higher content of iodide content. And then we estimate the using touch plot, and we found that the optical band gap in the cesium lead bromide with increasing the iodide content has more reduced. It is the progressive redshift is correlating with the schematic reduction of the optical band gap. And after that, we also using the PL photoluminescence decay, and we fit this graph with the B exponential function. The first exponential is the fast decay, and the second is the slow decay component. It is indicating that there are two types of the recombination pathway in our nanocrystal. So we compare the PL decay of the pure cesium PB halide 3 nanocrystal, and we found that for the cesium lead bromide has a fast decay. Fast decay is smaller than the cesium lead iodide. It is come from the strong confinement effect from the cesium lead bromide. So the effect of the surface may be negligible. compared to the cesium lead iodide has a large nanocrystal, so it can more probability the electron can reach the surface and trap to the surface recombination. In the mixed halide, we found the same ingredient, but the fast decay is come from the rapid energy transfer from BR rich region to the I rich regions. And the slow decay component is come from the diffusion diffusion from the lower energy domains in BR to the higher recombination before the undergoing radiative recombination. And we tried to make some impactful for the polymer matrix on the photoluminescence of nanocrystal, and we found that there are significant redshift on our photoluminescence, but the decay is more longer than others, because this is caused by the defect state of the on the nanocrystal surface. In the colloidal phase, the nanocrystal more be homogeneous. And in the matrix of the polymer, it looks like less homogeneous because the polymer matrix may be ingest the nanocrystal clustering and leading to the surface state variation and heterogeneous recombination dynamic. So this surface state maybe act as a trap state for the charge. So the second component decay is more longer. So in the summary, the mixed halide perovskite nanocrystal was successfully tuned to the control the optical properties of the nanocrystal, increasing the iodic content leads to the larger nanocrystal size, which reduces the quantum confinement and resulting in a shift of the absorption and photoluminescence spectra, indicating a narrower optical gap. And polymer embedding introduces heterogeneity and the surface trap that affects spectra, absorption spectra, and the photoluminescence decay, emphasizing the importance of the passivation and uniform dispersion to maintain the high for PL performance. Thank you.
Let's thank the speaker. Thank you very much for excellent talk. We have a few minutes for a quick question. Any questions from the audience? Okay, I will ask a question then. Mohammed, in your slides, you are doing the fitting of the photoluminescence and decay, right? Exponential decay. And you found that there are two processes with tau 1 and tau 2. Would you give us insights of the physics of these two processes? What is fast decay and what is slow? What's sort of origin of this decay?
Okay. Okay, maybe yes. Okay, there's two decay components. Right? The first component it's comes from the initial internal states, which are the bulks of the nanocrystals, and the second is represent the radiative or non-radiative recombination at the surface states. So if our nanocrystal has a smaller size, is the quantum confinement is more strong. So the decay, the first decay must be lower than others. But if the nanocrystals grows larger, the confinement is more weak. That's called the possibility the electron reach the surface is much higher, so it can be interact with the surface, especially in the cesium lead halide, because the cesium lead halide is a poor stability because they have changed from the black cesium, the alpha phase to the gamma phase, the non-radiative perovskite.
Thank you very much for clarifying it.
Thank you very much.
Let's thank the speaker again. And now we proceed to paper 12 that will be presented by Gaitsa Shofa. Gaitsa, can you please make it to the stage and set up? And the presenter is from I cannot pronounce it very well, but yes, Universitas Gadjah Mada, Indonesia. And the title of presentation, photoluminescence of green synthesized ferrofluids for magnetic hyperthermia application. Please proceed.
Thank you. Good afternoon, ladies and gentlemen. I'm very pleased to meet you all today at the International Symposium of Modern Optics and its Application 2025. First of all, I would like to introduce myself. My name is Gaijan Asma Yahira Sofa, a master student in Department of Physics, Universitas Gadjah Mada. In this great opportunity, I would like to present our latest research entitled Photoluminescence of Green Synthesized Magnetite C-dot Ferrofluid for Magnetic Hyperthermia Application. So here is the outline of the presentation. We know that cancer is the second leading cause of global mortality. Traditional cancer therapy such as chemotherapy or radiotherapy tends to damage not only the cancerous cells but also the surrounding healthy normal cells, leading to serious side effects and reduced patient quality of life. Now, the researchers develop more precise, targeted, and safer therapeutic strategies. Among these, one notable application is magnetic hyperthermia, which uses an alternating magnetic field or EMF to induce heat in magnetic nanoparticles concentrated in tumors, aiming to kill cancer cells. If therapeutic temperatures between 41 to 47 degrees Celsius. The fluorescent nanoparticles help in dose evaluation and precise localization before applying EMF to induce heat in magnetic hyperthermia therapies. So it can offer several advantages like precise localization, selective cancer cell killing, high biosafety, and deep tissue penetration. Among the various magnetic materials, magnetites are ideal candidates due to their high saturation magnetization, superparamagnetism, biocompatibility, in ferrofluid form, exhibit better dispersion. But magnetite has a weakness that magnetite can evaluating dose and cannot detect particle quantification. Carbon dots have many advantages like fluorescent material, chemical stability, non-toxicity, and biocompatibility. But C-dot also has a weakness too, that C-dot is non-magnetic material. So the incorporation of magnetic material with fluorescent material based on C-dot nanocomposite is an effective solution to overcome these above problems. So the research is aimed to green synthesize magnetite C-dot ferrofluid as bifunctional magnetic hyperthermia with fluorescence imaging application. Next, we are moved to the experimental method. The material that used for the synthesis are shown in the slide. All these materials were analytical grade and were used without further purification. Using copper repetition methods. And the next step, carbon dots were synthesized using hydrothermal method. And the next step, we are fabricate magnetite C-dots under the sonification method. In this step, we are finally get the magnetite C-dot nanocomposite. And the last step, we are fabricate magnetite C-dot ferrofluid with added magnetite C-dot, magnetite C-dot nanocomposite, citric acid, aqua dash, and MO. Next, the instrument setup. This feature shows the illustration of thermal Schwarzman instrument with calorimetric methods. In this method, a sample of magnetite ferrofluid subjected to an alternating magnetic field with a certain period and frequency experiences an increase in the temperature recorded and in the temporary recorded and certain periods. And as we prepared, we are characterized the samples of the magnetic C-dot ferrofluid or nanocomposite with with photoluminescence, ultraviolet visible spectroscopy, scanning electron microscopy, X-ray diffraction, transmission electron microscopy, Fourier transmission infrared, vibrating sample magnetometer, and the specific absorption rate to knowing their opticals and morphology and crystal structure, magnetic properties, and chemical bond and their heating characteristic. The first optical analysis is photoluminescence. A shift in the excitation of wavelengths of C dots was observed compared to magnetite C dot, specifically at 408 nanometer and 450 nanometer. So that results indicate the successful of the ferrofluid magnetite dot nanocomposite. So that result indicating that C dot exhibit excellent fluorescence compared to magnetite. And the excitation wavelength of magnetite C dot ferrofluids belong to the visible spectrum at 400 to 700 nanometers under UV light exposure. The incorporation of C dots into the magnetite C dot ferrofluid introduced significant fluorescence, enabling the system to be used for dose evaluation during magnetic hypothermia. And then the another optical analysis is ultraviolet visible spectroscopy. This feature shows the UV vis absorption spectra. In magnetite C dot, the absorption peak of magnetite was observed in 400 nanometers. Meanwhile, the absorption peak of C dot was not in 282 nanometers. So this is indicating the successful of incorporation the ferrofluid, and that's indicate that the band gap energy values increase with the rise in C dot concentration. The next characterization is scanning electron microscope, or SEM. This feature shows the surface topology of the sample, and the EDX analysis shows that magnetite C dot contain of iron, oxide, and carbon in weight percentage respectively, and the detection of carbon is magnetite C dot provides evidence of the presence of C dot in the nanocomposite, and the mapping image shows that the carbon elements are distributed around the magnetite, indicate that the lack of other impurities in the structure. The next characterization is X-ray diffraction. The feature on this slide shows the XRD pattern of magnetite C dot nanoparticles. The results suggest that the incorporating of the C dot led to modification the lattice parameters and reduction the crystalline size. So that indicate the presence of this carbon on the surface of magnetite, and the crystalline size, lattice parameter, and phase composition are shown and is stable. The magnetite nanoparticle exhibit an inverse spinel cubic phase. As C dot concentration increase, the phase composition of carbon increase, and the average crystal size is inversely proportional to the increasing C dot concentration. And then to examine the morphology and the particle size distribution of the samples, we are use the transmission electron microscopy. So the result that the samples are semi-spiral in shape, and the diffraction ring in the SAED pattern of the magnetite and magnetite C dot are consistent with the XRD result. And then the next characterization to know the magnetic properties, that this feature shows the magnetization curve of magnetite C dot nanoparticles, revealing that the magnetite are superparamagnetic materials and has a small remnant magnetization. So the magnetic saturation decreased at the concentration of C dot increase. This effect is due to the non-magnetic nature of the C dot, which impedes the growth and movement of magnetic moment on the surface of magnetite. And then this is the feature of FTIR spectra of C dot, magnetite C dot, and magnetite nanoparticles. And then the last discussion is specific absorption rate or SARS. That feature is the induction heating curve of magnetite and magnetite C dot ferrofluid at various frequency. That the feature indicating that the more significant the variation in frequency, the greater the temperature increase over time. And this is the feature of induction heating curve of samples with various magnetic field. The more significant the variation in EMF, the greater the temperature increase over time, and the more significant variation of C dot concentration, the smaller temperature increase over time. And the next, this is the feature of the SAR values of magnetite and magnetite C dot ferrofluid with various frequency. The more significant the variation in frequency, the greater the SAR values obtained. And the feature is about SAR values of the samples with various magnetic field. So the more significant the variation in EMF, the greater the SAR values obtained, and the more significant variation the C dot concentration, the smaller the SAR values obtained. The last discussion is about magnetism of the SAR Meares treatment, that nanocomposite magnetite C dots are primarily governed by Neal and Brown relaxation mechanism under the EMF. The incorporation of the C dot modifies Brown relaxation by hindering particle relaxation, resulting in the more gradual temperature rise, particularly a higher concentration. Beyond thermal effect, C dot enhance the dispersion and biocompatibility of magnetic nanoparticles, minimizing agglomeration and cytotoxicity while enabling dual functionality for imaging and for therapy. For that result and discussion, we can conclude that the magnetite and the magnetite C dot ferrofluid has been successfully synthesized by a green approach utilizing Moringa oleifera extracts and watermelon peels. These are values of the magnetite and magnetite C dot ferrofluids with various concentration were 383 and 230 to 350 watts per gram respectively at the maximum frequency and the maximum magnetic field variation. And the results suggests that green synthesized magnetite C dot ferrofluid show significant potential for bifunctional magnetic hyperthermia and fluorescent imaging application. So that's our presentation for me. Thank you for your attention.
Wonderful. Thank you very much for your presentation. We have a few minutes for questions. Questions, anyone? Don't be shy. All right. I will ask my first question. Maybe it inspires others to ask more questions. So when you did your distribution by size, you had those plots in your slides where you had distribution of particle by size, I think, and you used line fitting. Maybe if we go back to that slide, it will be easier to answer. Yeah, this one. So you have frequency and you have particle size. What line shape do you expect for these results, and what did you use for your fitting?
So that I expect for this experimental is decreasing the particle size while increasing the C dot concentration. That's.
But you do have a Gaussian shape.
Yes.
This is a Gaussian fit?
This shape in semi-separal in shape.
Is it a Gaussian or is it Lorentzian shape?
And shape.
Gaussian. Yes. And why would it be Gaussian?
I'm sorry.
Why would the shape be Gaussian?
What, sir?
So you have your histogram. So you have
Yes.
distribution of your particle size and your frequency distribution of these nanoparticles. And you are fitting your distribution with a Gaussian line shape. So my question is, why would this be Gaussian? Because there are different models.
So when we characterize the image of the morphology, there are semi-separal in shape. There are many separal in shape. That's the diameter of this nanomaterial is variation, like about if we are knowing that this is about 10 and that's nanoparticles that the diameters can detect in 6 or in 8 or in 10 and in 12. That's of many shape of this semi-separate.
Yeah, I understand what it means. Thank you. It's all good. Thank you very much.
Thank you.
Any more questions from the audience? I think the time is up. So thank you very much for your
Thank you,
presentation.
Miss.
So we arrived to the last talk of this session that will be presented, paper number 13, and the speaker is Hani Kilifia. I'm sorry if I mispronounced your last name, from Institut Teknologi Sepuluh November in Indonesia. So please proceed to the stage and get set up. All the slides are already there. Wonderful. So the presentation titled Morphological and Crystallinity Characterization of Gold Nano Islands on Sapphire Deposited Using Pulse Laser Deposition. The floor is yours.
Okay, thank you, Prof. Iriana, for the opportunity. So I will begin. Good afternoon, everyone. My name is Hani Fitriatul Hilfia. I'm from Department of Physics, Institute Technology, Sepuluh November. And in here, I want to present our work on title Morphological and Crystallinity Characterization of Gold Nano Island on sapphire deposited using pulse laser deposition. In this research, we are collaborating with a National Research and Innovation Agency and the Nano Center Indonesia. So, our background is why are the gold nanostructure important? Because its gold nanostructure is significant attention in nanophotonics and plasmonic sensing. Because its ability to support localized surface plasmon resonance or LSPR, and LSPR is highly sensitive to size, shape, and crystalline structure. Because of this reason, it's crucial for precise structural control at the nanoscale. Next, our motivation is investigate the morphology of gold nano island grown on sapphire substrate with pulse laser deposition, and we analyze the effect of the substrate temperature and on the crystallinity and morphology, and we are aim to correlate morphology and crystallinity with plasmonic performance using source measurements and identify the optimal growth condition for enhanced LSPR activity and hotspot density. So in here we are use a pulse laser deposition for our method because enables clean, controllable, and precise deposition, especially using for growing nanostructure is also support growth under high vacuum preserving purity. This is our method. This is a pulse laser deposition. Pulse laser deposition is when method then the laser pulse is hit the target material and it's applying material to the substrate in here. Substrate. The substrate is sapphire. So our target material is gold with a 99% purity, and substrate is single orientation sapphire with PLD laser setup is NDWAG laser 532 nanometers with a repetition rate 4 Hz and laser fluence 2.7 joule per centimeter square and 5,000 laser pulse. Our chamber condition is the best pressure at approximately 10 to the minus 7 torr, and our variation is a deposition temperature at 450 degrees Celsius, 650 degrees Celsius, and 750 degrees Celsius. Next is our result of our work. At first is atomic force microscope for the morphology of gold nano island. It looked that the morphology at the 450 degrees Celsius, it looks small and densely. Comparing with that higher temperature at the 605 C or 750 degrees Celsius is more larger and coalescent. It's also look at the histogram. In here, we can know the distributed of the our nano islands, and in here we can calculate statistically about the diameter average of the nano island in IFM, 11.27 nanometer for the diameter at 450 degrees Celsius, 15.94 nanometer for the gold nano island on sapphire in 650 degrees Celsius, and 16.57 nanometer for gold nano island on sapphire at the 750 degrees Celsius. It's can we conclude that the higher temperature in island size by enhancing adjective mobility, promoting island growth, and facilitating coalescence. So next is the result of X-ray diffraction. This is about the crystallinity of gold nano island. The peak of gold nano island is preferred to single orientation gold nano island. AU111 plane, it's equals 38.2 degrees, and the sapphire substrate is approximately 41.8 degree. About this result of crystallinity, we can calculate the crystalline size of this gold nano island with a scalar formula. So we have the result of this crystalline size in here. After we have the crystalline size and the average diameter of atomic force microscope, we can comparing of this. So we can know that the magnitude of the crystalline size and average diameter, it almost have or equals magnitude. So it suggests that the gold nano island is have single domain orientation at 450 degrees Celsius, and we know that at higher temperature it have gap from average diameter and crystalline size is can be suggested, but multi-domain orientation might start to form. This is came about the single domain orientation in one nano island, so it have a one direction like that, and multi-domain orientation in one nano island at the higher temperature is you can see in here. So next is our application of our gold nano island is a surface enhanced Raman spectroscopy application or SEARCH. SEARCH is technique that leverages the unique plasmonic properties of nanostructure to significantly boost the typically weak Raman signal of molecules. You can look at this figure. When light interact with the nanostructure, it generates highly localized and intensity electromagnetic fields known as hotspot. This hotspot can amplify the electric fields experienced by any absorbed analyte molecule. So our sample source preparation is the analyte is methylene blue with the concentration 0.1 millimolar. Our drop casting to 5 microliter the MB solution using a pipette into the active area and allow the droplet of MB solution to dry naturally at room temperature. So our result of SEARCH is here. We can know that the methylene blue at concentration 0.1 millimolar from the analytes is optimal source enhancement at 450 degrees Celsius, and the peak MB at 1625 centimeter minus 1 for vibration CC ring, and 1433 centimeter minus 1 for vibration asymmetric CN ring. We can look at this Correct. So the intensity of Raman spectra enhanced more than 20 times the Raman spectra from MB on Sapphire without the nano island. So we can look at this graphic. Next is our discussion. So hotspot density and crystallinity, we can know that at 450 degrees Celsius, nano island are single domain. It because the crystalline size and the particle size, it had the same equals magnitude. So at the 650 and 750 degrees Celsius, it has a larger particle than the crystal itself. So it's look multi-domain orientation. So hotspot density at a single domain, it have a uniform plasmonic fields. It make the search stronger, and a multi-domain it's make a grand boundaries these subfields. It's make a fewer hotspot, weaker shear. So we can conclude that the increasing substrate temperature improve crystallinity but lets domain splitting. It's make reducing plasmonic efficiency. So our conclusion, the morphology and crystallinity of nano island on Sapphire using PLD are strongly influenced by the substrate temperature. The higher temperature led to increased island size and the formation of multi-domain orientation and reduced hotspot field uniformity. And we know that the optimal search performance is achieved at 450 degrees Celsius because it's higher the spot density, smaller island size, and uniform fields due the single domain particles. Okay, thank you. After this, the author get fully acknowledge all the collaboration, and I'm open for the question. Thank you.
Thank you very much for your presentation. Do we have questions for the speaker? Okay, as a traditional, ask a question.
Yes.
So if you can go back to your temperature results, I think it's the slide before last. No. Two more? No, more. So here, okay, no, next one.
Discussion.
Yeah, this one. Yeah, so you are looking at the crystallite size here versus temperature. You have quite broad temperature range, but not very many points. Do you think it would be advantageous to look a little bit more in detail what this dependency might be?
Many points.
Well, what I guess what considerations did you have in mind by choosing this exactly 3 temperatures?
Okay, because it was the result of the AFM and the result of XRD. It has average diameter and clearly have a crystalline size to calculate with scalar formula, and we know that we only make a sample with a 3 temperature. We just ensure that two temperature that higher than 450 it has a different cap for the average size diameter and the crystalline size, so it can be concluded that it have a multi-domain structure like that.
Okay, so I guess I rephrase. So in other words, would looking at 500 degrees C be interesting at all or not really?
500.
Yes. Yes, centigrade. So you have no points between 450
Oh yeah.
650. Would it be interesting to look there?
Because we know that the 450 degree it's almost the same, but I at the 550 degree is might be had a cap too, so it's like uh it's like more have some result like the 650 degree and 750 degree, because the 450 degree too have the gap, but it's small. Our hypothesis is when the lower degree or lower temperature is maybe have same a crystalline size like the average diameter of IFM. So we are make a sample with this temperature like that.
Okay. Well, maybe something to think about for the future. Thank you very much. So let's thank the speaker, and the session is finished. So we'll thank all the speakers in the session. I think I pass it back to the master of ceremony, and thank you very much for your attention.
Give applause one again for Professor Iriana and also our presenter for today's event. And it's officially done, our sessions in room A. So we will continue with the coffee breaks, and then we will be coming back at 4:40, 4:45, and we'll continue our closing ceremony and also the announcement of the winner of the poster presentations and our favorite presenter. So please enjoy your coffee break. Thank you.
I would like your attention. For participant, you can also vote for favorite presenters, yeah. For invited speaker, we vote for best poster and best oral, but participant, you can vote for your friends for best presenter. We use LinkedIn, Linktree. You got your Linktree. In Linktree, there's a option to vote.
Okay, once more for announcement, I would like to inform for all the participants that want to join us for tomorrow's agenda. So please gather in the hotel lobbies before 8:30 because we're gonna depart from this hotel at 8:30. Thank you.
power supply, multimeter, and oscilloscope are used for the standard electrical test. In a typical industry in the lab, we need multiple of these devices, but the problem is they have excessive power, limited output, expensive, bulky, cumbersome, and inconvenient. And the solution is XDAC, a sophisticated source measurement unit for low power applications from simple electronic circuits to complex photonic integrated circuits. We also offer a variety of channel options ranging from 8 to 40, 80, and 120. We are also beginning to develop our product into a chip scale version with a wide range of imaginable applications. Start from sensing and instrumentation, telecommunications, machine learning, and quantum computing. If you're interested, we also provide a live demo unit and a GUI simulator to give you a better understanding of our product. You can find more information on our website. We are waiting for you. Together, we are unlocking the power of light.
At FLIR, we asked a simple question. Why choose between what you see and what you don't? For years, we've relied on visible light to define structure. But structure alone doesn't tell the full story. Infrared reveals transformation, heat radiating from machinery, stress forming in materials, energy shifting before failure occurs. But these two perspectives have always been separate until now. Introducing FLIR Mix, the first imaging system to capture high-speed visible light and the revealing power of infrared together in perfect sync. Every pixel aligned in time and space, every moment captured with absolute precision. Now, researchers and engineers can see structure and transformation at the same time, in real time, without the need to piece together separate data sets. FLIR Mix doesn't just show you the moment, it shows you what makes the moment happen. With up to 1,000 frames per second, every reaction, every shift in temperature, every hidden change is revealed, giving you the power to analyze change as it unfolds. No more wasted hours aligning data streams. No more uncertainty. Just faster, more accurate insights, so you can focus on results. With FLIR Research Studio, visible and infrared data are captured, processed, and analyzed in one system, eliminating complexity and delivering seamless integration. One workflow, one synchronized data set for scientists, engineers, and researchers across material science, electronics testing, renewable energy, and high-speed dynamics. Patterns once missed, now visible. Failures before they happen, now preventable. The future of imaging, now here. For researchers, for engineers, for visionaries. Because when two worlds come together, you don't just see more, you see everything. FLIR Mix. See more, no more.
If you're designing photonic systems, ANSYS Lumerical lights the way. From virtual reality to display technology, from auto sensors to smartphone cameras, from laser design to quantum computing, from 5G to data centers, ANSYS Lumerical is a world leader in photonic simulation. We've been helping engineers meet product development deadlines for nearly 20 years, collaborating with leading third-party tool providers to create new workflows, building better photonic systems on time, on spec, and with higher performance. Referenced in over 15,000 scientific papers and patents, Lumerical has been run in close to 30 million simulations by roughly 50,000 different users, by 90% of the leading research universities in the world, and by all 10 of the top IT index companies. If you are designing photonic systems at the component and circuit levels, ANSYS Lumerical is a complete cloud-ready simulation solution. It's easy to learn and deploy, constantly innovating new solutions and techniques. For reliability, speed, and accuracy, there's only one true leader in light, ANSYS Lumerical.
Power supply, multimeter, and oscilloscope are used for the standard electrical test. In a typical industry in the lab, we need multiple of these devices, but the problem is they have excessive power, limited output, expensive, bulky, cumbersome, and inconvenient. And the solution is XDAC, a sophisticated source measurement unit for low power applications from simple electronic circuits to complex photonic integrated circuits. We also offer a variety of channel options ranging from 8 to 40, 80, and 120. We are also beginning to develop our product into a chip scale version with a wide range of imaginable applications. Start from sensing and instrumentation, telecommunications, machine learning, and quantum computing. If you're interested, we also provide a live demo unit and a GUI simulator to give you a better understanding of our product. You can find more information on our website. We are waiting for you. Together, we are unlocking the power of light.
If you're designing photonic systems, ANSYS Lumerical lights the way. From virtual reality to display technology, from auto sensors to smartphone cameras, from laser design to quantum computing, from 5G to data centers, ANSYS Lumerical is a world leader in photonic simulation. We've been helping engineers meet product development deadlines for nearly 20 years, collaborating with leading third-party tool providers to create new workflows, building better photonic systems on time, on spec, and with higher performance. Referenced in over 15,000 scientific papers and patents, Lumerical has been run in close to 30 million simulations by roughly 50,000 different users, by 90% of the leading research universities in the world, and by all 10 of the top IT index companies. If you're designing photonic systems at the component and circuit levels, ANSYS Lumerical is a complete cloud-ready simulation solution. It's easy to learn and deploy, constantly innovating new solutions and techniques. For reliability, speed, and accuracy, there's only one true leader in light, ANSYS Lumerical.
Power supply, multimeter, and oscilloscope are used for the standard electrical test. In a typical industry in the lab, we need multiple of these devices, but the problem is they have excessive power, limited output, expensive, bulky, cumbersome, and inconvenient. And the solution is XDAC, a sophisticated source measurement unit for low power applications from simple electronic circuits to complex photonic integrated circuits. We also offer a variety of channel options ranging from 8 to 40, 80, and 120. We are also beginning to develop our product into a chip scale version with a wide range of imaginable applications. Start from sensing and instrumentation, telecommunications, machine learning, and quantum computing. If you're interested, we also provide a live demo unit and a GUI simulator to give you a better understanding of our product. You can find more information on our website. We are waiting for you. Together, we are unlocking the power of light.
If you're designing photonic systems, ANSYS Lumerical lights the way. From virtual reality to display technology, from auto sensors to smartphone cameras, from laser design to quantum computing, from 5G to data centers, ANSYS Lumerical is a world leader in photonic simulation. We've been helping engineers meet product development deadlines for nearly 20 years, collaborating with leading third-party tool providers to create new workflows, building better photonic systems on time, on spec, and with higher performance. Referenced in over 15,000 scientific papers and patents, Lumerical has been run in close to 30 million simulations by roughly 50,000 different users, by 90% of the leading research universities in the world, and by all 10 of the top IT index companies. If you're designing photonic systems at the component and circuit levels, ANSYS Lumerical is a complete cloud-ready simulation solution. It's easy to learn and deploy, constantly innovating new solutions and techniques. For reliability, speed, and accuracy, there's only one true leader in light, ANSYS Lumerical.
Power supply, multimeter, and oscilloscope are used for the standard electrical test. In a typical industry in the lab, we need multiple of these devices, but the problem is they have excessive power, limited output, expensive, bulky, cumbersome, and inconvenient. And the solution is XDAC, a sophisticated source measurement unit for low power applications from simple electronic circuits to complex photonic integrated circuits. We also offer a variety of channel options, ranging from 8 to 40, 80, and 120. We are also beginning to develop our product into a chip-scale version with a wide range of imaginable applications. Start from sensing and instrumentation, telecommunications, machine learning, and quantum computing. If you're interested, we also provide a live demo unit and a GUI simulator to give you a better understanding of our product. You can find more information on our website. We are waiting for you. Together, we are unlocking the power of light.
If you're designing photonic systems, ANSYS Lumerical lights the way. From virtual reality to display technology, from auto sensors to smartphone cameras, from laser design to quantum computing, from 5G to data centers, ANSYS Lumerical is a world leader in photonic simulation. We've been helping engineers meet product development deadlines for nearly 20 years, collaborating with leading third-party tool providers to create new workflows, building better photonic systems on time, on spec, and with higher performance. Referenced in over 15,000 scientific papers and patents, Lumerical has been run in close to 30 million simulations by roughly 50,000 different users, by 90% of the leading research universities in the world, and by all 10 of the top IT index companies. If you're designing photonic systems at the component and circuit levels, ANSYS Lumerical is a complete cloud-ready simulation solution. It's easy to learn and deploy, constantly innovating new solutions and techniques. For reliability, speed, and accuracy, there's only one true leader in light, ANSYS Lumerical.
Power supply, multimeter, and oscilloscope are used for the standard electrical test. In a typical industry in the lab, we need multiple of these devices, but the problem is they have excessive power, limited output, expensive, bulky, cumbersome, and inconvenient. And the solution is XStack, a sophisticated source measurement unit for low-power applications from simple electronic circuits to complex photonic integrated circuits. We also offer a variety of channel options, ranging from 8 to 40, 80, and 120. We are also beginning to develop our product into a chip-scale version with a wide range of imaginable applications. Start from sensing and instrumentation, telecommunications, machine learning, and quantum computing. If you're interested, we also provide a live demo unit and a GUI simulator to give you a better understanding of our product. You can find more information on our website. We are waiting for you. Together, we are unlocking the power of light.
I'm Dr. Yvette Matley, and I'm thrilled to be here today to tell you about the next generation of our NIR spectrometer, the NearQuest Plus. The NearQuest Plus is available in configurations covering the complete NIR wavelength range from 900 to 2,500 nanometers, and it's customizable to fit your specific application needs. We have put our 30+ years of experience to squeeze every ounce of performance out of the components that we're using in the NearQuest Plus. So it won't look any different to you than your standard NearQuest, but the performance of the NearQuest Plus will look much different. I'm very excited to report that we are seeing a 2.5 times increase in the sensitivity into the bench. For those of you who have ever worked in the NIR region, you know that we're always starved for light. And the best way to get the most accurate measurements is to get more light into the system. And that is precisely what the NearQuest Plus will do for you. To accomplish this, we're using various indium gallium arsenide or InGas detectors, a thermoelectrically cooled detector that will let you cool the detector down 40 degrees Celsius below ambient temperature. This keeps the noise very low, which also improves on your ability to detect low signal levels. Ocean Insight was the first to develop a modular spectrometer approach. And in the case of the NearQuest Plus, we've kept that going with different levels of throughput based on the slit that we use, with different responsivities based on the gratings, and can actually find its way out of the lab to make measurements, or can be taken and set up very easily where the measurements need to occur. And as a whole, this enables our customers, our partners, to do so much more than they could ever do with these benchtop integrated type of systems. A very important part of the whole picture involving the NearQuest Plus is having the tools that you need to use the data that you're acquiring from the spectrometer. OceanView will enable you to use the NearQuest Plus in absorbance, transmission, or reflectance mode, in addition to providing a full range of features, including strip charting, customization of your data processing, and many other features. We want to quantify, we want to be able to determine sugar for fruit sorting, for example. Ocean has a companion to the NearQuest Plus, called Ocean Intelligence, which is really going to allow you to take that spectral data to the next level. The NearQuest Plus is ready for shipping today, with custom configurations also available to match your specific application needs. That's it. That's the NearQuest Plus.
If you're designing photonic systems, ANSYS Lumerical lights the way. From virtual reality to display technology, from auto sensors to smartphone cameras, from laser design to quantum computing, from 5G to data centers, ANSYS Lumerical is a world leader in photonic simulation. We've been helping engineers meet product development deadlines for nearly 20 years, collaborating with leading third-party tool providers to create new workflows, building better photonic systems on time, on spec, and with higher performance. Referenced in over 15,000 scientific papers and patents, Lumerical has been run in close to 30 million simulations by roughly 50,000 different users, by 90% of the leading research universities in the world, and by all 10 of the top IT index companies. If you're designing photonic systems at the component and circuit levels, ANSYS Lumerical is a complete cloud-ready simulation solution. It's easy to learn and deploy, constantly innovating new solutions and techniques. For reliability, speed, and accuracy, there's only one true leader in light, ANSYS Lumerical.
Power supply, multimeter, and oscilloscope are used for the standard electrical test. In a typical industry in the lab, we need multiple of these devices, but the problem is they have excessive power, limited output, expensive, bulky, cumbersome, and inconvenient. And the solution is XDAC, a sophisticated source measurement unit for low power applications from simple electronic circuits to complex photonic integrated circuits. We also offer a variety of channel options ranging from 8 to 40, 80, and 120. We are also beginning to develop our product into a chip scale version with a wide range of imaginable applications. Start from sensing and instrumentation, telecommunications, machine learning, and quantum computing. If you're interested, we also provide a live demo unit and a GUI simulator to give you a better understanding of our product. You can find more information on our website. We are waiting for you. Together, we are unlocking the power of light.
At FLIR, we asked a simple question. Why choose between what you see and what you don't? For years, we've relied on visible light to define structure. But structure alone doesn't tell the full story. Infrared reveals transformation. He
Good afternoon, everyone. Now we will start our last session. So for all participants, can be please seated. Okay, welcome back everyone to our last sessions. That is the announcements of our winner for poster design, for poster, oral presentations, and our favorite presenter, and also our closing ceremony. So for the first ones, we would like to invite Professor Alex to announce our winner for today's event. Thank you.
Okay. Okay. Welcome back, everyone. At the end of our scientific activity, we still have one more day to go, but tomorrow is excursion. Just to remind you, before I forgot, we have shifted the time to gather to go for excursion tomorrow. By now, we are gathering at the lobby at 8:30. Yeah? Is it correct, Pak Heri? 8:30. Okay. 8:30 in the morning tomorrow. Thank you, everybody, for coming, especially our distinguished invited speakers, Professor Kaur Tamada, Professor Carsten Rockstuhl, Professor Minkyo Sho, Professor Rio Okamoto, Professor Kuroda. Thank you. Who else? Did I miss somebody? Professor Rahmat, my colleague. Okay. It has been our tradition that we vote for best oral, best poster, and this year we have favorite presentation. It's a live voting, so I need my laptop to check what is the latest result. Okay, so let's see. For oral, before I call, can I also invite my colleague who has beautifully organized our conference here in Bali, Professor Agus Hatta and Professor Heri Suyanto. Without the hard work of my colleagues here, we would not have a very nice conference here in Bali. The program, the dinner last night was by Prof. Heri, and all the organization is by Prof. Hatta. And by the way, although I'm the president of Indonesian Society, but my presidency is probably in another 15 minutes. Because after that, Vice President-elect Professor Agus Hatta will take over as the presidency of the Indonesian Optical Society. We have elected the new Vice President, but it will be open during our Congress later on. Now we just finished our symposium. So according to the live response, the best oral presenter, oral presenter number 6, which is, if I'm not mistaken, Muhammad Tegar. Pak Agus, terima kasih. So we have a certificate, best oral, and there's a voucher from World Scientific, $200 Sing dollar for you to buy any book from World Scientific. It's an online voucher. And we give you 2 years free subscription to Indonesian Optical Society. And next is our best poster. Let me check. Okay. Yes. Drum roll. Poster number 15. Irene Ahmad, is it? A certificate, a voucher from World Scientific Publishing in amount of 200 Singapore dollars. You can buy online book and regular membership free for Indonesian Optical Society. And lastly, the favorite presenter goes to poster number 15, Irene Ahmad again. Yeah, you. So you got 400 Sing dollar to spend in World Scientific. Okay, there's a request from World Scientific that we stand here and take photo. Can you take official photo? Yeah, you hold two. Okay. Yes. So to officially close our symposium, I will hand over to the next president of Indonesian Optical Society, Professor Hatta, please.
Okay, thank you, Pak Alex. Okay, good afternoon, ladies and gentlemen, especially our distinguished invited speakers and all colleagues. So I would like to share a little bit, not presentation, the slide. Yeah. So I would like to share the important that perhaps can change the Indonesian landscape in the next decade. This is the roadmap that appear in the recent days This is the roadmap for semiconductor industry in Indonesia. So it is initiated by Ministry Coordinator of Economics, and it's already explained there, starting from the material, the design, the fabrication, assembly, packaging, and then how the industry will impact it. So it will be a new economy in Indonesia, and then the most important thing is there is a photonics word in this slide, but it's too small. On the top of the right part, it is photonics, AI, automotive, something like that. So it's real. It's quite surprising for us that the photonics is now becoming understandable by the government. Then it's the emerging technology. So there is a target for the next 10 years, starting from short term, medium term, until the long term for the 10 years, how to prepare, how to fulfill this roadmap. Okay, next slide. So in the framework of Indonesian Optical Society, it is very important. I know, not this one. Yeah, in the framework for Indonesian Optical Society, I think we have to follow this roadmap to fulfill the roadmap. But unfortunately, we just started. I just discussed during this ISMOA with Pak Alex and also colleagues that it is very important to prepare in the so at least we need to prepare two things. The first one is road mapping the photonics development in Indonesia. So at now, we don't have that roadmap, right? Pak Alex in Bandung, Pak Heri in Udayana, and all of Indonesian scientists and engineers, we work with our own. So it is very important to develop a roadmap for Indonesian Optical Society. So the second issues, it is also now, it is a time for Indonesia, colleagues in Indonesia to have integrated, to have something like, connected postgraduate study, especially emphasizing on semiconductor and photonics. That will be very nice. For example, we have a good best practice in Europe, like a Erasmus program that the postgraduate student can get some experience from many universities, engaging with industry and also from other university abroad. So I think this is a good challenge for the Indonesian Optical Society to work hand in hand. And also we need our colleagues' support. We need your support and inputs or recommendations of how to road mapping for photonics in Indonesia, in order to be connected to all of you, and also how to improve our scholars and also the scientists. Step. Next slide. Huh? Oh. Okay. 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 The last information that I would like to share. So I would be. We are very happy that we already discussed. We are a sustainable organization. Now I would like to declare that the ISMOA, the 16th ISMOA, in 2027 will be held in Surabaya, Indonesia. So Surabaya is located between Jakarta and Bali Island, so in Java Island. Okay, thank you very much, Alex. Thank you. Good afternoon.
Okay, because our ISMOA has been done, so for the participants that want to join the Congress can be stay here, and then for participants that doesn't want to join the Congress can be leave. Thank you. Indonesian Social Optical Society Congress. Oh iya. Okay, for the participant that want to take off their poster can be taken off and you can take the poster home back. Thank you.
Kemarin itu mas siang-siang siapkan slide-nya.
Kita mulai aja, Pak. Gimana? Dimulai saja. Oh, Pak Indranya sudah hadir ya, Pak Indra?
Ya, udah Pak, udah.
Oke,
Selamat
makasih Pak
sore,
Indra.
Bapak Ibu.
Oke, baik. Selamat sore. Assalamualaikum warahmatullahi wabarakatuh. Nah, Om Swastiastu, Namo Buddhaya, salam kebajikan. Selamat datang kepada kita semua, anggota Majelis HOI dan juga anggota HOI serta BPP HOI yang bisa datang pada hari ini baik secara onsite di Prama Beach Sanur maupun anggota HOI yang sudah bersama kita join di ruang Zoom ya. Oke, baiklah, pertama-tama yang sama-sama kita hormati Ketua BPP HOI beserta jajaran serta anggota Majelis HOI dan semua termasuk juga Ketua Panitia Pemilihan atau Panitia Pemilu HOI Indra dan juga semua anggota INOS dan HOI yang sudah join bersama kita. Baiklah, dengan tidak memperpanjang pembukaan, adapun kegiatan kongres kita hari ini, pertama adalah pembukaan yang sedang dilaksanakan, yang kemudian akan dilanjutkan dengan laporan pertanggungjawaban oleh Ketua BPP HOI tahun 2023-2025 yang akan disampaikan oleh Bapak Profesor Alex Iskandar. Pada Pak Alex, silakan.
Terima kasih Pak Mulda. Selamat sore teman-teman semua. Ini kegiatan 2 tahunan kita, ada ISMOA, ada pemilu, dan diakhiri dengan kongres karena pada saat kongres kita berpindah ke pemimpinan HOI. Jadi saat ini saya akan melaporkan kepengurusan pimpinan HOI 2023-2025. Silahkan. Ya, next please. Oke, kelewatan. Ya, jadi dari kongres kita yang terakhir 2023 di Bandung, pada saat itu terpilih sebagai wakil ketua adalah Pak Agus Hatta. Kemudian kami berembuk, kita membentuk kabinet, di mana dalam kabinet itu ada sekretaris eksekutif Ibu Wati dari Universitas Halua Leo dan bendahara Pak Heri dari UNUT. Dan kegiatan kita sebenarnya direncanakan sejak saat saya menuliskan position paper. Position paper sudah sedikit ngomong mau ngapain gitu. Kurang lebih ada 3 ini mengadakan kegiatan yang daring yang bertujuan meningkatkan literasi ilmiah, mengembangkan media komunikasi daring yang reguler, kemudian meningkatkan partisipasi aktif dengan berbagai organisasi sejenis di tingkat nasional atau internasional. Jadi saya bisa laporkan beberapa hal dalam pencapaian target itu. Yang pertama, keanggotaan. Sekarang kita anggotanya ada 111 yang terdaftar di database. Dari 111 itu ada 91 anggota penuh dan 20 anggota muda, associate member. Dan dari sekian banyak 111 tersebut yang aktif dalam hal ini artinya membayar iuran yang 2 tahunan hanya 41 teman-teman. 46 teman-teman. Ini menurut catatan kita terakhir ketika mau pemilu, karena untuk pemilu kan yang berhak dipilih maupun memilih adalah yang aktif dalam arti kata membayar iuran terakhir. Dan sesuai dengan anggaran rumah tangga kita yang sudah diamandemenkan, kita sebagai BPP dan majelis itu berhak meningkatkan status keanggotaan. Kalau kita periksa yang dulu anggota muda, kalau kita periksa memenuhi syarat untuk naik menjadi full member, maka associate member bisa naik jadi full member. Dan itu kemarin kita periksa ada 1 yang kita ubah keanggotaannya. Selama kepengurusan kami, bersama Pak Hatta, Pak Heri dan Bu Wati, kita menerima 30 aplikasi. Ini dibandingkan kepengurusan sebelumnya agak besar. Dari 30 itu sesuai dengan anggaran dasar dan rumah tangga harus diperiksa oleh anggota majelis, dan yang memenuhi syarat untuk menjadi anggota, untuk full member hanya 10, full member 5 aplikasi bisa diterima sebagai associate member anggota muda. Nah, dari yang sudah diterima ini total 15, kita surati, kita beritahu sudah diterima, yang membayar iuran hanya 6. Jadi itulah situasi kita saat ini teman-teman. Memang organisasi kita adalah organisasi profesi yang keanggotaannya sukarela, kepengurusannya juga sukarela. Jadi ya kita mencari waktu-waktu, Pak Hatta, Wakil Rektor mencari waktu di sela-sela kegiatan untuk bisa ngurusin himpunan kita ini. Itu dari sisi keanggotaan. Sorry. Next. Ya, lalu untuk kegiatan ilmiah yang kita rencanakan secara daring, kita sudah berhasil melakukan 5 kali webinar. Memang untuk ukuran 2 tahun sedikit ya, mestinya 2 tahun 24 kali. Tapi seperti saya katakan, kami semua ini kan keanggotaan kita sukarela, kepengurusan kita sukarela, kita mencari waktu di tengah-tengah kesibukan masing-masing akademik maupun institusional, sehingga kami dalam kepengurusan kami memang untuk daring webinar hanya sempat melakukan 5 kali. Dengan ini judul-judulnya teman-teman. Next. Ya, kegiatan ilmiah umum yang lainnya, di samping webinar yang memang direncanakan cukup reguler, adalah kita setelah berembuk, kalau ISMOA memang keharusan, karena itu tertuang di anggaran dasar, kepengurusan harus melakukan ISMOA setiap 2 tahun. Sedangkan SKOMOA, Summer Course on Modern Optics and Application, ini setelah kita pengalaman 2 tahun yang lalu, kita mencanangkan kayaknya bagus untuk diteruskan, makanya tahun ini kita tetap melakukannya. Namun nanti mungkin dari panitia SKOMOA yang dipimpin oleh Pak Henry Uranus dari UPH, mungkin ada catatan-catatan yang kemarin ini agak berat karena lokasinya berbeda antara SKOMOA dan ISMOA. Mungkin kita bisa pikirkan kalau bisa di tempat yang sama, jadi nggak terlalu repot teknisnya itu. SKOMOA dipandu atau dipimpin oleh Pak Henry dari UPH, melibatkan Udayana, Pak Heri, ITS, ITB, ajak Pak Sulaiman dari Malaya sebagai panitia, pengajarnya dari Andalas, Undip, ITS, UPH, ITB, UNUT, Universitas Malaya. Mudah-mudahan tidak ada yang terlewat Pak Henry ya, rasanya ini. Dan pesertanya ada 118. 74 on-site dan 44 online. Dan di antara 44 online itu kalau tidak salah ada yang dari Yaman. Betul Pak Henry ya, ada yang dari Yaman. Ya. Dari Korea, ya. Perancis juga ada. Ya, Perancis juga ada. Jadi hasil dari SKOMOA kemarin rasanya cukup sukses. Memang tidak sebanyak SKOMOA pertama yang ada pesertanya 200, tapi peserta kita 118 saya kira sangat baik. Dengan tujuan bahwa memang melalui SKOMOA ini kan kita memperkenalkan bidang optika ya, karena mahasiswa peserta gratis, bahkan dikasih makan siang. Kalau mereka ke Bali itu mereka harus mikirkan transportasinya aja itu. Dan kegiatan besar kita yang utama adalah ISMOA. ISMOA ini dipimpin oleh Pak Agus Hatta dan Pak Heri, kerja keras selama sekian bulan Pak ya. Sampai menurut saya ini salah satu ISMOA yang sukses dari sisi kepengurusan. Kalau dari sisi peserta, saya tidak tahu, mungkin masalah ekonomi, masalah pendanaan nasional dan ekonomi dunia menyebabkan kehadiran peserta itu sangat rendah. bahkan mungkin setengah dari yang biasanya. Biasanya kita itu contributed dan oral speakers itu bisa sampai 60 orang. Kali ini kan cuma 30 sekian gitu ya. Dan non-presenters juga biasanya lebih banyak. Walaupun demikian kita masih dapat 15 invited speaker, dan ada 36 oral presenter dan poster. Seperti biasa, teman-teman dari Malaysia yang banyak hadir di sini, teman dari tempat lain, ada satu dari KAIS, satu dari NTU, mana lagi ya, yang selain itu, kayaknya cuma itu yang luar ya. Dari oh ya, Dokter Hailang Dai ya dari Cina, ya. Jadi begitu, dan ISMOA kali ini kita cukup beruntung, kita dapat sponsor dari Nix Lab sebagai sponsor platinum. Kemudian seperti biasa supporter kita yang selalu mendukung kita, Pak Paulus dari Serviam Abadi Murni serta Cat IT, dan kali ini kita dapat sponsor juga dari World Scientific, yaitu tadi voucher best presenters ya. Untuk sisi eksternal kerjasama, kita masih terus menjalin kerjasama dengan Optika dan juga dengan OSM, Optical Society of Malaysia. Dan dalam kerjasama ini bentuknya adalah Memorandum of Understanding, di mana anggota kita kalau ikut kegiatan Optika, kita dapat diskon yang sama seperti anggota Optika mengikuti kegiatan mereka. Dan kebalikannya, anggota Optika yang ikut ISMOA, ikut kegiatan kita, dapat diskon seperti kita memberikan diskon pada anggota kita. Demikian pula OSM. Ya, itu kegiatan dengan organisasi yang serupa, dan kegiatan yang lain memberikan dukungan bagi kegiatan-kegiatan ilmiah yang terkait optik. Kita pada kepengurusan kemarin itu mendukung kegiatan PKM yang dilakukan oleh Teknik Elektro UPH, Pak Henry, dan kita mendukung kegiatan Asian Physics Symposium yang waktu itu dipimpin Bu Wulan ya. Ini yang paling penting, keuangan. Ini berdasarkan laporan dari Pak Heri, waktu serah terima tahun 2023, uang kas kita ada 183 juta sekian. Kemudian selama 2 tahun kepengurusan ini ada pemasukan dari iuran anggota, ada biaya administrasi, bunga, pajak, bayar domain internet, biaya kegiatan kecil. Total sekarang lumayan, naik hampir 20 juta sebagai kas kita. Tapi ini masih akan dipotong, angka ini masih dipotong karena INOS, HOI, itu sudah berjanji akan mendukung SKOMOA. SKOMOA kemarin tidak dapat dana sama sekali, cuman kecil sekali dapat dana dari sponsor. Dan kalau sampai keuangan ISMOA kurang, minus dari semua yang udah kumpulkan nih, maka HOI berjanji akan nutup. Ya, mudah-mudahan minusnya paling cuma 5 juta lah, kalau minus. Begitu. Demikian laporan saya, Pak Mulda sebagai Ketua Majelis HOI. Mudah-mudahan laporan ini bisa diterima. Bila ada pertanyaan, silahkan. Juga dari teman-teman member HOI.
Oke, terima kasih banyak kepada Pak Alex sebagai Ketua BPP HOI 2023-2025. Selanjutnya mungkin dikembalikan ke forum. Apakah ada anggota majelis yang mau bertanya, atau Mbak Ulan yang ada di sini sebagai anggota majelis juga. Pak Indra di Zoom kalau ada yang mau ditanyakan. Pak Hendrik nggak tahu apakah hadir atau tidak ya. Belum. Oke. Jadi kalau tidak ada, artinya kita semua sepakat untuk menerima laporan BPP HOI ya. Oke, jadi dengan demikian kita nyatakan bahwa laporan BPP HOI 2023-2025 disepakati untuk diterima oleh Majelis HOI. Oke, selanjutnya dalam rangka pemilu HOI hari ini kita sudah Pak Indra ya sebagai panitia pemilu sudah hadir secara online akan melaporkan terkait dengan pemilu HOI untuk memilih wakil ketua terpilih dan juga anggota majelis ya yang terpilih. Silakan Pak Indra, waktu dan kesempatannya.
Ya, terima kasih Pak Mulda. Selamat sore Bapak Ibu sekalian. Izinkan saya untuk memberikan laporan terkait dengan pelaksanaan pemilu Himpunan Optika Indonesia tahun 2025. Apakah screen saya terlihat Pak Mulda?
Sudah, sudah.
Baik, terima kasih. Ya baik, Bapak Ibu sekalian, berikut adalah laporan pelaksanaan pemilu HOI 2025. Kami dari panitia, saya Indra Karnadi dan juga di sini ada Pak Suandoko Dwi Isro sebagai anggota. Nah, ini untuk kepanitiaan terlampir adalah SK pengangkatan panitia pemilu yang diterbitkan oleh Majelis Himpunan Optika Indonesia. Nah, di sini memutuskan bahwa susunan panitia pelaksana pemilihan umum HOI 2025 terdiri atas ketuanya saya, kemudian anggotanya Pak Suandoko Dwi Isro. Berikut adalah tahapan dari pemilu HOI yang telah kita laksanakan. Yang pertama, panitia pemilu menetapkan nama-nama anggota HOI yang dapat memilih dan dipilih pada pemilu HOI 2025. Kemudian kita melakukan sosialisasi terkait dengan pemilu tersebut. Lalu anggota HOI yang memiliki hak suara memberikan nominasi 2 calon wakil ketua dan 5 orang calon anggota majelis HOI. Selanjutnya, panitia pemilu menghubungi calon wakil ketua dan calon majelis HOI yang dinominasikan untuk menanyakan kesediaan dari masing-masing calon menempati posisi yang ditetapkan. Kemudian panitia pemilu menetapkan 2 orang calon wakil ketua HOI dan 5 orang calon anggota majelis HOI yang akan maju ke tahap pemilu selanjutnya dan meminta masing-masing calon untuk membuat position paper. Selanjutnya, anggota HOI dengan hak suara melakukan pemilihan wakil ketua HOI dan 3 orang anggota majelis HOI. Dan terakhir, panitia pemilu menetapkan wakil ketua HOI terpilih dan anggota majelis HOI terpilih. Nah, berikut Bapak Ibu, penetapan nama anggota HOI yang dapat memilih dan dipilih telah ditetapkan melalui SK pemilu. Ini ada SK nomor 1 dan juga SK nomor 2. SK nomor 1 ini tentang daftar anggota yang dapat memilih dalam pemilu HOI 2025. Dan SK nomor 2 terkait dengan daftar anggota yang dapat dipilih dalam pemilu HOI 2025. Ini berdasarkan pada anggaran dasar yang telah diamandemen dan kemudian anggaran rumah tangga dari HOI. Nah, berikut adalah lampiran terkait nama-nama dari anggota yang dapat memilih. Jadi berdasarkan SK tersebut terdapat 40 orang anggota HOI yang memiliki hak untuk memilih. Dan kemudian sedangkan untuk yang dapat dipilih terdapat 35 orang anggota HOI yang dapat dipilih sebagai wakil ketua. Dan terdapat 34 anggota yang dapat dipilih sebagai anggota majelis HOI. Nah, dari data tersebut kemudian kita lanjut ke tahap sosialisasi pemilu HOI. Jadi kita mengenalkan tentang pemilu HOI secara singkat kepada tiap anggota. Kita lakukan sosialisasi melewat WA group ketika itu. Nah, dari sana kemudian kita lakukan pemilu tahap pertama yaitu nominasi calon yang dilaksanakan pada tanggal 27 Juni 2025 sampai tanggal 4 Juli 2025. Dari hasil nominasi ini yang tadi diikuti oleh 40 orang pemilih, terdapat 28 yang memberikan hak suaranya yaitu dengan tingkat partisipasi mencapai 70%. Di sini untuk nominasi calon anggota dengan suara tertinggi adalah Pak Rahmat Hidayat, diikuti oleh Pak Husin Alatas dan juga Ibu Restuti Wulandari. Nah, ketika dari panitia menanyakan kesediaan, Pak Rahmat menyatakan tidak bersedia dan ingin memberikan kesempatan sebagai wakil ketua kepada anggota lainnya. Nah, sehingga kita menetap untuk calon wakil ketua HOI 2025-2027 kita menetapkan 2 orang yaitu Pak Husin Alatas dan juga Ibu Prestuti Wulandari. Nah, untuk nominasi 5 calon anggota Majelis HOI, berikut adalah hasil nominasi dari anggota. Pak Rahmat urutannya adalah Pak Rahmat Hidayat, kemudian Pak Henry Uranus, Pak Isnaini, Pak Husin Alatas, dan Pak Heri Suyanto. Kalau dilihat dari 5 teratas. Nah, di sini ketika kita menghubungi masing-masing anggota tersebut, Pak Isnaini menyatakan tidak bersedia. Nah, Pak Husin sudah masuk ke dalam calon wakil ketua, sehingga kita perlu menambah 2 orang anggota, dua anggota lainnya untuk masuk menjadi 5 calon anggota majelis, yaitu Pak Ai Bahtiar dan Ibu Maria Margareta Sulianti. Nah, selanjutnya berdasarkan hasil tersebut, panitia menetapkan bahwa dengan pada SK nomor 3 SK Pemilu 2025, panitia menetapkan bahwa calon wakil ketua terpilih untuk pemilu 2025 adalah Prof. Husin Alatas dan juga Dr. Prestuti Wulandari. Sedangkan untuk calon anggota majelis terpilih adalah Pak Rahmat Hidayat, Pak Henry Uranus, Pak Heri Suyanto, Pak Ai Bahtiar, dan Bu Maria Sulianti. Nah, selanjutnya dilakukanlah pemilihan wakil ketua HOI dan anggota majelis HOI. Nah, berdasarkan hasil pemungutan suara, untuk wakil ketua, ternyata Bu Prestuti Wulandari dan Pak Husin Alatas mendapatkan jumlah suara yang sama. Dan sedangkan untuk anggota majelis, kita lihat Pak Rahmat Hidayat, Pak Henry Uranus maksudnya mendapatkan suara tertinggi, diikuti oleh Pak Rahmat Hidayat, kemudian oleh Pak Ai Bahtiar. Nah, jadi karena Bu Prestuti Wulandari dan Pak Husin Alatas mendapatkan jumlah suara yang sama, sehingga kita mengadakan diskusi, kemudian dari hasil diskusi antara Pak Husin Alatas dengan Bu Prestuti Wulandari, disepakati bahwa untuk posisi wakil ketua terpilih pada kepengurusan BPP HOI masa bakti 2025-2027 akan diisi oleh Dr. Prestuti Wulandari dengan nomor anggota 22012120042. Dan untuk posisi anggota Majelis HOI terpilih masa bakti 2025-2027 akan ditempati oleh Prof. Henry P. Uranus, kemudian Profesor Rahmat Hidayat, Profesor Ai Bahtiar, dan Profesor Husin Alatas. Demikian Pak Mulda, apa yang dapat kami sampaikan terkait dengan pelaksanaan Pemilu Himpunan Optika Indonesia 2025. Terima kasih.
Oke, terima kasih banyak Pak Indra sebagai Ketua Pemilu HOI dan juga Pak Suandoko ya sebagai anggota. Sebagaimana tadi sudah kita dengarkan, sudah terpilih Wakil Ketua HOI terpilih, yaitu selamat Bu Dr. Prestuti Wulandari. Dan juga telah terpilih juga 4 anggota majelis, yaitu Prof. Henry Uranus, kemudian Prof. Rahmat Hidayat, Prof. Ai Bahtiar ada hadir secara online, dan Prof. Husin Alatas. Oke, demikian hasil pemilu saya rasa kita bisa terima ya sebagai majelis. Jadi dengan ini kita sepakati nama-nama yang sudah terpilih tadi itu kita terima laporan dari Ketua Pemilu dan kita sahkan sebagai anggota majelis dan wakil ketua terpilih. Oke, selanjutnya serah terima jabatan Ketua HOI dari Ketua BPP sebelumnya, Pak Alex, ke Ketua HOI 2025-2027, Pak Agus M. Hatta. Silakan Pak Agus dan Pak Alex. Aris. Oke, mungkin sedikit menjelaskan alasan pemilihan ketua dan anggota panitia pemilu berdasarkan anggaran dasar dan anggaran rumah tangga HOI, bahwa panitia yang melakukan atau sebagai panitia pelaksana pemilu itu harus orang yang tidak bisa dipilih ya untuk jabatan baik wakil ketua terpilih maupun majelis. Jadi karena alasan tersebut di rapat majelis diputuskan Pak Indra dan Pak Suhandoko yang memenuhi syarat tersebut. Oke, selanjutnya mungkin sambutan dari Ketua BPP HOI yang baru, Pak Hatta, silakan Pak.
Baik. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Selamat sore dan salam sejahtera untuk kita semuanya. Yang kami hormati segenap anggota Himpunan Optika Indonesia dan juga yang kita hormati segenap majelis yang terpilih dan juga wakil ketua terpilih dan juga Presiden HOI periode 2023-2025, Bapak Ibu semuanya. Jadi kita bersyukur sekali hari ini bisa menyelesaikan rangkaian acara kongres dan tentu saja hajatan yang besar ya bagi HOI yaitu ISMOA tahun 2025. Ini sekaligus mengumumkan ini terima kasih kesediaan Bapak Ibu. Jadi secara pengurus ada wajibnya adalah 4 orang, tapi di sini mengingat kita perlu dukungan, jadi ada ketua yang sudah kita bentuk terlebih dahulu, ya nanti mungkin ada tambahan. Jadi kita ada Bu Ulan selaku wakil ketua terpilih, kemudian Pak Heri Suyanto selaku bendahara, Bu Wati selaku sekretaris, dan ini Pak Mulda ya dari nanti kita minta untuk menjadi ketua bidang ilmiah dan publikasi. Ya, jadi Ibu Bapak sekalian, tadi pada waktu penutupan ISMOA kita ada potensi besar ya himpunan optika itu untuk bisa ikut terlibat ya dalam tadi yang saya sebutkan ada roadmap untuk semiconductor dan photonics. Nah ini kita perlu ada program bagaimana nanti mungkin beberapa bulan mendatang, ini nanti Pak Alex dan kawan-kawan kita coba membuat roadmap photonics R&D ya dan pendidikan di Indonesia. Ini kita untuk misalnya sampai 10 tahun mendatang, dan bagaimana peranan dari Himpunan Optika Indonesia. Kemudian yang kedua, terkait dengan ada peluang dengan pendanaan LPDP kita bisa menciptakan atau membuat program apa itu namanya pasca sarjana yang kreatif, pasca sarjana terkait dengan photonics. Jadi misalnya ada beberapa kampus ya, jadi mahasiswa bisa mendaftar di kampus masing-masing. Nah kemudian semester 1 di kampus A, semester 2 di kampus B, di luar negeri dan seterusnya. Nah ini bisa kita buat dan kita bisa usulkan ke kementerian dengan dukungan dana LPDP. Kemudian Bapak sekalian, kita akan melanjutkan ya tentunya sebagian dari keberlanjutan organisasi. Ada 2 paling tidak yang perlu kita lanjutkan. Yang pertama adalah untuk menjaga dan meningkatkan anggota kita. Nah, ini nanti tugas kita ya Pak Eri, Bu Ulan ya bagaimana nanti mengajak berkomunikasi silaturahim kawan-kawan yang seharusnya ikut bidang optika tapi belum bergabung pada kita. Itu yang pertama. Kemudian yang kedua, kita akan melanjutkan lagi webinar dan tentu untuk menjamin ISMOA ke depan ini makanya sudah ada ketua bidang ilmiah dan publikasi. Jadi kita merencanakan ya kegiatan-kegiatan webinar mengenalkan bidang optika ke masyarakat luas. Baik, itu saja sebagai sambutan dari kami dan tentu kami mohon bantuan, mohon doa restu ya dari Bapak Ibu anggota HOI dan khususnya juga Pak Alex ya, kami mohon selalu advice dan dukungannya ya dalam kepengurusan mendatang. Demikian Bapak Ibu, terima kasih atas kepercayaan dan mohon maaf apabila ada hal-hal yang kurang berkenan. Terima kasih. Assalamualaikum warahmatullahi wabarakatuh.
Terima kasih Pak Agus Hatta. Selanjutnya Apakah perlu diskusi, Pak? Oke. Oke, sebelum kita tutup kongres kita, mungkin terakhir kalau seandainya ada saran, masukan dari Bapak Ibu anggota majelis semuanya, baik yang hadir onsite atau yang di Zoom, atau anggota INOS yang lain, kalau ada saran atau masukan untuk kegiatan-kegiatan atau yang mau didiskusikan dengan BPP HOI, kita persilakan. Ya, itu ada sih. Sudah dituliskan. Ya, bisa juga di absen ada sih saran dan masukan untuk BPP HOI berikutnya. Bisa kita pakai itu juga. Pak Rahmat, ada yang mau disampaikan saran atau apa sebagai anggota majelis? Belum. Oke. Pak Alex, mungkin ada yang mau disampaikan pesan dan kesan atau apalah.
Satu aja pesannya. Pak Henry Uranus, Pak Rahmat, Pak Husin, Pak Ayi harus memilih siapa yang jadi ketua majelis. Karena sekarang muda juga sudah pensiun nih. Jadi nanti mohon berdiskusi para anggota majelis yang dipilih ya. Saya juga di majelis tapi saya kan sebagai mantan ketua. Jadi yang jadi ketua adalah yang dipilih. Silahkan Pak Henry, Pak Rahmat, Pak Husin, Pak Ayi. Boleh. Ya, atau katanya kata Pak Heri langsung aja sekarang. Ada empat-empatnya ada di sini. Pak Ayi ada, Pak Husin ada, Pak Henry, Pak Rahmat, siapa yang mau sukarela, sukarela.
Ya, kayaknya Pak Husin ada yang mau disampaikan. Silakan Pak Husin.
Oh, enggak, cuma nyalakan kamera aja. Saya ikut aja.
Bagaimana Pak Ayi?
Saya calonkan Pak Husin aja. Saya sudah kirim di chat, Pak.
Kita voting aja bagaimana.
Ada di chat,
Berempat,
Ada di
voting
chat.
berempat. Ya.
Ada di chat.
Saya pilih Pak Ayi.
Ya udah Pak Ayi aja yang
Pak Husin.
Pak Ayi aja yang belum pernah jadi ketua.
Saya setuju Pak Ayi jadi ketua.
Berarti Pak Ayi ya sebagai ketua majelis. Ya, gimana Pak Ayi? Bersedia?
Pak Husin aja, Pak Husin. Berpengalaman.
Bagi-bagi tugas Pak Ayi.
Ya.
Kadang bukan Pak Ayi.
Baiklah, kalau tidak ada yang
Oke, terima kasih.
Mohon
Oke, terima
dukungannya
kasih.
dan kerjasamanya.
Ya, Pak. Oke, jadi dengan demikian berakhir acara kongres kita. Pertama-tama tentunya terima kasih banyak kepada BPP HOI 2023-2025 atas kerja kerasnya ya dalam menyelenggarakan semua kegiatan, dan juga mungkin semangat dan selamat juga Pak Agus Hatta, semoga sukses detik ke depannya. Oke, saya kembalikan, saya tutup. Selamat sore, Assalamualaikum.
Waalaikumsalam warahmatullahi wabarakatuh. Terima kasih. Terima kasih Pak Indra.
Terima kasih Pak Ayi.
Foto bersama dulu, Husin, tolong screen-nya. Putu. Oh, Putu udah hilang. Ini siapa ya? Bentar. Kamu kan udah anggota. Tegar udah anggota.
Baik, saya izin lab ya. Terima kasih semuanya.
Ya Pak, terima kasih Pak.
Ya, saya izin live juga ya.
Ya, izin live.
Terima kasih banyak.
Wah, Pak Husin, Pak.
Selamat.
Ya,
Oh iya, iya. Oh iya, Oh, ini kita bikin terus kita kirimkan. Ya, yang
Recording stop.